I really appreciate the chance. Test 1 2. Okay, can you speak? Words and Mama, put on unmute corner. You can participant la bra. Sirintip na ni pun. Test 1 2.
Hello, hello.
From there, not from there. Test 1 2.
คุณเราได้ยินไหมคะ
1. Okay.
เราได้ยินไหมคะ
1.
One. Yeah, already. Hello,คุณเรา
Can Punem can hear me? Song message หน่อยว่าได้ยินไหมปันปะ Test 1 2. Hey, audio from there not coming to this speaker. Or maybe I need to change here, right? Just a second. Audio here. Okay, maybe put that. Okay.
Hello ได้ยินไหมคะ
Okay. Okay, good. Okay, this is okay. Working. Panapa, RM, can you hear us? Please send me my WhatsApp message or line message that you received. Not a problem. This is okay. Yeah. Let's check other one. Okay. Chale.
এখানে কতজনের মতো সিট করা আছে এখন? তো প্রথম এটা কতটা খালি তো এটা কোনটা? হ্যাঁ এটা বড় মানে ডিসেম্বর লাগে এটা অলরেডি সাজা আছে না এটা হতে পারে তো আমাদের স্টুডেন্টরা প্রথম সপ্তাহে জানি না এটা স্টুডেন্টরা একটু না ওটা নিয়ে আমার কোনো অসুবিধা নেই ইত্যাদি করে তাই তো ওটা কিন্তু রেকর্ডে তাহলে কি ওখান থেকে হবে আদার্স room settings then have some that's ready. Sorry. Right. আমার অনেক
রাজস্বী এইটা আমারটা এটা থেকে প্লে করবো হ্যাঁ
আচ্ছা
ঠিক আছে
অসুবিধা নেই
তুমি দেখছো তাই তো এটাতে
আমি হলবন দিব্যেন্দু আসছে এটা
দীপেন্দু এটা দেখছো তাই তো আমি এটা থেকেই প্লে
ঠিক আছে
ফার্স্টে বোধহয় আরশাদের আছে
so which one
fatigue and rub fatigue and wear
okay
yeah the first one
can I copy from
yeah
here?
yeah
This is room one, correct?
Morning, yes. Even morning or afternoon?
12:10 to 12:30. I think it should be the morning session.
12:10 to 12:30. 12:1.
Morning session. Yes.
You just remove that one. You have to delete that one. I think that was the older one.
Okay.
Just open it one side.
Mhm.
Can I just quickly go through?
You already put that?
Yeah, I have already.
Just a second. Did you already save into it or what? Did you save it?
Yeah,
I've saved it.
Into the,
Yeah,
you know, the place,
yeah,
right?
yeah,
Yeah, okay, fine.
I was just checking that whether all the slides are showing up.
See, whenever you share the screen, right? You know, listen to me for a minute. You have a display settings, duplicate, okay? You'll find like this. So you ask it use new hardware. And then this, okay? When you do that one, you will come back again, I think.
Mhm.
Okay, and so in the beginning they may not able to move the slides properly.
Mhm.
Okay, just click for a minute, put the mouse here, and then after that remote works here. Okay. Yeah. So
I think now you can remove the pen drive.
Yeah, yeah, just one second.
so you remove the old file, right?
Yeah.
Yeah, I
Okay, so that
replace.
yeah. Thank you.
So Param, I need to play it from here.
Look, in that case, you know, when your presentation is on, then you use it.
Okay.
So can I include into my folder as a or not the
Yeah,
file?
you can, but is it going to be published somewhere?
Basically, I'm going to put an e-handbook. Whatever is allowed to include, I will include.
Yeah, that is because some of them are unpublished. I cannot.
Understood. So you can remove those ones later on.
Yeah,
you
and
can-
then I can send you.
Yeah,
the files.
fine, that's fine.
That's
So in
okay.
that case, you just run through. Yeah.
I think we have a chance to edit also later on.
Yeah.
For this.
Yeah. Basically, I'm going to put together.
There are no
booklet,
issues.
you know, so
Main
that-
things should be there on certain maybe the critical information.
Of course, without before it goes in public, I'm double
Yeah,
check.
yeah.
That's see, it can tell them.
Yeah.
So that is what
No, like,
I call sir. What I was telling Param, some of the works which are unpublished. So we'll delete and share the remaining copies. Because the thing what yeah, that's what he said.
here I will double check before it goes out. Okay, so yeah, no worries about it.
For all.
I know about rules and regulations of the data. Okay,
The
good.
most trickiest part.
I know. Yeah. You see, yesterday this Amir is saying that don't publish. We want to do patent. Right? If you want to get more patent, don't publish it.
But since they do not really want to so they want to publish the public document.
But you know, you protect publishing line.
The thing is that how you are using it, how others, you can't go door to door and like there are many companies that don't even follow publication. The moment you get it, that's a public document. You can use some of the information there and you can see.
It works for the companies like you guys, you know what to do. But if you are like an academic, right, see how it can become. So he has to go somewhere, put it in public domain. So,
No worries, like, I mean, absolutely fine, just 1 or 2 pages from there. I'm going to send you the.
whatever is allowed, whatever is not allowed.
Yeah, we'll see if you want.
Got it? Fine. See, the moment is this, the is not in yet. So basically, I run the video like this.
I really appreciate the chance to be part of this Rubber Innovations Forum and talk with you today about how to use the RPA to characterize thermal stability of raw elastomers.
You can sit there also. Can sit there.
No,
Only
here.
Okay.
Only here, yeah. See, whenever the video comes like this, right? You can just webcams, hide all webcams. People see us, but we don't need to see ourselves on the screen. Yeah. So, and this is a minimizer. Yeah. I don't know. Maybe we have to delay a little bit today. It looks like not people come. So,
I started around 7. Woke up at 5:15.
okay.
But not from Frankfurt.
Somewhere is home is
It's not far from my. Went to sleep at 1 a.m. Was working on the pages.
the last minute.
That's all it had a sleep and reach around 10 p.m.
While traveling, that is the best time to
Yeah, that's right. In fact, I was doing some last moment change while sitting in the car also. Today, while coming transit,
Don't talk about. Don't tell it to others. I've done this one long time ago.
actually all idea crystallizes the more you go towards.
that's right. I was singing in the car.
Actually, I always feel that if you have pressurized time, then only the best comes out. If you say I have one more month, you have you got the best or don't see the last tonight, tomorrow is going to be too much. The last 1 hour, very 1 hour only. Yeah. You can shorten it away.
So what is very true for the rubber fraternity because the training is crystallization is happening here.
Yeah.
The stressing is
Imagine the theory.
matched with the future.
Till yesterday night, early morning rather, I would say I was very okay with the presentation. Then while sitting in the car, I thought of revisiting all the things. Then I realized, okay, how will I pitch the next page? I should have some filler over there. Okay. Then I started again.
I don't see to say that it will start from here. People should not go there right now.
Yeah.
Stand there.
Yeah. And where are your students?
Or one.
It's mangrove 1, mangrove 2, that's the big area. You're going back.
Yeah. On the way.
Actually, this is the pipeline. But
No, the issue is more from the institute. With central government, China does
okay. From our side.
our side. With more.
Actually, here,
September একটা আছে। আমাদের তো বীজদের না শুনতে আসছে
নেই। Good morning.
Sir, I haven't talked to you yet. Now, same department.
Yeah, we are.
You're tuning.
Yes. Yeah. Also student long back. Yeah.
Long back?
That was also student.
But now you are a staff, as a colleague.
Yeah, yeah. Other
Whether or not, what did you say about me?
Oh, yeah. You are good things on this.
Old friend. Old from old.
And the first party I would say what she joined was
What
my
your
defense
defense party,
My defense
after
party.
defense party. Was
in the
probably first week of after my arrival. Yeah.
okay.
Because he was about,
With it and you do.
he was, I went there into a postdoc
Uh-huh.
and it was about to
Leave.
to leave, yeah. So yeah, the defense.
And already you made for support.
Yeah. But I met him earlier than that. I mean, he came to the conference in Thailand. No,
Really?
after the conference. So I met him before that.
Before?
Yes.
So he's my one of the. So he placed you. So maybe you know that for 5 years he was there another IT was the first day and IT partner. That time I moved from IT partner. That was the time he placed me.
Where he's now working.
Yes, yes, right, right. So my other advisor.
So is this what? Is it? You got it.
Yes, yes.
So your presentation will be.
Yeah, yeah.
Now the problem is we have to choose. We have two rooms.
These are my in terms of performance and we are also working on something energy architectures using renewables. So something.
I mean, in energy
In
harvesting
that's right.
material.
Yes, that's right. Also, you have the natural rubber and the oxidized. Couple of
Photo days. Right?
Also, we do the Supplies. Maybe you are around. My talk is at 9:50. And just talks. Third card.
Group one.
Again, this is common. First one is common. And then experience.
Sounds like.
Put him the Chris as a panelist so he can see us now.
Did you join?
Yeah,
You said good morning to him?
yeah. Good evening to him. Oh, almost
yeah.
finished, yeah. Hi, Chris, can you hear me?
I can hear you.
Your voice is low. Just a second, let me check. How about now? Can you hear me well?
I can hear you just fine.
Okay, great. Can you turn on your camera? Have a look, please.
I think it's on.
Okay, just give me a second. Okay, show all the cams. Okay, that's there. Okay, you want to say hi? Somebody
Hi,
know?
Chris.
Hi, Kanika.
Yeah. What
You have
time
a
is
nice
there?
conference so far. It's
Yeah.
Can you see it's the dark?
Yeah, we had a great day yesterday.
Good.
Hi, Chris. This is King Shuk.
Hello.
Oh, good to see you here. But next time, definitely in person. Huh?
I think so.
Yeah. Okay, good. So yeah, yesterday it went very well, I would say. There are a lot of people, and we also, felicitated three very senior Rabat technologists from this region. So it went very well, and the lectures from delegates and the sponsors are very happy also with day one. And today we will start with you very soon.
Okay. I will turn my camera off and wait for questions at the end. Yes.
Yes. Yes, please. Thank you so much.
We may little bit delay, little bit, Chris. Okay. Hey, this is Param. You recognize me, I guess, right? Yeah.
Of course.
Yeah. Yes, man. I will once we start, you will know what time we started. Yeah. Okay.
Okay. I'll mute myself and stay tuned.
Sure. Sure. Thanks. Okay, let's wait for a little more delay. Yeah, let's some more people to come so that we can start maybe. Yeah, 5 more minutes. Yeah, so let's. Oh, you guys had a good sleep? Yeah. Yeah. This presentation here. So. Is online too. I sent a message to me this morning to them. Yeah, we want to. Ah, I not open yet. Okay, that's like.
Yeah.
Yeah. Okay, let's do that one.
Both of us.
No, but it is like it's good that and it's expensive to get them because so if you go to a province next to there on that website cheaper and quiet. But if you go but we have campus that's good. Did you watch the
Chris, we may little more delay, Chris, because we're waiting for a few more participants to come in. It's been early morning here in for Indians, little bit. So please stand by.
No worries.
Thank you. I know it's almost getting at midnight for you guys. Yeah. Get some nice hot coffee, man. Yeah.
Okay.
Good morning, ladies and gentlemen. Welcome everyone on day 2 of this Kolkata Rubber Forum. Today, our first keynote speaker is Dr. Chris Robertson. He's online and he'll deliver his talk through video. And let me very briefly introduce Dr. Chris. Chris is a principal consultant at Polymer Technology Services LLC in Akron, Ohio, USA, a company that he founded in 2021 to provide technical consulting and training for the rubber industry and the polymer technology field in general. Chris has more than 20 years of experience as a materials scientist and engineer in the tire, synthetic rubber, different rubber additives, and plastics industries, including 9 years working in R&D at tire companies. Since 2020, Chris is serving as the editor-in-chief of the scientific journal Rubber Chemistry and Technology. I think all of us know about this prestigious journal, and was an associate editor of that journal for 10 years prior to that. Chris also teaches online graduate courses on elastomer science and technology as an adjunct professor in the Department of Plastics Engineering at the University of Massachusetts. Chris has expertise and research interest in polymer viscoelasticity and rheology, rubber compound development, and elastomer fracture behavior. Okay, with this brief introduction, please join me in giving big hands for
I really appreciate the chance to be part of this Rubber Innovations Forum and talk with you today about how to use the RPA to characterize thermal stability of raw elastomers. And this work was conducted with my colleagues at Zhongsha Rubber in Hangzhou, China, Dr. Zhepun Wang, Dr. Minglong Gao, along with our collaborator from ACE Laboratories, Doug Foster. There are a lot of reasons for using rheology to take a look at thermal stability effects. There's a big need to look at different alternate polymers in the industry and have something beyond just simple Mooney viscosity and specifications provided by the supplier. We can do a quick check of thermal stability, and you'll see later that can really reveal some huge differences of what nominally are two polymers that have the same grade name. Also, I think many of you are aware and are contributing to the hunt for new stabilizers to protect elastomers against oxidation and ozone attack because of the issue with 6-PPD. And so a quick rheology test that can help in the screening of new AO alternatives would be helpful. The main tool we used is a rubber process analyzer, which I think many of you are familiar with, shown here with the test geometry over here. It's an oscillatory shear rheometer, and as such, it's very sensitive to polymer macrostructure. And that's exactly what changes when the material goes through thermal oxidative changes. So it's the right tool to measure what's going on. There's also something interesting about the RPA that maybe we don't often think about. We know it's a sealed cavity because that's how it forms a sample. You push down the platen, the rubber squeezes out, and so it's excellent for sample preparation and automation. We understand that. And that geometry also, from another side, because it's sealed, is a low oxygen environment, very similar to what's going on in the internal rubber components of a product, like the belt rubber component of a tire. So we saw the utility of using rheology, although it wasn't the main focus, but to take a look at thermal stability. In this case, we had a high temperature bound rubber test. We wanted to see what was happening at the high temperature. And if you do a time sweep, you can see that at 90 degrees and 110 degrees, the material is fairly stable. However, again, this is the gum SBR, no additives, no cross-linkers, sealed cavity, low oxygen. Even still, it cross-links all on its own, and you can easily detect that. And you say, well, is that really cross-linking just because G prime went up? Absolutely. The sample turned yellowish, and we put that sample in solvent, toluene, and it never dissolved. It just formed a swollen mass. We took the same sample after the same amount of time in 90 degrees C, and it completely dissolved. And so, yes, indeed, this is cross-linking of the gum polymer all by itself. Natural rubber, on the other hand, in this case, we wanted to verify that the material was thermally stable so we could do filler networking dynamics experiments. And so we tested the gum and natural rubber. And indeed, it was stable at the temperature we were interested in. However, you can see as you go to higher temperature, there is chain scission. So in this case, the viscosity goes down opposite to the cross-linking effect. So I'm going to show you in our new study a couple of different ways of looking at thermal stability data from the rheometer. One is a time-resolved rheometry experiment, and the other one is especially useful for looking at series of data at different temperatures, what's known as a Van-Gert-Palman plot. It's used to detect long-chain branching, and it's also useful to follow thermally induced branching and cross-linking. And then we did an antioxidant study taking a look at natural rubber and butadiene rubber with different levels of common antioxidants. And we did that with the RPA in the sealed test cavity. Again, that's a low oxygen environment. And we compared that to an Aries G2 rheometer where we had an air surrounding the sample. So time-resolved rheometry, you have some change in the material happening shown by this red curve. That could be cross-linking, or it could be chain scission, some change in the polymer macrostructure. And you want to follow that as a function of time. And you do that by having a very short snapshot frequency sweep. So this is a 5-minute frequency sweep, and you periodically apply that frequency sweep as the changes happen. So that's called time-resolved rheometry. And we have to keep the amount of time short that we're doing the frequency sweep so that it is indeed a snapshot and the material's not changing significantly during the actual frequency sweep itself. And that was a technique that was kind of pioneered by Henning Winter and his group. And others have used it throughout the years. So if we apply that kind of protocol to butadiene rubber, you can easily see in the low frequency region is where all the action is. That's where macrostructure effects show up. And you can see cross-linking, tan delta goes down, and the viscosity goes up. So that's the signs that the material's branching toward cross-linking. So that's BR, tan delta goes down, viscosity goes up. Natural rubber is exactly opposite. Natural rubber becomes more mobile, less elastic, right? Tan delta goes up, and the viscosity goes down. And so this kind of testing using this time resolved rheometry can pick up these differences. If you look at a fairly stable material like butyl rubber, viscosity really shows no change. Look at this. This also shows you, you need to have a good RPA when you're doing this kind of testing. Is look at this right on top of each other. However, there is a subtle bit of chain scission that shows up, which makes sense. It does have the isoprene comonomer in a small amount, just a tiny amount, I would say, of chain scission, but fairly stable. Instead of looking at this whole frequency sweep, we could just do a time sweep, or just take a look at the time-dependent data from the larger experiment at this lowest frequency, because that's where the biggest changes are happening, right? If you looked at a time sweep over here, you're not going to see much. But you look at a time sweep over here, this is where all the macrostructure changes are happening, typically at low frequency. And so we're going to take a look at that time-dependent tan delta, time-dependent viscosity. So now we can compare the different types of elastomers. So here's tan delta versus time. The ones that cross-link, BR and SBR, they go down, right? Natural rubber, the blue one, chain scission, it goes up. And then the other two are fairly stable. Butyl rubber, fairly flat, I would say slight chain scission. And EPDM, another more stable elastomer, it has slight cross-linking. We also took a look at an anionic lithium polymerized BR, which has a very narrow molecular weight distribution. So this is more of like a model, well-defined polymer versus these are commercial elastomers. It also has the same effect, actually even more pronounced. This had to be on a different scale because this material has true flow behavior. So it's very sensitive to cross-linking. Viscosity is opposite, right? So the changes were in tan delta, you flip that. So what do I mean? Well, cross-linking, tan delta goes up. Chain scission, cross-linking, viscosity goes up. Chain scission, viscosity goes down, and stable materials are flat. And so I show these different elastomers because you have some feeling about whether they're historically more stable, or they cross-link predominantly, or they scission predominantly. And so this is a reality check that this kind of testing does in fact pick up what are the known differences among families of elastomers. So it should give you some confidence that it's giving you the right insights into what's happening, right? Natural rubber chain scission, butadiene rubber, SBR crosslink, and the stable ones are measured as fairly stable. Another useful tool, especially when you're trying to sort through data at different temperatures, is a Van-Ger-Palman plot. And if you plot the data as phase angle, this is delta, right? And G star, sometimes people normalize G star by the plateau modulus, but you don't need to. You could just plot versus G star. And if you collect data at different temperatures for a linear polymer, that's this one here, you don't even have to make a master curve. When you plot it this way, they create a master curve on their own. And so you see that's the behavior. For a linear polymer, when you have branch polymers, you can see what happens. You can see that these go in this downward direction of phase angle. And so this is used as a way to detect different kinds of branching, in this case, polyethylenes. The same has been done in butadiene rubbers. So this is a nice study by Parisi Coppola and co-authors. And again, the linear material of these, what's shown here, that's the linear behavior. And then as you go down, you can see more branching showing up in these samples. And they plotted long chain branching amount versus this phase angle in this highlighted region here. And so you can see that you can detect the presence of long chain branching. This Vanguard-Kalman plot is very useful also if you just want to test whether your material obeys temperature frequency superposition, WLF kind of behavior, but only if it's uncross-linked, because this is the terminal flow behavior that's being monitored. Doesn't work for cross-linked materials. So we did this on that model lithium butadiene rubber sample. If you recall, that was the one that narrow molecular weight distribution. And you get this master curve behavior that I just talked about if you look at data at different temperatures. Again, you don't have to make a master curve. You just plot it this way, and it makes its own master curve. That's the beauty of it. It's a good test of time temperature superposition. But look at this. After 140 degrees C, we start to see some departure from the master curve. So this. And so somewhere between 140 degrees C and 160 degrees C, this material is starting to branch and eventually will become fully cross-linked. Look at the data if you just looked at the raw data like this, tan delta versus frequency at the different temperatures. It's really hard to sort through. And so that same data here, you convert it into this Vanguard-Kalman plot. You don't do any shifting. You don't do anything. You just plot it this way. And look what you can do. The master curve automatically forms, and you can see the branching departures from that. So now you know exactly at what temperature things are starting to change within that material. So you can do that to compare different types of elastomers. In this case, we did a temperature series starting at 100 degrees C, same sample. The previous testing was done with fresh sample at each temperature, and this is a more practical test. You load a sample, you set up the series, and you walk away and you get all this data. And it then returns after going up to 180 degrees C, it returns back to 100 degrees C. And so again, you don't really know how to handle the data when it's tan delta versus frequency at all these different temperatures. But when you plot it over here as a Vanguard-Kalman plot, you can see the very classic signature of branching and cross-linking. So that's SPR 1500. What if we look at SPR 1502, another type of emulsion SPR, different grade? And these are on the same scale. So you can see this particular sample of SPR 1502 has much bigger changes, less stable in this procedure. So this is the one that's really shows that we should be doing more of this kind of testing. So this is BR 9000. It's a high cis butadiene rubber. This is sample G, fairly stable. So you can see not very many, very, very low degree of changing behavior here. The same BR 9000 grade, but a different sample from a different supplier. And now suddenly huge amount of instability showing up in this test. And if you compare the changes that happen between the start and the end of the test, let's take a look at the BR9000. They both start out with about the same viscosity. So if you did a Mooney test or even a frequency sweep at 100 degrees C, these two will look very similar to each other. But after going through that increasing temperature up to 180 degrees C, look what happened. This one went up a little bit in viscosity, but this one went up almost by a factor of 5, at least a factor of 4. And so this kind of testing can reveal those huge changes. And look what happened at the tan delta at the end of the test. It almost looks like fully cross-linked rubber. So you can also do a quick test, just a simple time sweep at different temperatures. So if you really want a fast test, a 10-minute test at 180 can already show the differences here. The only thing about 180 is that you might lose, because the degradation is so fast, the material's changing so quickly, you maybe lose some of this initial behavior. Maybe 160 is a good balance. But again, you can see, you can do a simple time sweep and pick up the differences. And just to take a look at another type of BR, this is CB22. It looks a lot like BR9000 in terms of, some small changes, but fairly stable. And this sample is quite bad. So the last thing I want to take a look at is an antioxidant study. We looked at 2 polymers, natural rubber and butadiene rubber, 3 antioxidants, EMQ, 6-PPD, and IPPD, and 2 different loadings. And these were mixed on a 2-roll mill. And then they were tested in the RPA, like we've been talking about so far, but also tested in an air environment with an Aries G2 rheometer. So we have an oxygen-rich environment over here, and we have a low oxygen environment over here. So you can follow the time dependence. In this case, we use that very quick test at 180 degrees C. So these tests are 10 minutes long, and you can see butadiene rubber cross-links slightly. And the surprising thing is adding the antioxidants actually caused more cross-linking. Same thing over here on the viscosity. There's a good reality check here. If you take a look, this black one is the BR with no extra antioxidants. Of course, it has some antioxidant in it from the manufacturer, but we did not add anything extra. And so you can see it does have some cross-linking. Good reality check is viscosity goes down when you add 3 parts of AO. That makes sense, right? These are like plasticizers, if you will, small molecules. And consistent with the tan delta, we get more cross-linking with the antioxidants. So a little bit surprising. So we can take a look at it this way. We can take a difference between the end point and the starting point and get a delta. We can do that for eta star of viscosity, and we can do that for tangent delta. And this line is completely thermally stable. And for tan delta, up is scission, down is cross-linking, and for viscosity changes, it's opposite. Above the line is cross-linking, and below the line is scission. And what you see is there's no benefit. In fact, the changes seem to get larger in the presence of these stabilizers. We compared to the higher oxygen environment in the Aries G2, same plotting of the data. In this case, less negative effects, I would say, in general, but still no clear stabilization effects of the antioxidants. So if they're having an effect, they should be moving toward this line, right? So here's the material, control material without any antioxidants, AO level is 0. That's the starting point. If the AOs were working, these should be moving towards this dotted line, right? Natural rubber should be getting less scission, more towards this direction, and BR should be getting less cross-linking, moving. In fact, they stay flat, or if anything, some slight increases. However, when we look at a longer amount of time in the oxygen environment, so the RPA test and the test I just showed you with the Aries G2, that was 10 minutes, 10.5 minutes. Now we're looking at 26.5 minutes. Now we see some big differences. In the case of natural rubber, if we look at tan delta, it moves towards this, this neutral line, right? This thermally stable line. However, if we look at viscosity, we still see some scission. So it's complex, as I'll mention later. And certainly if we look at BR, the change of viscosity without stabilization and with stabilization, the antioxidants all seem to have some benefit, but only after we look longer period of time. So hopefully you are in agreement that the RPA can see differences in thermal stability between different types of raw elastomers, and through the two examples of BR 9000 can see the utility of this in comparing raw materials from different suppliers. And I introduced the Vanguard-Kalman plot, which is useful for, especially when you have a set of data at different temperatures, identifying the onset of thermally induced branching and cross-linking. It got confusing and surprising when we did the antioxidant study, because not only did we not see a stabilization effect, but actually in the low oxygen environment of the RPA at 180 degrees C, we actually saw more severe changes. But we did see some stabilizing effects in an oxygen, high oxygen environment, air environment, but only for longer periods of time, and those effects were not straightforward. And just to show an example of how complicated it is, this is the Aries G2 air environment. This is that longer test that I was talking about. And what you can see is the material without extra antioxidant, this is natural rubber, and delta goes down. That looks like cross-linking. However, if you look at the viscosity, it looks like chain scission. That's already confusing, and we haven't even gotten to what's going on with the antioxidants. Once you put the antioxidants in, we see chain scission and then cross-linking by tan delta, but for all of them, we just see the viscosity going down. So it's not a simple picture. But what I am convinced is that dynamic rheology is an important tool for sorting this out. Finally, I want to thank again my co-authors. Thank Zhongshan Rubber Group and ACE Laboratories, Brian Wheatley at ACE for help with the rubber mixing, and thank Alpha Technologies for allowing me to use one of their premier RPAs. And finally, I'd like to thank the organizers of this Rubber Innovations Forum for inviting me. It's been an honor, and I want to thank you for attending.
Thank you, Dr. Robertson, for your excellent talk. It was well appreciated. And I think it is midnight over there, if I'm not wrong. Okay. Thank you very much for your patience as well. Now it is open for the discussion. I think I'm having a very quick question. I can start a question first. So my question is that, for instance, if we have, let's say, EPDM rubber, and in presence of peroxide, it is reported that part of it is mostly cross-linking, but also to some extent transition can also happen. My question is, from RPA, can we think one step further that whether are we able to quantify the extent of cross-linking to transition, the kind of ratio, let's say whether 85% is cross-linking and 15% is transition or something like that? That is my question.
Yeah, I think there's a chance, but we would have to look at a broad range of frequency, so that there is a chance to sort out the distribution, those chains that break versus the chains that branch. The chains that branch will show up at the lowest frequencies, and so that's why we have to have a big enough window. But I believe there is a chance, particularly if your material was fairly narrow molecular weight distribution to start out with. The challenge I sometimes see is the commercial elastomers that we face. They're already broad molecular weight distribution, and a lot of times the manufacturers intentionally already put branching inside, right, for cold flow resistance and for processability. So assuming that you had a nice clean, maybe more of a model EPDM, I think there's a chance to do exactly what you're talking about.
Right. Okay. Thank you. I think if there is any more question, anybody from the audience? Kanika, you have any question? Yeah. So Kanika is coming. She's having one question.
Okay.
Yes.
Okay, thanks for a very nice talk, Chris. So yes, you compare between TMQ 6-PPD and IPPD, and so far there seems to be different behavior between rubber, like you observe in NR and BR. So in your opinion, I mean, if we want to compare thermal stability of this polymer, can we really clarify which one is more effective, and if we want to apply those stabilizers? I think now we are working very hard on finding alternatives. So this is one of the important or potential tools to differentiate for those alternatives. What is your opinion on these topics? Thank you.
Yeah, so this was a big surprise, because I thought we were just going to do this AO study just to show the technique works. And in fact, what we realized is that at 180 degrees C, there's something else happening that the AOs do not help. And so if we're going to use a test, maybe there's a possibility that if we have this test, a much longer test at maybe 100 degrees C, right, that's more relevant to aging of rubber, then I think we'll see the usual AO effect. But the high temperature test that I did just showed that it really doesn't distinguish between AOs. In fact, AOs made things worse, which was the biggest surprise. But I think things should be pretty normal at 100 degrees C, where the mechanism.
Have you tried testing with the blends? Because you show, I mean, individual elastomer, right? You compare different elastomer, but I wonder if we use in the blend, and can we also observe the same behavior under this RPA? Have you ever tried?
I haven't tried because it's more complicated, but it could be a next step. Yeah, if we understand the neat polymers, then maybe we could understand the blend. In particular, when you have a blend and you add stabilizers, there's a partitioning effect that's possible, we don't often, we tend to think everything sort of homogenizes, but the AO has a choice, right? It can go into this phase or it can go into this phase. Maybe a study and blend is an opportunity to figure that out, which phase it's going into more preferentially.
Okay, thank you very much. There will be a more question from other audience.
Thank you. Thank you. First of all, good evening, and Dr. Chris. Your presentation was really great, but unfortunately, I'm very sorry I joined a bit late, so I could not see the initial part. But like I discussed during the last question, 6 PPD as well as understanding replacement of 6 PPD is very, very critical to us. Oh no, sorry, I forgot to introduce myself. I'm Dr. Jyoti Prakash from Apollo Tyres R&D. So we are trying hard to how to have an alternate to 6 PPD. And so have you any publication, and can we go through a little bit more in details, because I joined late also. If you have some publication, you can share it, then we can go through it. And maybe of course we use alpha equipments a lot of in our plants as well as in R&D. So we would like to understand this technique, and if it can help us in understanding the behavior of different antioxidants and whatever the things, and how RPA can be helpful in addressing the 6 PPD alternate.
Yes, I will certainly. We have not published this yet in a journal paper, but I will share my slides for sure. What I would say is that the test we did at 180 degrees C, I think, is not the right one. Maybe something more like 100 degrees C. If you did a similar long time sweep, you have a good chance of being able to characterize 6 PPD and then some alternative. Only the antioxidant capability of 6 PPD, right? 6 PPD also is an antioxidant, and it's an anti-fatigue agent as well. So only the antioxidant part of 6 PPD's function. That's why 6 PPD replacement is so challenging, is it's really doing like 3 jobs inside the rubber.
Thank you. I will collect your presentation maybe from Payram. Thank you.
Thank you, Chris. Wonderful presentation. You'd like to see our audience? Just a second. Let me turn on the camera. Yeah. Okay. I guess you can see them. Yeah.
Oh wow! Very nice.
Yeah. Okay.
I see some familiar faces. Yeah.
Yeah. Yeah. I know it's midnight for you. Just want to make sure that we have. So yeah.
Thank you. I will stay on and listen to the other presentations. So I'll be here.
Yeah. Please stay on. Actually, it goes up to the morning for you also tomorrow, so we can stay on there as well. Yeah. Okay.
Is a possibility I may take a small nap somewhere in there.
Okay. Thanks a lot, Chris. Once again, big hand to Chris. Yeah.
Thank you again for inviting me.
Thank you. Thank you. Okay, let's minimize it. Okay, guys, we are going to have 2 sessions now onward, so you can choose rooms that you're interested in. There's a room 1 and room 2. Yeah. So I'm going to take over the room 1, and Dr. Kinsuk will be taking over room 2. Yeah. Okay. I hope I get more audience here. Huh? Just a second. Okay, just a second. Yeah. Is Arshad here, right? Okay, hi Arshad. Guys, when young people make a presentation, I do request you to cheer them up, and I want them to be more enjoying this presentation. Okay, so when you see the researcher IIT Kharagpur or from other university, I like to have more Okay, so let's start with our first speaker, Mr. Arshad Rahman, and he's going to give a talk on the hybrid curing systems in elastomeric composites application. Okay, guys, you know that it's a 10 minutes presentation slot. Okay, so let's keep that way. Yeah. See. Okay. This gets recorded. Okay, now it's going to the audience will be there. Okay, so relax. Okay, okay, yeah, sure. Okay, let's welcome Mr. Arshad Rahman. He's a research scholar at the IIT Kharagpur Rubber Technology Center. So join me to give him a come on, yeah.
Thank you. Good morning. The topic of my presentation is hybrid curing system in elastomeric composites and applications. This work is done under the supervision of Professor Kinsuk Naskar in Rubber Technology Center. I will go through a small introduction and motivation of our work and some of the results we got. So coming to the introduction, rubbery materials are known for humanity for very long time, but however in the 19th century, discovery of cross-linking by Charles Goodyear actually led to its commercialization. Looking into the cross-linking structure of a material, the cross-link network can have various components like this elastically active and elastically inactive components. Elastically active components are rapid entanglements and normal cross-link density. Inactive components like dangling chain ends also has effect on these properties of the sample. So we can characterize cross-link network by four characteristics. These are the four. They are like the total amount of cross-link density and its spatial distribution and type of linkages. Each has different kind of effect on the final properties of the vulcanizer. For example, total cross-link density affect each property in a different way. So we can see that there is a maxima for tensile strength, tear strength, etc. Same as in the case of cross-link type also has effect, as we can see from this table. It actually has different bond energy that actually has effect on the total strength of the material and all. Coming into the most sought after cross-linking system in industry, they are sulfur and peroxide based. We can see that each has their own peculiarity and they have their own application also. Sulfur is most used in dynamic applications. So where this higher temperature and set requirements comes, we use for peroxide curing. So if we take a summary of the properties of most sought after three curing system, we can see that each cross-linking system is good for different kind of application. Like say sulfur is good for its tensile tear properties. On the other hand, peroxide is good for its temperature resistance, compression set, etc. So our objective was, or our motivation was, can we combine two kind of cross-linking into one matrix, and is it possible to bring the better properties of these two cross-linking, say higher thermal resistance from peroxide curing and better dynamic properties from sulfur curing into one matrix. So we actually studied that, and here in this part of the work I also represent about a detailed study. We studied the life of the products, life of the product and thermal aging effect on this curing, influence of curing system on life of the product and thermal aging effect. So we choose an EPDM as the matrix because EPDM already has application with both sulfur curing and peroxide curing. So that's why we have chosen EPDM as a matrix. So as we see, if we look into this EPDM curing, peroxide radical actually abstracts hydrogen from this and for hydrogen from EPDM chain and forms macro radical. So this macro radical can react another EPDM macro radical or another EPDM chain or sulfur. So as we can see that if it is reacting with EPDM macro radical and EPDM it will create crosslinks as like a peroxide curing. On the other hand, in the hybrid curing system where sulfur accelerated curing system is also present, it can react to this sulfur, and that sulfur tailed macro radical can react to another EPDM or another macro radical that can lead to production of sulfidic crosslinks in alkyl locations of EPDM chain. That is actually not possible with in the conventional curing. As we can see, conventional curing, sulfur can only create these allyl bonds in EPDM chain diene unit. So that's what a hybrid curing system can bring extra into this curing technology. So initially we studied using some statistical analysis like Taguchi methodology, the effect of the levels. So we tried to optimize the levels of sulfur and peroxide curing system in various systems. So we did multi-objective optimization in the samples in terms of various properties, and we ranked the compounds with different considering 8 or 10 properties as shown in the table. So we got the optimum level, and we compared that optimum level with the conventional sulfur and peroxide cured samples. So we could see that some of the properties like tensile strength, elongation, and break were getting improved for this hybrid cured samples. However, we studied further regarding degradation of these samples, how this for EPDM degradation behavior is important. So how this degradation happens. So conventionally, that is also important for its lifespan prediction, and it has also great environmental impact if we can predict lifespan of a product very clearly. So we have chosen these 4 formulations for that. One is based on sulfur, one is based on peroxide formulation, and 2 hybrid system we have chosen. One is with a coagent and one is without a coagent. And we have mixed in Haake 2-rod mill, and we did the rheographs and everything. So after that we thermal aged it in 125 degrees Celsius, and we tracked it for 504 hours what is happening in the samples. So so we could see that there is cross-linking during aging in there is improvement in cross-link density during aging in sulfur cured samples. On the other hand, there is little bit scission in these peroxide cured samples. We also studied the mesh size difference before and after aging using DSE analysis. So what was the mesh size of the cross-linking before aging and after aging? So from the mesh size also we got some influence about existence of both sulfidic and peroxide crosslinks, because after aging peroxide crosslinks was intact. So we got we got a proof for coexistence of the cross-linking, and more importantly, we tracked the tensile strength also through the path. However, these all are conventional degradation tracking mechanisms. But in conventional degradation tracking mechanisms, say for hardness, if we track, hardness can improve if cross-link density is improved during aging. Hardness can decrease if chain scission happens. But in a case where equal amount of chain scission and cross-linking happens, there will not be any change in hardness even after aging. So we cannot say the material is not degraded. It has degraded, but equal amount of scission actually cancelled out the increase in cross-link density. So what we did actually, we used a method based on compression set analysis, where we aged the samples in 2 conditions. One is without a strain and one is with a strain. So after the aging, if we measure the we aged at 125 degrees Celsius. After the aging, if we measure this compression set, actually we can see that in case of samples where chain scission happens and it is aged without a strain, we can see if in samples aged without a strain, If the compression chain scission happens, it increases the compression set, and if cross-linking happens, it decreases the compression set. But on the samples aged with a strain, we can see that chain scission and cross-linking both increases the compression set. So that is a plus or minus an inequality there. From that, there we used the governing equations of rubber elasticity, and we could actually derive these factors like the chain scission and cross-linking amount in samples. So we could see there 4 graphs. One is for this sulfur curing and one is for peroxide curing. These two are hybrid systems. This one and this one. So one is for with cohesion and one is for without cohesion. So we can see in that samples with from the slope we can see what is predominating in each sample, scission or cross-linking. So the samples with cured with sulfur was actually cross-linking predominating. The samples cured with peroxide was actually scission predominating, but in case of samples cured with hybrid curing system, it was showing an equilibrium between scission and cross-linking reaction. That's why it was showing actually a better thermal properties during the analysis in conventional analysis. And we have done FTR studies and carbonyl index, so we could see also a large peak for carbonyl peak for this sulfur and peroxide cured samples compared to hybrid cured samples. That also indicate the presence of oxidation reactions in peroxide and sulfur cured sample more than the hybrid cured samples. Thermogravimetric analysis also got some improvement, and the first and second onset temperatures have improvement in hybrid cured sample compared to this sulfur and peroxide cured samples. So we also study the contact angle of the sample, which also indicate the polarity of the surface. So from that we can actually say what is the degradation in the surface. So in the we can see that sulfur cured samples was actually going from hydrophobic to hydrophilic after aging. That indicate more oxygen is there on the surface, or that kind of polar groups is there. On the other hand, hybrid cured samples, it was in the opposite trend. So these are my conclusion for the presentation. We have found a method to divide between cross-linking and scission in the samples, and we have further studies are going on dynamic properties of the samples. I would like to thank my institute and department, Technobis. Actually, this is our group from Rubber Technology Center. Thank you.
Any question to Asha? Yeah, please.
That's okay. So, if you know, we have used the peroxide system for EPM curing on the microwave line.
Okay.
We have to use the HCM lines for the extrusion. So, is there any chance that we could use this hybrid system on the microwave line? Do you do that, or can you advise on that, whether it works or not? Do we actually do the trial?
So you need some glycol kind of molecule to polar molecule for microwave line heating.
Peroxide reacts with the oxygen.
Okay. Okay.
So before reacting with the polymer, it reacts with the naturally available oxygen, so it can't be on the microwave line. But with the hybrid system, maybe we could use it.
Yeah, actually, we are trying to cure even EPM with this system. EPM, there is no dye-in, so that works like this without dye-in, where if we improve, we can impart the sulfur bonds into EPM. That can be done using this system. So the same methodology applies there also, I think.
So, we'll get the presentations later on. Yes. Yes. Okay.
Okay. Thank you.
Thank you.
So good presentation, Ashwin. I have a very small doubt. Okay, you are telling that you are using contact angle to measure how much oxygen group is generated on surface of the thing. Consider that I am doing this for tire application. Okay, so do you recommend any other methods to measure how much degradation happens or oxidation happens in different layers of tires or different layers of compounds? So you have time for like 2 mm thickness. So think like when you have 6 mm big sample.
Yeah.
And giving aging when dynamic conditions also apply. So can you recommend any other?
Actually, you can do XPS. XPS has this option of spattering, so you can do spattering each layer of the samples, and through that you can analyze each layer of the sample, so you can get a graph like the thickness of the sample and content of oxygen in this sample. So that will give the depth of oxygen, how much depth the oxygen actually degraded.
Thank you. Nice person.
Thanks.
Okay, thank you, Dr. Thank you very much. Getting a plug-in. Yeah. Give me this one. This one.
Yeah, sure.
Okay, let's welcome our second speaker, a young and dynamic Dr. Titash Mondal is an assistant professor at the Rubber Technology Center. I like the way what he's doing is all focusing on the advanced technologies and for the rubber technology in aspect rubber technology. Is going to give a talk on the elastomer-based electronic skin next generation sensor. We don't know where we are going. Everything is going to be automated.
Yeah, that's what we expect.
We're going to be more lazy. Okay. Join me to welcome Dr. Titash.
Thank you, Pairam, for this invitation. So next 20 minutes, I'm going to talk about something really cool and neat, which is elastomer-based electronic sensors. And why am I calling this as a next generation sensors? Because you will get to see pretty soon. Okay, before we go into the nitty-gritties, like yeah, so this picture is pretty known to many of us, which is evolution versus revolution, right? So when the humans evolved over the period of time, this was a picture, but I still remember my father carrying a Nokia phone. I mean, if you throw it on somebody's head could have been broken. But look into the kind of the phones that is coming into the new generation. They're pretty smart, very sleek. So there is, I mean, if we compare these two processes, what is the basic difference between thing is the first one was more of a natural process. But this movement from a big bulky size phone to a smartphone involves a factor known as strategy. So strategy is something which is very important, and to strategize, it is really important because the frame is changing very rapidly. If you look, we have been talking about a different industrialization, like industrialization, it started with 1.0. Yesterday, somebody was talking about industrialization 4.0, and now it is industrialization 5.0, which has kicked in from the year 2019. And what does this industrialization 5.0 talks about is basically integration of these elements like sensors, making life a little more easier, more human-centric, and all these factors are coming. And along with that, there is another factor which is also big time coming, is that most of the industries are typically focusing on the SDGs, which are kind of showcased by the United Nations. SDGs means the Sustainable Developmental Goals. Okay, and from a rubber fraternity, we are pretty much happy with the tires, the new types of elastomers, their applications in conveyor belt and whatnot. But the fact is how we can align these rubbers to this industrialization 5.0. That is what my research team is doing. And the kind of, after doing a lot of brainstorming and going through, because I before joining academics, I was in the industry actually, so I'm pretty much used to all this brainstorming session. So what we figured out is that the elastomers, owing to their very flexible nature, one of the domain wherein this particular elastomers can be fitted in is sensors. So because if you look, and this is very different from the traditional sensors that we use. I mean, in the case of traditional sensors, these are rigid bodies, like, you know, these are typically kind of, you know, semiconductors which are not flexible. You cannot bend it. It's not conformable. So this is kind of a domain that we identified, and we wanted to test the applicability of different rubbers in this particular domain. Now, this decision of working in this domain was largely guided by the market. Like if you see, like it is already a kind of a $421 million US dollars market already has kind of achieved in the year of 2024 till now, and this is projected to something 960 million US dollars by 2034, and this is something with a CAGR of 8.6%. Okay. And it is also very important to see that many big players, starting from DuPont to Henkel to 3M, these companies are very much investing their time and manpower on this developmental process. Now, if we look like what are the segment in which this particular sensors can cater to, actually the flexible sensors, you can find kind of multiple applications in different domains, starting from consumer electronics to the medical and the healthcare section. Like if I do a kind of a segmentation on the emerging and the established segment, if you can see the kind of the light blue nodes, the motion tracking gloves, the human machine interface control, battery health monitoring, robotics, patient monitoring, these are like some of the things. But unfortunately, in India, this technology is not progressing that well. Maybe this technology, what I am practicing currently, is very new, very advanced for India. Maybe after 5 years, we'll also start running in the race. And not only that, we also find that there are a lot of applications of this particular flexible electronic sensors in automotive industries, like because EV is something which is booming in our country and the other parts, and there what you get to see that the applications of flexible sensors have potential. I mean, these are typically like listed down over there. With all this thing in mind, what we did is that, like I mentioned, I am from industry, earlier phase. What we did is something for any project that we uptake, we work on a parameter called DVF, which is typically the desirability, viability, and feasibility part. And when this DVF part is there, when it overlaps, basically we identify the innovation sweet spot. So as you can see here, this is the kind of the innovation sweet spot. And then we map it kind of an attractiveness versus the ability of win. And what we are typically targeting is something that particular regime where it is the attractiveness is also very high and the ability to win is also very high. And with this thought process, my research team, along with my research team, what we did is basically focusing on big bets. Like we did like all this comprehensive analysis of the market. And then what we started doing is that we started to leverage these elastomers for generating certain sensors that kind of focuses on haptics, or it is basically tactile or non-tactile based sensing. When I say all this jargon, please don't get disturbed because it's very simple. Like why I say this as an elastomeric electronic skin, because human skin is the best sensor one can ever think of. If you pinch it, you will have pain. If you put some kind of a hot temperature or cold temperature, you can feel the same. So the best known sensor in our world is human skin. But this elastomeric skin, what we are working works on the principle very similar to the human skin,
but they are not equivalent. So with that, basically, I will start the first point. The first point is basically one of my PhD students from down south, Mr. Muthamil Selvan T. So what he did is designed a very unique strategy. We recently published this actually. So what we have taken a carbon nanotubes, and we have taken liquid isoprene rubber, and we kind of mixed both the system, and then we did the cross-linking of the same. Now you have to understand one basic fundamental criteria here is that when you put a filler inside any kind of a rubber matrix, what it does is that beyond a certain volume fraction, it starts forming a network structure. Okay, and this network structure, what it does over there is that basically in this particular case, what we are using is carbon nanotubes. And carbon nanotubes, all we know, is an electrically conductive material. Okay, so what we can think of is that if we source an electricity from one of the terminal and map it on the other terminal, through this network, the electricity is going to pass, right? Now imagine this chandelier which is at the top. If I disturb it, the whole system is going to disturb. Let's say I'm going to take a stick and beat it. Actually, I'm not going to do in reality, otherwise Param is not going to leave me. So basically what will happen, this is going to disturb the whole system. So here, similarly, when we have this particular system of the polymer, which is having a filler network inside there, and if we are applying any stimuli like pressure or temperature or anything like strain, what it does is basically inside it creates pain into the elastomer system. And that's what the pain effect also comes from there. And it also disturbs the filler networks over there. And when there is a disturbance in the filler network, this results in a fluctuation in the electrical resistance value that I was talking about initially. So what Muthamil did is very smartly here, designed a kind of a sensor, which is like, kind of a skin-like material. And in this particular case, he kind of applied temperature. And when you apply temperature to this type of system, there is a flow of electron which can increase and also decrease. And that's why what you get to see is basically a change in the electrical resistance. So that's what he did very nicely over here, that if you can see here, this is a kind of a cyclic study that Muthamil did. Like, he took the sample to 30 degrees C and then he immediately heated the sample to 50 degrees C. So you get to see that when you are going from a 30 to 50, actually, you get a change in the relative resistance. This is the parameter we call the relative resistance. Okay, so this material is something which is thermoresponsive. Actually, this simple elastomer is thermally responsive, right? So what he did is that he wanted to make this a kind of an haptics based, non-tactile based sensor. That means you really do not need to touch the sensor. If you bring your finger in the close proximity of the sensor is going to kind of give you certain signals. Okay, so initially what he did, he wanted to check the effect of convective air. Like he took a hot air gun, blown a hot air gun from there. So when he started blowing the hot air gun, what you get to see that there is a kind of a decrease in the relative resistance value when the temperature is like from 33 to 75. Okay, not even that actually, when he kind of brought his fingers very close to the sample, actually, because our body temperature is close to 35 and 37 degrees C, and the sensor was kept at 33 degrees C or 31 degrees C. So there is a delta T which exists. So there will be a heat exchange through convective mode, and soon the finger was brought into close proximity. There is a kind of a change in the relative resistance. So this type of sensors can be used very much in the domain of human computer interaction, or HCI, that words, because you have to understand there is a growing market in the virtual reality and the augmented reality section, where you see people are wearing a glass-like thing and hovering around and screens are changing. So this is for an HCI application. The next thing, one of my good student, you can see he's with a champagne bottle already. He's celebrating Mr. Ajay Haridas CP from Kerala. So here we designed a kind of a sensor which is recyclable, and this is based on thermoplastic polyurethane actually. And what we did here also, we put carbon nanotubes over there. We compounded in a very simple way in a Hakerio mix actually and fabricated a sensor. But this sensor is very different from the traditional sensor, because what we call is that this sensor is having a brain, and this brain is guided by Internet of Things. So what you can see here is that the main objective, you might be aware that when any chemical process goes, like, you know, you have a thermometer, then you have a controller to control the temperature. All these things are separate attachment in any thermal process. But in this particular case, this material itself can show a dual characteristics. Like, let's say you have a distillation process going on, or any kind of mixing process going on. This material, if you fix it over there where you want to monitor the temperature, basically it will sense the temperature. And let's say you have a kind of a temperature fixed 60 degrees C, and for any reason there is a fluctuation happening over there. What it will do is that it will switch its role from a sensor to a heater. So this material, as you can see, it can go as close high to, like, you know, 192 degrees C with a very minimal power consumption. Even with a AAA battery, you can, you know, run the show. If you have a pocket and you want to make a coffee or anything in hill station, you just need to pad it in, put a, you know, beaker or something like that, make a hot tea or coffee out of it. What we did is that we demonstrated this whole process. As you can see here, this is a chemical reaction which is going on here. And at the same time, you could also see that it is like, you know, we developed an in-house application, mobile applications also, through which you can monitor all these changes that is happening. And if there is a kind of a change in the set temperature, immediately it will start hitting. I mean, this is what the video, I mean, if anyone is interested, I can show you it in the laptop. Due to the paucity of time, I'm just running quickly. Another segment, what we have seen is that this sensors also find a lot of applications in the healthcare domain. We started off with this particular thing. We have got pretty neat results, and the results were getting highlighted in Nature. I mean, we are working in Kharagpur. Couple of our works have been highlighted in Nature, as you can see this. But this is like, you know, for motion monitoring. Some of the talks my students are going to talk today, actually. These are basically what we call as a point of care sensors, and everything is using rubbers over here. But what is the problem? Why we need an alternative strategy to this? Because if you can see this whole sensor to perform or run, you need a power source to run this one, okay? It cannot run without any power sources. That means you need to affix a battery over there, and battery is kind of a bottleneck because it kind of kills your form factor, your flexibility, all those things. Even though there are a lot of flexible batteries available in China, but that's not a sustainable solution. So what we decided is that let us design something which is a self-powered technology. That means you are typically providing any energy in terms of, let's say, mechanical energy. We often walk actually, right? And at the same time, we are generating certain mechanical motions over there. So how about providing all this kind of energy to that and see if we can generate certain current over there or not? And using that, basically, one of my students recently published in a very prestigious journal. So what she did is that she has taken natural rubber as the base material, and we compounded this material with graphene in it at different dosage. And what we have observed is that when you are providing a kind of a mechanical force to that, it is producing electricity, right? And this is kind of an energy harvester. Not only that, what we have also seen is that we did the kind of modeling of the same and everything, okay? And what we have seen is that this material is also an excellent pressure sensor. As you can see, we have tested for multiple cycles actually, and the sample remains, the functionality of the material remains very nice. So basically, this is a kind of a next-gen pressure sensor where you do not need to use any battery. You just need to use a kind of a natural rubber compounded with graphene, and certain other element, another polymer set, and it is like a sandwich structure which you can embed in any parts, like for instance in tires or anything, or in shoes. Let's say in army people, you can put it in the kind of footwear so that it can, while walking or running, it generates energy. We were not happy with this even. We wanted to go a little different approach. Now, all it is taught in geography and the basic science classes is that our earth is composed of a lot of water, right? Roughly around 71% is composed of water, right? Okay. We wanted to leverage, like, can we take this particular water as the source and can we generate electricity out of it without doing much of a rocket physics? And that is what my student Aparna did very nicely. What we did here, we have taken epoxidized natural rubber. We did a bit of chemistry over there, but it's a very simple chemistry that we adopted. And then what we made is something called a hydrogel-based, skin. And this hydrogel-based skins are like very sensitive again. So if there is any fluctuation in the humidity, okay, so then again, it does provides electricity. It kind of generates electricity. And this class of materials are known as moisture electric generator. For instance, our hands have a lot of humidity, and that's what, like, Aparna have very nicely demonstrated here. Like when you are putting a gloves on and when you are bringing your hand very close to the sample, actually what you get to see, there is no change, no fluctuation, no current production. But soon you take off your gloves and bring your hand very close to that, you get to see a lot of fluctuations happening. And this is what is captured here, as you can see here. Like she's bringing in the hand close to the sample, and this is what it is. You are getting the typical peaks over there. Okay, and this is again for application in human computer interface. Then we did something even more interesting. This is something, Durga Puja is also coming in this part of the world, right? So you can see we made some sensors, and this is so powerful, it can lit up like literally more than 500 LEDs. And trust me, there is no battery in usage. I cannot disclose what material we have been using because the patent filing is in progress. So this is what you get to see is like roughly around 500, more than 500 LEDs. Without battery, it is performing well. You just need to provide a mechanical energy. So what you can get to see is that, like for instance, this is another video. This is a kind of a demonstration. So see, it is plugged in, and you get to see a small electronic device is also powering up by its own. So it does not require any battery. You can basically leverage whatever charges your mechanical energy you are generating. So coming to the future scope, like how we can effectively take this kind of materials, it finds a lot of applications, and especially with Industry 5.2, this kind of materials can very well integrate into different, and this is altogether a different type of application where rubber can fit in, and the rubber industry should definitely look in. So this is a very futuristic way. I was in the United States, so I have seen, like, whenever there is a kind of an icing on the road or anything, people spray salt water or they use certain chemicals to have the de-icing. But utilizing similarly some type of sensors, see, this is a concrete block, and on the kind of extreme right hand side you can see basically the rubbery part material is embedded inside the concrete, and we put certain ice blocks, and you see this is the control sample, and within, like, you get to see like the ice block with the sensor, when it is sourced with a kind of a power supply, is melting it very fast. So you do not need to use any kind of a salt spray or anything. So this is how you can think of, like, the sensors can find different applications. So with that, I'm going to end my talk. My group, I call it as E-Company. E for entrepreneur. Company means less water, more concentrated entrepreneur. Okay, and these are the group of entrepreneur, because rather than PhD student, I train and to be more like an entrepreneur. Okay, and trust me, they are excellent, and some of them are going to give their talk today. And a bit of background, like 14 years experience in graphene based rubber composite, also experience in epoxy composite. I do have multiple US patents and European patents, and strong expertise in silicones because I was working earlier in a silicone MNC, Momentive Performance Material, wherein I got trained, to commercialize material from incubation state, and that is what we are doing here. With that note, thank you so much to the organizers. Thank you. Any questions?
Any questions?
Yeah.
I think your talk was super, very informative. Thank you so much.
Thank you so much.
I just want to know, it seems that you come from industry.
Right.
Now in academia, but how does one go back in the sense? How do you integrate with industry, or how do you give out your ideas?
Yeah.
Then come into commercial production.
Absolutely. Yeah. Thanks for the question. No, I'm reaching out to different companies already. Few companies, almost in the final stage for some of the things, because industry, many industries, I cannot name them, including some big rubber industries, they are working. They are not telling it, they are not making it public that they are formulating, including synthetic rubber manufacturer. So they are not making it public, that because everybody wants to keep it confidential and win the race. Okay, so some of them are, I'm working with them actually on the documentation part. So basically what the plan is to license the patent, whatever we have published, and transfer the technology to them so that they can take it forward. Thank you.
Thank you, Dr. Bond. It was an excellent presentation, a lot of information together from your work.
Thank you.
Really, it's high-end work which can be commercialized.
Right.
Now, the thing is that, of course, the sensors are made in the lab, and we need to go through robust testing.
That's right.
When we go for a real life.
Absolutely.
So, is there any plan to have it in between? Because, of course, we have seen the laboratory performance very well. I am not discussing anything.
Right. No.
So
Absolutely.
when it goes to the thing is that there is always a reversal of what to say, phenomena happens very often.
Absolutely.
So when a certain severity, it works very fine. Beyond a certain severity. So
right.
Whether in a real life application is it happening? That's very important things to understand. It's too early to comment on this because I'm not listening to it, and you can always say that in an academic environment it's very difficult.
Absolutely.
It needs time, but having said that, I think it's there are a lot of potentials to explore, and so that this whatever the apprehensions, those things can be really clarified. That's only humble solution from my side.
No, thank you, Dr. Ghosh, for your suggestion. I mean, you're absolutely correct, because like I mentioned during some of the commercialization thing, what I did are in the market, and I've seen like when we do it in a small scale, level of complexity is very different when we translate that to a bigger scale. So what we try, even though we are in the academics, what we try to do, thanks to my previous experience, within this 20 minutes of time I could not show, we torture the sample. We literally torture the sample and try to see, even after those tortures, like how much is the sample, staying good, showing the sensitivity same. Like for instance, this material which was showing this bulb is glowing like more than 500 LEDs, and it is providing and hopping power density of 80 watts per meter square, which is huge. So we cut the sample, reprocess it, again do it. It's a recyclable material basically. We are working.
Just one more idea.
Yeah.
I would like to share with you.
Sure.
Sorry, I'm taking a long time.
It's going to create entrepreneurs. I want to.
Yeah. The thing is that, like when you were thumbing on something,
right?
Try to measure how much is the impact force.
Yes, we do that. Yes. We again, it's a funny thing. Maybe I can share. We have designed an instrument. I do those designing part also. We call it as Muhammad Ali. It goes, and because Muhammad Ali was famous for this action, so we are connecting this to a force gauge, and we can basically measure how much.
Or some accelerometer. Then
Accelerometer should be fine.
Yeah. So that that will give you an idea.
How much force is
How
active.
much force is coming.
Right.
And when you try to, let us say, again from the tire industry, it always comes that thing.
I am ready. Please take it, sir. I have some, because bending, twisting, all those with torsion, how is the performance? We have data for everything. And the biggest part is this is a kind of a scalable technology, because all the materials, whatever I'm using is off the shelf, except one or two, like Aparna did a bit of fancy chemistry. Even though I'm a chemist, I hate it actually nowadays, because fancy chemistry is okay, but you need to think about the scalability also. This is a scalable, the mixing is also scalable technology. That
So
is
the moment you get those ideas that how much impact force, how much acceleration is coming,
absolutely
it's very easy to correlate
with the tire performance.
and you are there. So that's how we.
Sure, maybe we can, but thank you so much. Thank you so much.
I'd like to present a token of appreciation for being part of this Rubber Innovation Forum. Thank you very much. One more time, guys. Innovator. Thank you.
I'll just take it out.
Sure.
Just cross
May
it.
help you.
Yeah, please. Thanks.
E-company, is it?
E-company.
E-company.
Company matlab less water.
Okay. Yeah.
E for entrepreneur.
Right. Got it. Right. Dr. Nadarai, don't know why. Yeah. Good. Okay, our next topic is on the also very important marine applications, recent trends in rubber science and technology by Dr. P. Nadarai, scientist NEF level. He works for the DRDO under the Naval Physical and Oceanography Laboratory based in Cochin as the head of the Material Science Division. Join me to welcome Dr. P. Nadarai and ask him lots of questions as well. Yeah? Okay. Next slide. This one. Next. Okay. You can use this one. What should I use this one?
Good morning, you all. I thank our organizer for giving me a wonderful opportunity. So, as he pointed out, I'm basically a rubber technologist working in defense, DRDO. This is Defense Research and Development Organizations. So we work for Navy. So I am talking about recent trends in rubber science and technology. It means the role of rubber technology in marine applications. So this is my outline of my presentation. So I will be covering what this importance of rubber, particularly in underwater applications. So and I will cover the little bit case studies also. So this is my, introduction. Everybody knows that what is rubber, but there are some few properties of the rubber which cannot be replaced by any other material. One is insulation resistance, that is electrical resistance. The second one is isolation, vibration or shock. This property possessed by the rubber cannot be replaced by any other material. The advantage of rubber is which has got high extensibility. It means it can elongate more than some 5 to 10 times. It means what? It can absorb more energy. So compared to other material, the material which has got more energy can be used for multiple applications. So this is what underwater, scenery. What is in underwater? How these navies are working. You all know that we are all protected by our defense force. Defense force means 3 forces are there: Navy, Army, and Air Force. Yes. So we are working for Navy. Navy means what? So our Navy means the most important things for our naval officers are like they use ship, submarine. People are working in submarine, ship. The submarine is working under more than 300 meter to 500 meter, and all people are working in it. So how to navigate through the underwater? We all know that when you fly by the airplane, how the pilot knows that which direction he goes. He uses radar. So when you want to navigate in underwater, what do you need? This is called sonar. That's right. Sound navigation and ranging. That is my laboratory, which specifically make this sonar for Indian defense. So our system laboratory means our is mostly dominated by electronics paper. So you all wonder that what is this fellow? What this rubber fellow is going to do in a Navy? That's what I am going to do it. Because there is no world without polymer, isn't it? All you know that without material, you cannot imagine the world. So this is not an exception of this Navy also. When you talk about this sonar, I told this is a sensor. The sonar means which has got 2 parts. One is active sensor, and the second one is passive sensor. Active sensor means what? It generates energy like a transducer. It generates energy, send the energy, and also receive the energy. That's called an active transducer. Passive means there are a lot more material which does only one function, means which listen. That is which does only one function. So these are all active material. And previous speaker, he has talked about very good, fantastic material. These are all active material, means that can be used for sensor applications. But passive material means which does only one purpose. It may be production of some sensor, which may act as some resistance coating material. So these are all passive materials. So passive material, I am talking about where these passive materials are played in the naval applications, rubber and adhesives, and there are so many allied material like PU and other things are there. Okay. So these are the various applications like rubber used in underwater applications. Because as I told that a transducer, which is nothing but a sensor. This sensor means this transducer is actually eye for the sonar, because which only send the signal and get back any target or underwater, any target which is moving in underwater is there. So we are using it, this sensor. But these are all electrical ecosystem. Electrical systems means you cannot just like the deploy in underwater. So what is the use? That is to be protected. So thereby our role is there. So rubber or polymeric material which plays very important role in production of all these transducers. So that is called encapsulation. There are some material which is which absorbs energy or which absorbs shock and vibration. These are all called mount. Then when you talk about a ship or submarine, there are a lot more components. So many things are there where this underwater seal, shock mount, junction box, so many things are playing in that role, which mainly this rubber is acting as a new role. So the first one I will talk about this encapsulation. I told that this is a encapsulation material. I think I am audible, I think, isn't it? So this is encapsulation means which protect the sensors. what is the main function of this encapsulants? Main function of sensor, you see the sensor with the encapsulants which is going to be used for underwater application should possess all this property. Particularly, what I am trying to say is the compound which you are developing for conventional like application like a tire or V belt or hoses and other things cannot be utilized for underwater applications. So why you know? Because underwater which is salt water, which is corrosive in nature. So when the most industries, they are all based on working on natural rubber. But the problem here underwater application is natural rubber cannot be used because natural rubber will be attacked by this corrosive chemicals. So synthetic rubber plays very important role. So these are the basic elastomers that we develop for encapsulation applications. I told that the protector, hydrophone, these are all part of transducers. Okay. So when you do this actually encapsulants, the main important property is it has to protect in water environment. It's mean what? It should not absorb the water. It should have impermeability should be high, and also electrically it should be resistant. The problem is when you compound it, you are adding carbon black and all. So when you add more carbon black, what will happen? In addition to give strength, this is also increasing the conductivity, which we don't want, because this is to be worked in underwater application. So this is some sort of compromise you have to do it, particularly when you develop a material for underwater applications. In research, so conventionally people have been using all over the world synthetic polymer like neoprene rubber and all. But what is the advances after that? When you want to improve the life, so what is the advantages of making other rubber? Because neoprene also has got some limitations, like you can use it for 7 to 10 years. But there are some transducer which works more than some 12, 15 years. So we recently done based on the blood-based elastomers, or recently a rubber nanocomposite. I was closely working with Dr. Soundanu Satapathy also for this particular work. So what is the advancement in recent encapsulation means when you blend it, for example, neoprene blending with butyl rubber. Butyl also it's very difficult when you go with alloy butyl rubber, because you have to select bromobutyl rubber, because neoprene is a little bit of chemistry also, that also you should understand. When you make a blend, you have to make the compatibility, and also it is to be cured in the crossing agent also you have to be in the, so common crossing agent is also most important. Then these are all why you are doing this blend and the nanocomposite. The advantage is you see that water permeation stream, 1 order of magnitude it gets increased by when you do nanocomposite. You all know that in nanoclay, when you introduce into the polymer, what will happen? It's a tortuous path, means the water molecule will diffuse very slowly when you make a nanocomposite. It's why you are improving the life of the product. Okay, next one is rubber for vibration damping application. Like I already told that ship and submarine has got many compartments where rotor, engine, machine, and electrical equipment, instrumentation, all these are all placed. When the ship or submarine move, what will happen? Which is generate vibration. And also that other part of the sea also, many places where ship and underwater vehicles are moving, which also create the noise and the vibration, which will affect our transducer. So when you develop a material, you have to take care of all these things. This is the scenario you see. The submarine is going, ship, we are our people are sitting there. So they are continuously sending the signal. So it will get, if any target is there, it will get reflected. Signal processing man will be sitting in the ship. He will analyze which direction some people are coming, because we are surrounded by many countries, isn't it? Particularly, we are facing always danger from Pakistan, China, and other. They can easily intrude through the ship. So our sonar, which could be able to make where these people are coming, what they are doing, everything we could be able to make it. Okay. So this is a damping application. First, I talked about the encapsulation, which should be acoustically transparent. But in this case, it should be opposite. So it should be damping. So what is the reason? Conventionally, everybody knows that when you select a carbon black, or when you select some, for example, SBR rubber or nitrile rubber with a higher acrylonitrile content, if you select it, which has got inherent damping, but that's not sufficient. So when you want to do that, people are always doing a new work. This is what recently people are working with the carbon nanotube or graphene reinforced composite, which will have a impact particularly for less weight reductions and also highest performance. So these are the advantages when you introduce this carbon nanotube into the polymer matrix. But you could be able to perform maximum property at a lower level of loading. This is what. So we have also done recently the effect of multi-word carbon nanotube, and we will be seeing the what is the effect into that. Because there is, but the problem with the nanocomposite is, or nanofiller is, interfacial interaction with the polymer, and very difficult to disperse. So what do you have to do as a chemistry, as a student? You people should think that, because this is most important area, like functionalization of polymer, surface modification of polymer. People are simply ignoring that, and they think that when you put this carbon block or when you put a nanofiller, it will automatically improve. That's very difficult. It's not possible also. It can improve, but after some time it will fail due to environmental other conditions. So what you have to do? Concentrate on surface modification of polymer, functionalization of polymer, so that interface between the two substrate will be very strong. Okay. So what is the advantage of measuring tan delta? I have given this. My motto is development of damping material. Yesterday, our Das from he was also talking about a DMA. So DMA is the technique which gives importance of measuring damping properties of the polymer. Okay. When you change the loading or when you change the polymer, you will see the effect of this tan delta value. So damping polymer means what do you want? You need maximum tan delta value. Okay. So when you achieve the maximum tan delta value for particular materials, you will be, that will be used for a vibration or shock absorber applications. But this cannot be used for transparent application, because I told that encapsulation means which generate energy, that energy has to pass through my material. It means acoustically transparent. That case, tan delta value will be, should be low. So DMA is a machine which will give idea about how to select the material, particularly for damping applications. Okay, this is what we have. This is the one of the damping material. We call it as a baffle. Baffle means, why means this, all these transducers are placed over the baffle. This baffle is fitted with the ship. Okay, I already told that vibration, shock, everything will be when the movement of the ship or submarine is there. So if I put my transducer directly to the hull, what will happen? All these vibration will be transferred to my transducer. So there is an interface layer which act as a damping. That's called a nanocomposite baffle, that which improve the performance of gradations. Okay, next one is vibration isolation. You know the difference? What is the vibration absorption, vibration damping, and isolation? Isolation mean what? All this rubber mount. These are all, it does isolation purpose. All rubber mount. Vibration isolation means any equipment. Suppose if you keep it any equipment, for example, you are moving it, you are disturbing this floor. What will happen? Its energy will be transferred to the equipment, which is very delicate, particularly for you are all using that characterization of same TEM. This equipment all you are to be isolated from the ground, because vibration will affect its performance. So isolation means you are protecting one element from the disturbance of other area. Okay, you all know how to design a rubber compound, particularly for rubber isolations. You know, this is when you measure the you develop a rubber to metal bond for a particular mount, then you measure the transmissibility. Vibration measurement means transmissibility. When you measure it, this is the isolation ranges. But most of the rubber, the problem is all this rubber mount, whether it is nitrile rubber or natural rubber, these are all work at higher frequency. Means its effective is at 40 Hz, above 30 or 40 Hz. But you know, in the world, most of the people, they want it should work at a very lower frequency. That's a very challenges in particularly from passive material. But active material, it is there. I don't know whether you have heard about the magnetorheological fluid, electrorheological fluid. This Benz car and all, if you see that, they are using magnetorheological or electrorheological fluid based mount. But for all our even small compressor, when you operate in compression in industry and all, 4 rubber mounts are fitted into that. But the problem is the same mount you cannot fit with the application where low frequency is very important, particularly naval or air force, plane and other things. There you have to select a material which is to work at a lower frequency. But the challenge is how to make this passive material, rubber mount, to work at lower frequency is a challenge. That is what recently all over the world people are working into that. So these are the example of rubber isolators, which you also know that many isolators are there, rubber based under rubber metal combinations, which are all being used in general applications apart from defense applications also. What is the reason to work? That's what reason. Every application of work, definitely you have to work in future also, because when you think about a material, you have to think about our future generation. This is most important because it should have a societal impact. Then only you have to do the research. Just like that, doing research which doesn't have any application, what is the use? So that's what we are always thinking of. So what is the next stage in vibrational isolation? People are working in pad, simple pad. But pad means, you know, mechanically, when you want to adjust the frequency, lower or higher frequency, either what is the formula of natural frequency? K by M. K by M means stiffness versus mass. You cannot change the mass. Suppose if you want to change the mass, you can't change, but you can play with the stiffness. How do you play with the stiffness? There are a lot more ways. Like you can give multiple configuration. You can change the formulation. But changing the formulation, you will get only minimum. But what other things? If you change the configuration also, you could be able to adjust the frequency. Okay. Next one is acoustic observer. This acoustic observer is why I am talking about this acoustic observer means all this submarine hull. I already told that when our Indian Navy are moving in underwater, enemy people also will send the signal because they are also watching us. We are also watching them. So we are everybody is, I mean, they want to be in safest side. So my vehicle cannot be identified by my enemy people. Of course, that's what my job. So what we will do? He is always throwing acoustic energy, like a previous speaker were talking about many mechanical energy and all. So that acoustic energy should be absorbed by our material. So we developed a rubber tile which is based on some filler filled or some inclusion filled, particular inclusion filled rubber compounds which observe this acoustic properties. So this is what you are seeing, that you see this is a submarine view. This is fully covered by the acoustic tiles. The challenge is acoustic tile means people are making like a 15 mm, 20 mm and all, because this is the disadvantage. So what is the recent research? Can you able to make it with micron thickness or less than 1 mm thickness? That's what all over the world people are working in it. So these are all a lot of scope for particularly young people and those who are working in that multiple lines. Okay. The next one is we have talked about always solid polymer, but this is the most ignored area, like adhesives and coating, which is most important in any application for rubber to metal. If product is there, there is a combination of multiple components. So interface is most important. So adhesive is play very important role in including defense application also. So there is a famous advertisement and all. Anything can be bonded except your broken heart. Something is there. You may be knowing. But now the technology is available. Even I can able to bond it, even if you have a broken heart. So that much improvement in adhesive has gone, isn't it? So you have to think a smart way. Like always, people are saying conventionally some adhesives are there. It's a very quick fix. You just apply it, you will bond it. But when it rains, it will go that. So you have to plan how the environment, how much strength you want. So which adhesive plays very important role. You all know that what is the advantage of particularly polymer based adhesives compared to mechanical fasteners and other things. Adhesives also, I told that this is a defense application, particularly underwater applications. The adhesives which is developed by many people that we are using for a tire, like this steel mesh or nylon treatment, or all thing you are doing with some adhesive. That adhesive cannot be working underwater. So you have to specifically formulate for underwater, or there are some commercial material also available from market, like a Chemlock Corporation and all. They give adhesive, but it is very costly. Even 1 liter, if you ask, no, they charge us 15,000 and all. So recently we could able to make one adhesive, which we can make it with just with 1,000 rupees. And we made one better development also with Vajra rubber in Kerala, and we are also developing adhesives. So why these are means these are all part of there are a lot more cable splicing or encapsulation. These are all to be bonded with using adhesives. That adhesives also should be environmentally, it should be compatible with the underwater environment. Okay. Okay. Next is the last this coating, polymer coating. Okay, coating, you all know that coating also is that's the purpose of adhesive, but in addition to that, it protect your all substrate surface. So what are the coating and all that you will get it about the basic definition and all other things. So recently, that is the question. So what is the advantage of nano coating? That is where I talked about. You can able to reduce the thickness. So sensitivity is more, performance is more. Because of high surface area, you all will get that better productions at using this nanotechnology. Okay. Then one of the most dangerous thing is corrosion. Corrosion is this phenomenon is everywhere, because when it is any metal or any substrate, when it is interacting with the environment, definitely it will get corroded. And particularly, there is no exception because all this ship hull and other things are metal based one. We are using it so many metal parts in that also, that is and all getting corroded. So polymer or rubber based solution is the coating. But but recently, what will happen? IMO, International Marine Organization, they banned the conventional marine coating and all, because which is based on lead and tin based one. So people started to work nowadays based on self-cleaning coating. Self-cleaning coating, I will talk about. This is a fantastic rubber chemistry or polymer chemistry where plays major role in developing smart coating. Okay, that's what biofouling. I think you may be knowing that what is biofouling. You see, this is one of the submarine which was completely fouled. Fouled, it is actually what we call it is it's a technical disease, isn't it? This fouling is a technical disease. What in some other time we are saying that it's a cancer. It forms on the our substrate, which is to be protected. But the traditional coatings are copper and tin based. I already told that 2008 itself is people stopped to use this type of coating, but only India we are using it. But anyway, now we are also changing it. So what is the alternative non-toxic coating? That's what coming low surface energy polymer. So what is this low surface energy polymer? Silicone or fluorinated polymer. This can be used. So what is the purpose of selecting the silicone and the fluorinated polymer and all? This is called hydrophobic. So when you want to make a alternative coating material, which is smart in nature, you have to think about some new technology, what we are calling it as a super hydrophobic or self-cleaning coating. You see, the super hydrophobic means, have you heard this word super hydrophobic? You we all may have seen in our village under lotus leaf. By nature, it is the purity, isn't it? Scientists are really inspired by, there are a lot more natural phenomena are there. Our natural, like a lotus fever, water spider, butterfly wing, the skin of a dolphin. These are all people trying to mimic the surface of all these things to make it more hydrophobic. This is the advantage. So I am also giving you advantage of particularly the area, research area. In addition to development of your application, develop your rubber compound with a more hydrophobic. It means what? It will not absorb water, which will, and it will be highly resistant to the environment. So you see, when you talk about this super hydrophobic surface, there are many applications. You see that lot of car window, foreign countries and all, where people are not using wiper. Automatically, this what is that? Water droplet, when it hit on the surface of the glass, what will happen? It will roll off. It will roll off. When it is rolling, what will happen? If at all, if any dust is there, that will stick to the roll and it will automatically clean. That is called self-cleaning coating. And also, these materials are very much useful in multiple applications, like if you go to Leh, Ladakh and all, ice formation of that is the ice formation is the very tricky one because you cannot avoid it, because there also people are using antenna and other things, isn't it? Their ice particles are depositing on that. So when you apply this self-cleaning coating, it will be protected. Can I take 2 minutes, sir? That's all right, sir. Right. So this is what. So I want to, give more attention to this futuristic material. People can work. This is a fantastic work. Super hydrophobic or self-cleaning material. I am specifically requesting all students to work in this area. You will have a multiple applications, and this is the future of your technology also. Okay, this is my last slide. So what is the future perspective of our rubber technology? Particularly, you should not always satisfy with the conventional development of, I developed a material, I have seen that the effect of carbon filler, the effect of curing agent. This is a conventional, isn't it? You should take the challenges. The world is growing. We are changing into digital world. So these are the main area. Like recently, yesterday also people talking about additive manufacturing. But the problem, anyway, you have the advantages, merit and demerit when you start the technology. But definitely this will be applicable to other things also, like a 3D printing, automotive technology, salt gel synthesized material. This means more interaction with the polymer and the filler. Like then try to introduce artificial intelligence everywhere. People already started to work in this line. Then green material technology. Anyway, the previous speaker, he was talking very nice things about electronic scale, particularly automatic sensor, MEMS sensor. These are all even has got a multiple application in defense area. So people should work in this line also. Okay, thank you. That in summary, that so rubber, as I said, that which plays very pivotal role, particularly for our everyday life. Thank you very much.
Oh, fantastic.
Thank you.
One question, at least one question.
Yes, sir. Yeah. Yeah. Anyway, I am audible, please.
Yeah, this super hydrophobic coating that you are talking about with the pattern surface, how scalable it is, like when you want to implement it to a level 3?
Actually, now right now this is a prototype level only. We are trying because most of the things are in a device-based level we have developed.
Yeah.
When you talk about large area sensors, so we need to work further.
Not the sensors.
No, I am talking about hull, even hull area, big area also. We are trying to do that because right now you can able to spray coating. You can do that. So we are trying to do with this breast coating also, that we are trying to develop it. Conventionally, it is available in market UK and all, but when you talk about defense, they will not give it. That is also because when you talk about this is going to be used for Indian defense, particularly getting material from that is for that we are doing it. Definitely, it will come. Thank you. Thank you very much.
Once again, guys, he does not need my mic. Huh? Thank you very much.
I have to come this.
Oh, please. Okay. Dr. Naga, I think ask you to give a longer talk in my online session as well. Yeah. So, thank you very much. A lot to talk about it. Thank you very much. Okay, I need to manage the time. We are a bit behind the schedule. After this, we will have a coffee break. Simran, we will have after coffee break. Yeah, it's all right. Otherwise, everybody will kill me. Yeah. Okay. So, okay, let's go to the next topic of the today's present session. On the focusing on the anti-corrosion protective coating with the self-healing and vitrinization of elastomers. Is it somewhere connected with the marine application as well? Yeah, fantastic. Okay, so it's rightly placed. So our invited speaker is Dr. Hari Krishnan, an assistant professor at the School of Nanoscience and Nanotechnology at Mahatma Gandhi University. Worked closely with Professor Sabu Thomas. Yeah, so the legendary figure as well. So all over to you, man. Good.
So good morning to all. My name is Dr. Hari Krishnan. I'm coming from Mahatma Gandhi University. the topic of my presentation will be anti-corrosion protective coating for with self-healing. So I have slightly changed the title of my presentation, and it will be I'll make few slides on victimization as well. So as I said, I'm coming from Mahatma Gandhi University. It is one of the universities located at the southern part of India, Kerala, in the town of Kottayam. So as you can see from the picture itself, we have a very good scenic beauty in the Kerala and Kottayam. So actually, we have ranges from mountains to waterfalls and backwaters. So those who are wishing to visit our place, they can find it very like you can come for 1 week or 2 weeks. There are so many places to visit, so that you will enjoy each place in a different cultural way. And telling about the Mahatma Gandhi University, it is one of the young universities which was started in 1986. So, and within a short span of time, it is having a very good ranking in India as well as in the world level. And recently, we have also received a NAAC accreditation of A++, which is the fourth cycle. It is the 13th university in India. And as I said, if you want to come to Kottayam, there is an option for you. We are conducting one international conference, Polymera, which is on recent advances in polymer sciences. So we are jointly conducting this conference with IIT Kharagpur and Professor Kinsuk Naskar. He's the co-chair of this event. And we are conducting it from December 1st to 4th. On the 1st of December, we will have a 3D printing workshop conducted by IIT Mandi and Sri Idra. So I take this opportunity to invite all of you to attend this conference. This is just before the RubberCon in Kochi. So you can club both the conference together and come maybe. So coming to the school which I'm working on, it is School of Nanoscience and Nanotechnology. It is a very new school, maybe 4 or 5 years old. It was started by Professor Sabu Thomas, the visionary leader in the polymer science field. And we are running 5 different courses, basically on MSc Physics and Chemistry, which is specialized in nanoscience and nanotechnology. And also we have joint programs with Kannur University, which is another university in the northern part of Kerala. And we also have a MTech program. And as we know that we already had a talk from Professor Srigala. She's a joint director of the school, and she's also a director of the polymer science and technology at our facility. Coming to the work which we have discussed. So the background of the work is that our aim is to make a coating that can protect the corrosion. So as already Anadresa has mentioned, it is a very like a what we call difficult to maintain in the application area. So the main problem is the corrosion will deteriorate the metallic structures, which can result in fatal failures. And also, in order to overcome, there are many in past they have coatings. The general coatings can protect the metal surface, but the problem with such coatings is that over the prolonged exposure to environment, such coatings can deteriorate and it can cause damages. So it will further cause some cracks, produce some cracks with the presence of the moisture, and it will corrode the metal surface. And other developments were that instead of using the regular coatings, people come across with corrosion inhibitors, and such corrosion inhibitors actually protects the surface from corrosion. So they actually hinder the corrosion process. But the problem is that when we add the corrosion inhibitors in the coating, it does not provide a prolonged protection. So actually the corrosion inhibitors leach out of the coating, and during the period of time, the corrosion protection is lost. So we come with a concept of smart coating, which is the concept of self-healing coating. So self-healing is defined as the artificial or synthetically created substance which can be built in to automatically repair the damage. So as I said already, the coatings under the atmospheric, the harsh atmospheric condition, it undergoes some deterioration, and minor cracks are formed on this coating. So if we are able to stop that cracks immediately when the crack is formed, we can stop the further propagation of the cracks and thereby protect the surface from exposure to the environment. This we can protect the metal surface. So from the picture itself, we can see that in the earlier days, people used to work in the very difficult situations like high-rise buildings or metals. So the problem with this is that there is no safety for the human intervention, right? So, and in certain applications, there is impossible, like for example, underground pipes or overhead pipes for gas transport. Such places, there is no possibility of human intervention. In that case, we can use such kind of smart coatings which can sense the corrosion and heal it. So how does it work? So basically, in simple words, we can say that when there is a damage on the material, we can say that the crack is occurred, right? So when the coating is deteriorated, the crack is initiated, and this crack will trigger a mobile phase. Mobile phase means it can be also said that, in other words, we can say that it's a healing material. So healing material will come onto that crack side, and it will cover the crack, and later on it will immobilize on that crack surface to protect the underlying metal substrate. This is a simple video. So the material is cracked, and the healing agent or the mobile phase will come to the crack side. It will close, and once it is closed, we can immobilize. Immobilization can be done by cross-linking. So this is actually inspired from nature, as Dr. Annadure already said that there are different biomimicking, importance of biomimicking in the synthetic materials. So for self-healing also, we have mimicked certain nature's marvels. We are also having different mimicking examples. So this is the example of biomimicry of self-healing. So we know that the human skin or the animal skin, which when undergoes some kind of wounds or cracks or bruises, it starts to automatically heal itself. So we are bringing this healing effect into synthetic materials. Also, we know that in plants also, as most of you are from the rubber background, we know that we are in the morning, the farmer comes to the rubber tree and he taps the tree. By evening, the flow of the latex or the sap is stopped. So this is also a healing process. But we can tell that it is in the two phases. It is happening in the two phases. One is sealing phase, and second one is healing phase. Sealing phase means the initial stoppage of flow of the blood or sap from the tree, right? So this can take maybe hours or days in case of animals or human being, and in case of plants, maybe it will take a few hours. And the final healing phase, that is a new tissue formation on the skin of the wound surface, may take maybe up to a year, months and years, right? But in case of plant line, it will take maybe weeks to a month. But in the synthetic line, it is much more enhanced. So we can finish the sealing phase within maybe minutes or hours, and complete the complete healing phase within maybe days, hours or days. So how to measure the efficiency of this self-healing? There are different techniques to measure the self-healing efficiency. One is to take the optical image, SEM, or any optical instruments can be used to check the crack formation and the self-healing. Then we can also use the sweat analysis, where the profile of the material, or AFM also. If the cracks are too small, we can use AFM, or any kind of profiling test can be done. And if the material is cracked, or if the material is broken into two pieces, then we can also do a mechanical test. That is by finding the retention of mechanical properties. So initially we find the mechanical strength, then we break the sample, right? In the tensile machine, we break the sample. And if the material is healed together, we'll measure the tensile test again. Then we can find out the efficiency of the healing. So as I said, we can have different applications where the human intervention is impossible. I will take one example. There was one incident happened in Japan a few years back. One complete street was exploded because one single pipe that was transporting the LPG, that was having this corrosion, and due to the heat, the rising temperature, actually one of the pipes actually exploded. So this is the problem, that we cannot identify the corrosion in such kind of metal pipings at all. So if we have some coating, smart coatings that can heal the stop the corrosion from damaging the metal structures, then it is actually worth many lives. And so we can now come to classification of self-healing. There are two types of classification. One is based on the nature of self-healing, that is how it is healed, like whether it is automatically healed, or is there any need for external stimuli like heat or light. So if the damage itself activates healing, it is called as autonomic healing, and if there is any additional energy needed, it is called as non-autonomic healing. And the second type of classification is based on healing agents. So we have two types. One is extrinsic healing and intrinsic healing. Extrinsic healing means we need some external healing reservoirs to be incorporated in the matrix. And in case of intrinsic healing, we have to modify chemically. We have to modify the structure of the polymer so that we can get the healing within the polymer itself. So we have worked on extrinsic as well as intrinsic healing. If we come to extrinsic, there are different ways to achieve the extrinsic self-healing. That is, we can have the containers in the shape of tubes or capsules, or even we can incorporate the self-healing agent in the polymer itself, like phase separation, say phase separated thermoplastics we can incorporate. And when the phase separated thermoplastics in the thermosetting or rubber, or maybe thermosetting epoxy or polyurethane, any kind of polymers, if we incorporate thermoplastics which is phase separated, when there is a crack, we can heat it, and the thermoplastic phase will come and fill the crack site. And another example is using of microcapsules, which is based on urea formaldehyde or melamine formaldehyde. We are using emulsion polymerization to encapsulate healing agent, which can be any kind of resin, like epoxy or any resin we can use, which can be cross-linked later. So then also we can use glass tubes or tubular structure like carbon nanotubes or halocene nanotubes, TiO2 tubes. There are different tubular containers which can be filled with the resin. And if we are using a one-part system, we can completely fill the tubes with that one-part system. It can undergo cross-linking with the presence of heat or temperature, heat or maybe UV light, or any kind of cross-linking process. And even we can use alternatively we can use fill one container with the healing agent as well as the second container with the hardener or a catalyst, right? So when the hardener and the catalyst come in contact with the resin during the cracking, in that crack site itself, it will start cross-linking. Or even the third type, we can have the resin completely filled in the tubes, or we can disperse the catalyst in the bulk of the material. So when the resin come out of the tube during cracking, it will come in contact with this catalyst and undergo cross-linking reaction. So we have done some work on the extrinsic healing. In our work, we have used a dual container system. That is, we are using two different containers. One is based on the clay sheets, which is known as halloysite nanotube, clay nanotubes. We are using clay nanotubes to hold the healing agent, as well as the silica, mesoporous silica, to hold or immobilize on the surface of that is UV initiator, so that in the presence of sunlight itself, we can carry out the self-healing process. In order to make such material, we can use a process called as vacuum infiltration. So when we are using the halloysite nanotube, it will be mixed with the resin, and it will be vacuum will be applied to that, so that in the high vacuum, the air inside the tubes will be frizzled out. That is, it will come out of the tube and it will be replaced with the resin, and thereby we can fill the tubes. And we can fill the immobilize the silica just by ultrasonication process. We can immobilize the UV initiator on the surface of the mesoporous silica, because the mesoporous silica has too many porous sites to hold the UV initiator. And when we mix the material in rubber or epoxy or any kind of matrix, we can have that, like during the process of cracking, the halloysite nanotube will break and the material resin come out and come in contact with the UV initiator on the surface of silica. So in order to confirm the filling of resin, we have done TEM analysis, and you can see that during TEM analysis we are having that healing agent inside. This is a regular tube, and this is the tube filled with resin. And also we can confirm the filling using FTR analysis. The presence of unreacted epoxy is found with the increase in the halloysite nanotube in the matrix. Also, we have done SEM and EDX mapping. During the EDX mapping, we can find that there are a lot of dispersion problems, but the silica particles are actually dispersed heavily throughout the matrix, as well as throughout the nanoparticles area. So we are expecting a very good self-healing. And same way, we have measured the self-healing using nano indentation machine, where the nano indentation, that is a nano pin will be there that will make a scratch on the surface and take a photo. So during this process, the halloysite nanotube will break, and the self-healing process will complete, and we can see that during the process 100% healing is happening. Now coming to the second type of healing, that is intrinsic healing, we have used, we can have a different chemical, reversible chemical cross-links, or physical like hydrogen bonding or electrostatic pipe stacking, and in dynamic covalent bonds, diols are this reversible interactions can be brought into the structures of the polymer, and thereby we can have, like when we give a temperature or pH change or any kind of different stimuli, we can have a rejoining of the material. But in our case, we are using an ionic liquid based self-healing method. Same like previously we said, we are mixing the ionic liquid into the epoxy resin. So in order to get a highly flexible and transparent coating. So this is the transparency we are getting even after putting the ionic liquid. We are getting good transparency, and we were able to reduce the glass transition temperature below the room temperature to get a very flexible and this also help in the shape memory behavior. And in order to find the self-healing efficiency, we are using nanodegradation as in the previous work. Here we can see that the presence of ionic liquid. The presence of ionic liquid, we can see that immediately within 3 seconds we are undergoing self-healing. So the healing immediately initiates the crack, or the initiation of crack immediately starts the healing process, and within the span of 48 hours there is no sign of any cracks. This is the mechanism behind. We are having a charge transfer complexation reaction happening between the ionic liquid and the epoxy groups. So this will enhance hydroxyl group of the epoxy, and this will enhance the self-healing. And in order to find out the efficiency, as I previously mentioned, we are using a tensile method. We are finding out the tensile strength and elongation before and after baking. So we can see that around 50% of mechanical properties are retained even after the healing process. And coming to the but the problem with this kind of material is ionic liquid material is during the outdoor weather condition, that is if we are using UV light or sunlight, this kind of ionic liquids can during that time it can deteriorate. That we have done with the accelerated weather test machine. And we found out that during some exposure to 1 year or 1.5 years of exposure to the sunlight, it can deteriorate. So the properties of self-healing will be lost within maybe 6 months or 8 months. We are expecting that. So in order to avoid that, we can also go for other kind of intrinsic methods where the material property will be retained for a longer period of time. And one such method is using of Wittermers. Wittermers is nothing but vitreous monomers, like this, introducing thermoplastic component in the thermosets. So it will actually it will be the introduction of dynamic covalent bonds, which are reversible in the presence of temperature. The bonds will in the presence of temperature, the bonds can realign itself. Just like the disentanglement of the thermoplastic material, here we are having a reversible reaction happening. And in our lab, we are able to produce some Wittermerization process with natural rubber, as well as other blending natural rubber with other general purpose rubbers. So this is actually once the film is made, we have cut the film into small pieces, and again we have remolded it. So this can be continued for 3 or 4 times. We are only in the initial stage of the study, and we expect very good recyclability as well as reshapeability, shape memory behavior, as well as self-healing behavior. So I would like to thank Technobis and Mr. Peram for inviting me for this Rubber Innovation Conference. And I would like to thank Professor Kinshuk Naskar also for inviting me. And I would take this opportunity to thank my co-authors, Professor Susha Singh, Professor Jyotish Kumar, and Dr. Jürgen Piontek. So this is a short biography. I am working on different toughened blends, polymer composites, water remediation, then self-healing coatings, packaging materials, novel plant fibers, 3D printing, and Wittermers. These are the currently my research areas, and I actually I find this opportunity to tell that I'm open to any kind of collaborations, and in future we can maybe collaborate on any of these areas and other areas also. So thank you so much. One more thing, this is actually we have a new school at Mahatma Gandhi University, School of Polymer Science and Technology. We have started a executive MTech program for working employees who are working in employees or other research institutes. The courses will be offered online and offline. It will be in hybrid mode. So those who are interested can share among your peers. Thank you.
Thank you, Hari. Thank you very much.
Thank you, Dr. Hari. It's a nice presentation. Suppose, for example, there's a thermoplastic urate TP. You want to introduce this simply moieties. Also, how to process it?
It's easy. We can. I will not suggest the ionic liquid base, but we can go for ionomers base, which is more stable. We can introduce some like electrostatic or much more which can be reversible in nature. Like if we have some change in temperature or pH change, we can get the reversible interaction between the TPU.
Why I'm asking is there are some hoses which is 100 or 200 meter length of thermoplastic elastomer based hoses, which is being used in underwater application. The problem with this all these polymers, there is a problem of fish biting. Once it is biting, means all this water will enter into the tube where all the sensors are placed. So, and also when you apply this coating or your material, it should be transparent also, because we have to see that what is inside also. So that's so what is the process? These are extrusion process. So is it possible to incorporate during this extrusion process?
Actually, if we go for Witrumers, what kind of thermoplastic TPUs? Is it by itself transparent or
yes,
transparent?
Yes.
Okay. Then by incorporating Witrumerization, we can introduce this kind of dynamic covalent bonds within the bonds, so that there is no need of coating. We can directly go for changing the structure of that material. Then we can have self-healing behavior in TPUs.
Thank you, Hari. Thank you very much. Thank you. So I'd like to present, you know what I said. Thank you in Thai language. He lived in Thailand for a few years, so thank you very much. Thank you very much. I'd like to present Arshad. I don't want to miss that one. Give him a big hand, young boy, the future of rubber technology. Okay. All the best. Okay, let's have a coffee break for it. If I ask 10 minutes, anybody throw stones on me? Nobody throws stone on me, right? 10 minutes, man. Okay, we'll back it. I would like to get in on time schedule. So 10 to 15 minutes. If 10 minutes looks like by the time you get a coffee, you're already 10 minutes. So 15 minutes coffee break. Yeah. You're updated. I'm actually thinking of what time you want to do exactly. Time exactly from the hotel.
Immediately I close my assignment.
Okay. I'm thinking that because we are one topic. There's a girl before you. I'm thinking maybe I ask her to wait and you do the presentation first if you want to. Yeah. Because just be depend on how much time you have here.
No, I can stay till 1 o'clock.
Not till 1 o'clock, right?
11:45. 12:30.
Yeah, I think so. I can manage it. 12:30. Up to 1 is okay.
I'll just upstairs after second. I can just see my email and second. Today,
I think you sent me the latest one, right? Just check first. Today, yeah, fine. Okay, so yeah, I use it. Okay, fine. Let's check this one.
So for Technobis food. Yeah, that's
Actually, I want this topic to be in my rubber tech talk, because this you can spend more time on it.
Yeah.
So
This is very compressed actually, but
you can expand it. Yeah, you can.
Maybe
next time.
So now after Ajay, then that lady, and then my talk with them. You are shuffling it.
Yeah, exactly. Because just
Yesterday,
because of
you
mine.
also leave.
What time you're leaving?
I'm okay. I have a flight at 7 o'clock. Yes. Just open and check if it's working.
When you have so many speakers, it's a challenge to get on time.
Yeah, that's okay.
Why is it show here? Why didn't it show here yet?
It's all right? Maybe it's a extended. Maybe that's a second display and this is the first display like that. Maybe that costs sometimes. Yeah. It's closed.
Let me take out your flight. Then press this thing. Because all the files are there. You have to be careful. Sometimes you forget things. Eh? It never happened to you?
Yeah, it happens multiple
Let it go
times.
as social.
Huh?
Let it go as social.
Okay, fine. Ganesh, there's no gap in between? Do you have a gap?
Oh, I have a gap.
Is it?
Space is there.
Yeah, I think sometimes you write together.
No, I never write like that. I always put a gap in between.
Okay. I don't see here.
That is what it's going like extended. Okay, it's a presentation file, so that's the reason. But just change that in active window. Yeah.
Second. How should you do that?
That's presentation file. Maybe that's the reason it's just coming as a slides.
So what I need to do?
Just you open it and then open. And then I can just what is it? This is the one, right?
But it's not showing.
Yeah, it's fine. It will not come because it will be a slide.
Oh, okay.
Yeah, it's going. Fine.
Okay, I see.
So you can close it.
Okay, so you don't need to see here. You can see on the screen.
I'm fine with that.
Okay, fine. Yeah, let's
close it off.
Yeah, let me do that.
Thanks.
Next, sure.
I need to load out directly. I think it's not a good time.
This way.
The other way.
Can you put it in? There is a problem with the dry. No wireless dry?
Yeah, I use it just.
Okay. I'm scared of my computer nowadays because so many people put so many things in there.
Yeah. You must be having antivirus.
It is there, but still. Why you have so many CSV? Yeah?
Actually, yeah, it's like I'm a PhD scholar. I have a lot of data.
Data, right?
Yeah.
Okay, see.
There's a folder, if you can see, with the Technobis name on the line. Yeah, from here there will be a folder.
This enough of it.
Just a second. Yeah, Rubber Technique Forum. This one. Okay. So I'll keep the presentation open, updated one.
You have 10 minutes, yeah? We need to know we are beats behind the schedule.
Actually, I was finishing in 6 to 7 minutes,
Oh,
so I
okay.
added 2 slides more. I think that will ease your work.
Yeah, it's all right. Just want to manage my time. So this is true one. Have we delete this one?
Yeah, you can.
So let me take out your. It's already out. Okay, all good. Yeah. I'll keep it open so that we save the time. Yeah, okay. Let's keep it that way. Okay, moving. Like one. Yeah,
The pointer is also there.
I guess so. Okay. Yeah. So, okay. Are you good?
Yeah.
Very good. Yeah. Yes, that's close. Yeah. Yes, that's right. Close. Yeah.
Close to the mouth and
And also you can get some Basi and Northway, maybe meeting.
okay. ओके वीडियो है
ओके ठीक है और एक बार कर सकते हैं
nice and to calculate. Now, अच्छा अच्छा अच्छा
Come on, guys, let's get inside. Okay,
I think, it's always challenging to manage the time in the conferences. How much you want to be good at it, it's not possible. Yeah. So let's invite our next speaker of this program, Rubber Innovation Forum. We have a young researcher from IIT Kharagpur Rubber Technology Center, Ms. Simran Sharma. She's going to give a talk on the graphene liquid rubber nanocomposite based flexible sensors. Lady researcher. So I'd like to have a warm welcome to her. Yeah.
Thank you. So good morning, everyone. Today I'm going to present one of my PhD objective, and that is the development of liquid rubber and graphene based nanocomposite based flexible sensors. So I hope whatever the last speakers gave in the future scopes, so we have already started working on that, and this particular topic I have done as my second objective. So let's go further. I have not prepared many slides. I will not take much of your time. Hope to complete it on time. And then firstly, like, what are the benefits of the elastomeric nanocomposite sensors? So why should we go for them? So basically, these kind of elastomeric sensors provide the flexibility, thinness, lightweightness, body conformability, and multiple sensing capabilities. For example, you will be able to monitor different kind of strains, pressures, temperature, humidity. All these kind of things can be monitored through such kind of sensing devices. But now the challenge is, if we are going to utilize the elastomers directly, we cannot develop these kind of devices. Henceforth, what we do, we utilize certain functional fillers. So the functional fillers that we utilize are like graphene, carbon nanotubes, MaxSense. So such kind of materials, when they are mixed with elastomers, provide such benefits that we can utilize these materials as sensing devices. So there are different technologies that we can utilize. I will be talking about printing technology that I have utilized for the development of such type of sensing materials. So general techniques that people are utilizing all over the globe for printing of sensors are like screen printing, inkjet printing, lexography, stencil printing, due to their ease of use, time saving, and their cost effectiveness. Now, what I have done, so in this work, I have utilized liquid polyisoprene rubber, graphene, and dichromyl peroxide as a crosslinker. So the usage of liquid polyisoprene rubber allows me to make a solvent-free system. So basically, I have utilized the neat liquid isoprene rubber, and then have utilized graphene, that is giving me the functionality to the system, and dichromyl peroxide as a cross-linking agent. So the method I have utilized, firstly, I have mixed it in a thinking mixture or the centrifugal mixture where I can get a bubble-free formulation. For example, if I'm going to print something and it is having bubbles, that will cause problem in my device. So basically, more the bubbles, more will the resistance. Henceforth, we need a system where the foam and bubble is not there, and this kind of machinery is allowing us to develop such kind of inks. Now I have utilized a simple stencil printing technique where I have printed this layer onto the substrate of polyethylene terephthalate, and then what I have done, you can see over there that in the So here we can see the printing is done. This is what, then after the curing, I've applied the silver paste that will act as the electrode, and then I have applied the copper tapes and the wires to the sensor, and then I have used this particular sensor for the breathing, for detecting the breathing. Okay, so firstly, what we studied different kind of graphene loading we have done to the system, and then what we find out, we plotted this traditional conductivity graph, low conductivity basis, the amount of pHR of graphene that we have utilized. So what this graph tells me, so this is a graph where I can see in the lower region when I'm loading different graphene to the system, here the material remains insulating. Okay, and as I increase the loading from 5 pHR to 6 pHR in 7, it just increases exponentially and further saturates down. So this particular regime is of particular interest to us. So you can see the insulating phase, the fillers are segregated. In the percolating threshold, after this particular threshold, the network structure is starting to form, and after that it becomes conductive when a lot of these percolating networks are joining together. So then this particular region, why is it of interest to us? Basically, when we take samples from such a percolating regime, that sample is more sensitive to the external stimuli. What are we going to apply? Okay, so we have taken this particular sample. Then how I have done all those things? Firstly, the liquid rubber, what I have done, I have plotted this viscosity profile, and we can see that it is giving us shear thinning behavior. That is very much needed if you want to coat a material or you want to print a material. So such a behavior has been analyzed with the usage of rheometer. And then how do I optimize that my material is being cured? So also we utilized rheometer here again, and then we optimize it traditionally, but this is a parallel plate rheometer that we utilized for this study. And then we have taken out this much of time we will take for curing at a particular temperature, and then have done the study. Okay. Further moving forward, what we did, so this was a viscoelastic liquid material that we were having. So you can see the characterization, like we have plotted the loss modulus and storage modulus. The storage modulus tells us about the rigidity of the system, and the loss modulus about the how much damping it is having. Okay, so basically we can see that loss modulus is higher because it's a viscoelastic liquid system. Okay, so further when we cross-link it, we checked it through the thin films DMA, we can see the storage modulus has increased and loss modulus has decreased. Okay, so from this particular viscoelastic liquid, we have shifted to the viscoelastic solid materials through the cross-linking process for this particular liquid rubber. Okay, then what happened? We studied it for strain sensing, like what will happen to it. This was the reason that we selected the percolation regime. Okay, so for bending strain, I have sensing. Since I am going to use the sensor for sensing breathing profile, so I need what will happen if I apply small amount of strain. Okay, so what we did, we applied different kind of bending angles to the system. Okay, we have done at different bending angle, we have done the study so that small strain is being applied, and then we have used the equation to convert the bending angle to the bending strain that will be generated. Right. So these different three small strains we have studied: 0.11%, 0.17%, 0.2% strain. Okay, very less amount of strain that is being generated in the system. And this is what cyclically we have checked. For example, the black graph represents when we apply 0.11% strain, and then 0.17 and 0.2%. So different strain it can sense. This is what we concluded from this study. Okay. Now what happens for the application part? So I'm showing in very short that this particular sensor I have attached to the mask that I have developed by the process that I've discussed earlier. And then when we attach the sensor to the mask, due to our breathing, if we are breathing normally, we can get a different waveform. If we are breathing fast, a different deep breathing will give us a different kind of waveform. And then if I do no breathing, no signal will be detected. If I do slow breathing, then I get a different waveform. Although we have done further analysis of all these waveforms that you can, if you are interested, I can share my paper, and I have also given the reference over here. Then this is what we have done, a real-time study. Okay, so what this video is going to tell you that this kind of small sensors can be utilized to power, can be utilized basically for the IoT-based devices. We have made a prototype. So this prototype is like wirelessly the data from the sensor is being transferred to the mobile phone, and the corresponding graph you can see on the computer. Okay, so you can see over here. Oh, I'm sorry. So you can see over here the profile, the graph. You can see it is, we are getting peaks over there, okay? And also in the mobile phone, their virus is transferring the data. So it's a real-time prototype that we have made in our lab. Okay. Then further, how do we look forward for these kind of works? Basically, we all saw in COVID times, we had a lot of difficulty in getting hospitals. We do not have so much of healthcare facilities available everywhere throughout the country, especially in the regions where rural population is there. Like a model like hubs and spokes model can be utilized where spoke D or the small clinics or the D type of clinics and small healthcare centers can have such kind of devices where you can see that what kind of damage is there to the person. So these kind of profiles can help in such areas, and then further they can refer it to the highest hospitals. So that is what the outlook is for these kind of applications that we have looked forward. And this is my team, and I acknowledge SCRB for funding the project that I have done, and my institute. Also, I'm thankful to Technobiz for organizing this event and giving me the opportunity to speak over there. So thank you, everyone. These are the references. Thank you. And if you are interested in the topic, this is my publication, already done, also highlighted in Nature. So you can go through it. I have done more work. I've shown a little amount of work over there, but there are different things we have done in this segment. And any questions?
Thank you. Any questions to us? Questions to Zura?
Thank you then.
Thank you, Harsh. Thank you, Zura. Thank you, sir.
Come on. Token appreciation. Thank you very much. Can you take a picture for me, man? Okay, camera, video camera. No, you can use my mobile. Come on, just a second. Okay. Oh, okay. Camera is there. Okay. Thank you. Thank you very much. So let's move on to the next presentation. What's up, Kevin? Kevin. Is a video? Okay, this one. Super. Okay, let's get to the next presentation. This person is very special to me. He's also traveled to Bangkok in my conferences, and very knowledgeable guy, active guy, specialized in the rubber testing and rheology aspects of it. Currently is working as the senior scientist, senior manager at the HASETRI. As in many of you know about that reputation, the services they provide across the India and beyond. So he's going to give a Mr. Ajay C. And I always ask what is C means, Ajay. Okay, maybe you can say expand it more. And we'll invite him to give a talk on the enhancing quality control and performance optimization, the role of rubber process analyzer, RPA. Ajay, over to you. 20 minutes. Yeah, thanks.
Thank you, Parag. Good morning, all. Okay, it's good afternoon. Good afternoon. Myself, Ajay, I'm representing Harshankar Singhani Elastomer and Tire Research Institute. Today, I'm here with a topic on enhancing quality control and performance optimization, the role of rubber process analyzer. Actually, my colleague Dr. Sekhar Dasgupta has already given a brief about the activities of SZ3 yesterday. So I'm skipping this slide and will be more concentrating on the presentation with respect to my topic. So RPA is nothing new. It has been there since last almost 20 to 25 years. It's a very sophisticated equipment. At the same time, means it is highly research oriented, and at the same time it is very much quality oriented, and which has to be utilized in the day in day out regular shop floor activities. So my presentation outline will be giving an introduction on RPA. We will see the overview of RPA applications, certain test possibilities. I will take you through the basic test possibility. Maybe a few of them will be very much aware of it, but still I will be taking certain basics of RPA. What are the different test configuration is possible through RPA? Then we will see something different apart from what we do in our regular routine activities. What makes a difference of application of FT rheology in Laos? Certain case studies which we have done in our laboratory, and followed by conclusion. So RPA is a tool which we evaluate, which we utilize for evaluating the material properties and for processing characteristics. The main importance involves the evaluating the quality and performance of rubber products, key role in various stages of rubber production, even from material development to the process optimization, helps the manufacturer to develop the superior rubber compounds and improve the manufacturing processes. Main function include, we know MDR can be, RPA can also be tested as an MDR, like the rheological testing which we do for understanding the flow and deformation behavior, cure properties, dynamic mechanical analysis, as like what we use the dynamic mechanical analyzer to study the cured vulcanized. Same way we can study the characteristics of dynamic mechanical characteristics in the uncured stage by doing the in situ vulcanization, also by using rubber process analyzer. Hysteresis testing to understand the thermal performance. Today morning, Dr. Chris has given a beautiful presentation on understanding of the thermal properties, mainly which involve the cyclization and also how the chain session can be studied through the presentation, which is very clear and which will be very easily understandable and informative. Moving into the overview of RPA applications, these are the different RPA applications which we can take the input from it. Quality control, it helps in maintaining the quality by measuring the key properties. We will see the different properties. Performance optimization helps to optimize the performance, leading to a better product durability and functionality. Helps in material development for fine-tuning the different recipes and formulations. It is very useful. Process optimization helps in the processes like mixing, calendaring, extrusion, curing. All these areas, the contribution of RPA is tremendous. Understanding the defects. After becoming the product, before becoming the product itself, we can get an insight by using rubber process analyzers to ensure the reliability and performance of the rubber products. We'll quickly go through the different test possibilities. Normal cure kinetics. You can study the cure time. We can study the onset of vulcanization, scorch time. We can study the cure rate index, how the rate of cure has been taken place. These will help us for fine-tuning the curing system, helping for the formulation of the rubber compounds. We know what is the ideal curing time which can be given. It can be addressed, means the issues like under-curing and over-curing can be addressed by using this tool. In addition to cure kinetics, the same machine we can utilize for studying the variable temperature analysis, which help us to optimize the curing profile. which is very much important in factories to know that where my product is, whether it has been undercured or it has been overcured, or the curing process which has been efficient and consistent throughout. This is very helpful for very helpful for the factory. Certain times we get polymers of different similar microstructure and viscosity, but it behaves very differently in the shop floor. The complex viscosity, which gives us some kind of an information that what is the overall resistance of the polymers, which directly deals with the issues which can come about the improper flow characteristics. We have been using this for understanding the filler-filler interaction for a long time. That's the pain effect. Sometimes understanding the pain effect also, RPA is very much tricky, that we will see in the latest slides, how we will be getting misled at certain times by studying the pain effect alone. Strain sweep, we can vary the strain, we can understand means over a range of strain we can do by varying the strain, and we can do the study. This is very important for products like seals, vibration dampers, etc. Same way we can vary the frequencies, very much important for tires. It will help us to understand that during the operating conditions how this compound can behave well. All this can be done after in situ vulcanization too. So this gives more complex information, because in one extent, if you look into the total testing possibilities of RPA, we can get an insight what we are going to get from partners, tensile, dynamic mechanical analyzer, rebound resilience. All this information will be able to capture for a good scientist to understand from the RPA study. It can act as a DMA. Same, we can understand what is the stiffness, what is the energy dissipation, the ratio, which has been already explained yesterday when we are discussing about the DMA. We will be able to know the tan delta. Today morning also we have seen different examples. Creep and stress relaxation also can be possible by using RPA. Creep, which gives the deformation of the rubber compound at a constant stress over time. Same way stress relaxation, because this helps in understanding the different issues which can come due to premature aging or service or the failure during the service. Hysteresis, test method itself, we are thinking of to develop by using RPA, how the heat generation properties can be studied. I will share the glimpse in my slides. So these are the different different day-to-day tests which we can perform on rubber process analyzer, and to get some kind of insight from it to understand the properties. But nowadays, earlier also, as an updation to the rubber process analyzers, manufacturers are coming with this Fourier transform information into the Pro software, where we can study the harmonics at different level. This is very insightful, because as you know, whenever you see the behavior of the rubber, it is not going to be linear throughout. There is going to be having a non-linear viscoelastic region. So whenever you give a strain, when you give a high strain in this non-linear viscoelastic region, your signal, the stress signal, what you're going to capture back is not going to be as sinusoidal what you think of. In case of pain effect, it is assuming that it is the stress signal is somewhat as like what you are given as a strain, and we are capturing the data, but it is not exactly. There is a distortion which can happen, which happens at higher strains for higher strains in the non-linear viscoelastic region. So this can be addressed by studying the FT rheology at a non-linear viscoelastic region. Viscoelastic region itself, like we can study at a different strain, like small amplitude, medium amplitude, large amplitude, oscillators. So if you can see the graph, the signal which has been given on the linear region and on the non-linear region, you can clearly say that non-linear region you are not getting a exact sinusoidal curve. So this is going to have an impact on your test data when you compare between different particle size, different structure, you may not be able to see this kind of differences, because of course that impact what is going to have on the test of different particle size and structure is one way it is getting, but this is getting masked. But if you see, if you check by varying the mixing time, like 1 minute, 2 minutes, 3 minutes, or different minutes, sometimes your test results will overlap each other, because there this information really plays a role. So when we study about the harmonics, the Horde harmonics, which gives us some kind of information to the primary flow, and the even harmonics, which gives us the secondary flow. It's a very sensitive tool which helps us to understand the filler-filler interaction and also the polymer-filler interaction too. So in the initial, the first one which you can see, that is a normal plane effect. What you see, we give some kind of a strain and we are getting the stress. But when you see the signals from the signals in the form of the strain what we applied in the non-linear viscoelastic region, you're not going to get exactly as like what we have given, and it is not going to be a good response to it. But by applying the FT rheology, we can get a good amount of signal and good amount of information that how your rubber compound is passing through this region. So these non-linearities, which gives us a good information about the because at lower strains always the filler information can be gathered, whereas at higher strain it will be rather the role of the polymer is going to have more impact on it. So polymer filler interaction will come to the play, and at the same time whether this fillers is again getting reagglomerate or deagglomerate, we can be able to understand from this. Non-linearity parameter I will be touching upon. Now we will see certain case studies what I would like to show. So this dynamic viscosity is having basically complex viscosity with a shear rate, which is having a very good correlation, and at the same time very good information towards the factory process, other than comparing only with the microstructure properties. Certain times we used to get an feedback information that this rubber which behaves on the rubber process analyzer is having better processability while comparing to the inputs from other test parameters. Pain effect, if you look into, at the initial time we will be able to have a clear-cut variation, but once it goes above a 10 to 15% strain, you can see that we will not be able to have a clear-cut differentiation between the different test data. So this, to an extent, it is because at when we go for the higher strain during the non-linear viscoelastic region, pain effect will not be able to support to a greater extent. Whereas if you compare between the particle size and structure, this is still a fine, very good tool. We will be able to, but very close to go into the next level to understand what is the exact the filler-filler interaction has been, how well it is, whether it has been getting break or not, how the polymer is getting interacted with the filler. For that, we may need to go for support of the FT rheology, what I was trying to connect over there. LAOS is a very useful test and very much known for everyone, which will gives us an information about the LCB, basically long chain branching. LCB index, when it comes to whether there is any kind of a secondary loops into the Lissajous curve. Lissajous curve is also everybody knows might well. So when there is any secondary loop, we may be able to know that there is a linearity exists. When there is no secondary loops, it's a branching. But certain times here also we used to see that the polymers exactly it is claimed to be a linear, but we will not be able to see that there is a kind of secondary loops. So certain times LAOS may not be sufficient enough to understand that this long chain branching. So at that point of time, so this LAOS means if we will be able to understand with respect to how it can be correlated with the polydispersity, whether the long chain branching what we are seeing over here, whether we are getting the sufficient correlation with the other available techniques for studying the molecular weight, and how whether it is wide or broad. There is a relationship also existed, and it has been proven also. But sometimes very close configurations will not support for understanding whether it is really a branching exists or not.
Non-linearity index, which is basically with a non-linearity index with a strain, which gives us a kind of an information. Like if and this graphs as I have clubbed together, it has been a little bit clumsy and together. If you really look into the graph, the initial onset region will gives us a good information about your filler-filler interaction, and in the middle strains you will give an understanding on the like a non-linear viscoelastic region has been started, and further going on higher strains you will be able to understand how the rubber filler interaction is better. So this is basically non-linearity index, which gives us the third ratio of the complex modulus of third harmonics to the first harmonic. So you can see that one is master batch and another one is final, how the dispersion, because here it is a mixing study where it is started from 2 minutes to 10 minutes. So this gives us somewhat a better trend, and also a better trend in the sense we know if you start mixing from 2 minutes to 10 minutes how the dispersion can be. So this gives more or less a practical example. So this FT rheology also, this is the first harmonic data with comparing with the strain, how the filler interaction higher by seeing the graph we can see that how the blue dots which you can see that which is a very small mixing time, how the filler interaction has been more on that, and how it drops later on the third harmonic when we are studying off. This is another one study where we can study the phase angle with the frequency. It is one additional test which we can perform and see that whether the LAVO study that we have got, whether it is linear or branching, whether it is really supporting to the claim or not, because the phase angle at a lower frequencies which gives higher phase angle at lower frequency which gives a more linearity to the polymer. Van Gogh plot which we have seen in morning also, this also gives us a better understanding on long chain branching. At the same way, lower the phase angle we will be having better elastic characteristics, and higher the phase angle we will be having better viscous characteristics. This also gives us an input ahead on what the normal information what you used to get it from the literatures. To study, I have touched upon how we can make use of the thermal characteristics. At the same way, we can study the heat buildup characteristics also on the rubber compound stage itself. This is having a very good correlation with the existing heat buildup characteristics by using different other available techniques, which we try to correlate with the UTM, heat buildup, BF voltage flexometer, dynamic mechanical analyzer. There's a good correlation, and also a test procedure and configuration has been prepared based on the experience and with the manufacturers. So in short, if you look into RPA is a very good tool which will help us for the daily day out the quality control activities, understanding the performance optimization for developing materials, developing new materials, optimizing the processes, and also analyzing the defects. These are the different references which I have gone through. Thank you.
Sorry. Running around all things. So, right. Question to Ajay. Yes. Okay. Ask a tough question.
I have a simple question. Actually, what is the importance of this strain essay or strain if it is an application point of view? If it is increasing in a compound, the linearity increasing, what it means?
No, in SAS generally, which gives us the information about the filler-filler interaction. So whatever the fillers is there during that particular strain itself, it will get broken into. So that information we can able to understand from there itself. But the thing is, when it goes into the non-linear viscoelastic region, we will not be having a great information what is happening with the polymer. If you look at normal pain effect, your 100% data for all the test data will be very much similar, whereas everything which has been broken up in the initial stage itself. So that is why most of the RPS go up to 1000%, and they have been categorized that up to 100%. You can see that it is a SAOS range, whereas 100 to 300 can be MAOS, and above that it will be a large amplitude oscillation. So all the filler-filler interactions which will be able to visible in the SAOS range.
So it depends on filler type also.
Yes, because that is why very easy to characterize of
fillers of different particle size and structure. Whereas when it comes, if you are comparing the 5 same compounds by using various minute changes in the process, some certain times RPM may mislead. But we need to interpret the results accordingly with your experience and wisdom. Thank you. And thank you, Mr. Param and Technovis for giving me this opportunity, and also thanking the management to allowing me to share this small presentation over here.
Thank you very much. Thank you very much.
One more.
Okay, there is some shift in the presentation slots. Okay, the next speaker will be also from same organization and his boss, right? Just let me open the files first. So our next speaker is Dr. Prasenjit Ghosh. He is from Hassetri, the general manager at the prestigious, Rubber and Tire Research Institute, testing as well, rubber testing and tire instrument. How many years in the? Don't want to tell how many years, right? Or your industry experience with close to 30 years now, 25 years. So well experienced. Is a well-known person, well-known rubber technologist, Dr. Ghosh. So I have one more thing to tell you. I'm going to add 10 more minutes time for you. This topic is very, very important. So please elaborate, because this one I like to be part of my library, okay, in the rubber industry library. So please allow me to give a little extension time, fatigue and aware of rubber and insight. So join me to welcome Dr. Ghosh, please.
So this one is good afternoon, everyone. Before I start my presentation, I would like to thank the organizer, especially Professor King Srinaskar and Mr. Param, for giving me the opportunity to present my thoughts with all of you. And these are the fatigue and wear are basically two topics that itself and can take hours to discuss on those matters. And fatigue, I think Mr. Param has ensured that everybody gets fatigue at the end of the day because of the extended hours. I'm not sure about the wear, how much wear is happening. No, it's compliment. Yeah. So the thing is that why these two topics? So let us try to understand that is there any relation between this fatigue and wear of rubber? And before I start my presentation, I would also like to mention, because rubber is a vast field and there are many rubber products are involved, and this fatigue and wear can be applied in any of the products. So whatever the examples I'm going to show, it will be mostly for the rubber, because I am working in the rubber tire research for a long time. So this is the outline of my presentation. So I will try to introduce what is the concept of fatigue and wear, and what are the influencing factors that can have impact on both fatigue and wear characteristics. And in the form of a case study, there will be there is one or few compounds where I will show that how this fatigue and wear behavior of these materials, and of course the results, and finally I summarize it. So what is fatigue actually? So there is a classical definition that it's a progressive weakening of the material, or it could be anything under cyclic and repetitive loading. And it's a cumulative damages. It's not only the one time, its damages are getting accumulated over a period of time. And why these damages are happening? So there are intrinsic defects in any materials, whatever maybe even the glass, which you can see that it's a transparent one. Naked eye, you can't see any kind of defects at that level. But believe me, there is a defects exist in any material. And that's the reason actually you will not get the material doesn't fail to the ultimate whatever the theoretical strength of that material. It fails much below than that kind of what is the strength, actual theoretical strength. And these intrinsic defect sites exist in any kinds of materials, and specifically for the rubber or rubber compounds, you can see even in the raw rubbers also. Let us say natural rubber, there are a lot of impurities in the form of proteins, and those impurities can act as the defect sites. And specifically for the rubber compound, we are mixing different chemicals, different fillers and all, and because of heterogeneous mixing or any kind of thing, that those defect agglomerates can act as a defect sites. And these defect sites varies in quantities, and topology may be different, and length scale may be different. However, one thing is common, that when you apply the force or on any such materials or any such products, there is a stress concentration on those defect sites, and that is actually the starting point, and it increases the crack length over a period of time. And this is a cumulative process. And in the first, that fracture mechanics concept was introduced by Griffith, and that was for a brittle material like glass. And later on, in 1953, Rivlin and Thomas laid the foundation for fracture mechanics application in the rubber materials. So what is that fracture mechanics concept? So any fracture mechanics concept is that there is a known crack length, there is a crack length which exists. They assume that there is a crack exists for a certain length, and then how it propagates on application of forces, and it can be done on different environment. It could be temperature, it could be some different waveforms, it could be many ways, or it could be the aging also. And those concepts actually used in doing the application, actual testing over there. So before I take into the experiments and all, so I'd like to draw your attention that how the fatigue can have a catastrophic effect on the failure. So many of you may be aware about it. When personally, when I started my career, it was we came to know about the Ford Firestone fiasco. So what is that? Actually, before that, how the Ford and the Firestone started their journey. Actually, they were personal friends, and Henry Ford and Harvey Firestone. So all of you might have heard about the Model T. That was one of the successful and the first generation car automobile from the Ford. So Henry Ford decided that he will put the tires in Model T from the Firestones, and that's the corporate relation started at those days. And Ford was always a very respectable automobile manufacturer. And in 1990, they introduced the Ford Explorer, and it was a very popular car all those years. And what happened then? But it is still today, maybe that is one of the very popular vehicle, but the journey was not smooth all those years, and it entered into a certain kind of difficulties as well. And the statistics says, or the literature says, that between 1990 and 2000, that NHTSA, the National Highway Transportation of USA, they received a lot of complaints on the tire failure, and it is the complaint is not only the tire failures. There are about 200 deaths on the road because of this accident due to the tire failures, and this resulted in recall of 23 million tires from the market. And corporate journey, the corporate relationship stopped. You can see that almost 100 years relationship stopped due to this fiasco. So fatigue is so important. And incidentally, this investigation gone to the Caltech, California Institute of Technology, and one Indians, we should be proud of it, Dr. Sanjay Govindji is a father figure of continuum mechanics or finite element analysis, and he was given this responsibility to investigate this failure, and he found that problem belt separation is understood to be the propagation of fatigue crack in the bulk of the rubber separating the two steel belts of the tire, not at the interface. So in a tire, those who may not be familiar with the tire, there are a lot of layers like the body plies and the belts, which are actually the steel cord fabric coated with rubbers. And that was the starting point, and the crack initiated at that point, and it propagated throughout, and that was the reason of the failure. So the story doesn't end here. Actually, what happened? Why this thing happened? You know, all of you know. How many of you know that there is a suspension? There is an object called suspension in a vehicle. I hope everyone knows, which gives us a comfort. Correct? So there are in the previous days there was a dependent suspension. Means like you have two wheels, front wheels. The two suspension will be there, but they are dependent to each other. Dependent to each other means if something happens to the left side suspension, it will also impact the right side suspension. So and then the automobile engineers thought that why don't you have a independent suspension, meaning that let us say your left side wheel is on a rut or maybe pothole, so only the effect will come on the left side, the right side will not have any impact. So it is what is that? There is a decoupled the things, and that's why I call it the independent suspension. And this independent suspension again had issues when it was moving on any speed breaker or any kind of hump. It was having a difficulties with respect to two things: the straight line stability of the vehicle. Why? The camber. Again, what is the camber? This is a bit of what is automobile technology. Your tires or the wheels are not straight, it's not at 90 degrees. There will be either lean towards the vehicle or out towards the vehicle slightly, maybe in a very 1 degree, 2 degree, or maybe something like that. But that is very important for your straight line stability of the vehicle. All vehicle has that camber angle setting, even including the trucks. And maybe if you see the auto, you can see it is very much, and the tractor, it is very much, and those are on purpose. And because of this independent suspension, it was not proper, and this was getting destabilized all the time when it was moving over a pump. I'm taking a little bit of time just to explain the things. And what that Ford engineers, they found that okay, one solution they found that if they reduce the inflation pressure of the tire, the front tire, that gave some relief to that, but it came with a cost. What will happen if you reduce the inflation pressure of a tire? It will have a over deflection, and if there is a over deflection, what will happen? There will be a lot of temperature development, isn't it? And there will be a lot of strains, as Ajay was saying that how the stress is important, and that is the reason. Because of this over deflection, the crack initiates at the belt edges, and because of the temperature as well as the repetitive fatigue cycles, those cracks propagated. I can show you that this was the region. Actually, that was the actual picture of any one of the tires here, and from that onwards, that fatigue crack growth was one of the important topics for research. And just as a background, I wanted to inform you this is and this is available in the internet. I'm not creating anything; it's available everywhere. Just to set the context, I just put it. Okay, so now coming to the wear. Again, the wear is, there are two major categories like abrasive wear and the fatigue wear. And abrasive wear happens between the micro cutting, tear, and rupture of the polymer surface by sharp asperities with respect to the road. And it could happen with the conveyor belt. It could happen with your timing belt also. And fatigue wear, basically, it's the fatigue failure due to repetitive interaction with the, again, the road asperities, but relatively less sharper or the blunt kind of surfaces. So these are the two different types of wear. In the case of tire, it is again it is a combination of abrasive wear and fatigue wear, and it is very difficult to quantify. But people say that fatigue wear is the predominant it plays a predominant role in the total wear contribution. So this is just a picture that the roads are always not so smooth, and specifically in India and the interior portion. Of course, the highways are very smooth nowadays, but you can very often see this type of, don't you see this type of roads, the potholes, the stones and all those things, and that can create initiate the crack, and that crack can propagate. And you can see that why this picture is purposefully kept, that if you have a very small portion of the area which is come contact, it's like a thumb or palm size thing in the contact area, and there is a lot of stress concentration happens, and the crack can initiate from there. And once the crack initiates, it can propagate very faster depending on the, and of course that where actually it's not an intrinsic property of an material, although people say that okay, TG has a relation, this has a relation, that has a relation, but if someone asks what is the intrinsic property of wear, it's very difficult. Like it's not a very easy things to solve. So we need to correlate with something, and that's the reason actually we are bringing here the concept of fatigue. So now all of you know that what are the challenges of now wear. Wear is important from many aspects. One is your economical thing, like if let's say your vehicle is running only 10,000 kilometer and 20,000 kilometer, and if you have to change the tire because of tire is wearing out faster, then it costs you a lot. It will also have influence with respect to the performance of the vehicle, of the automobile, like your handling stability and other things, braking and other things will be impacted. And third is the now environmental part. So tire and road wear particles, I think many of you know about the tire and road wear particles. These are actually microplastics, and how the TRWPs are generated because of the frictional forces at the tire and road interface. And these materials are actually average density is about 1.8 times heavier than water. So it will go into the water and set there. And these particles are always not very in a same one length scale. There are many, there are fine particles, PM 2.5. Those are airborne, and one can inhale those rubber particles. Rubber and it's not only the rubber particles, tire and road wear particles, because your whenever the rubber is getting detached from your tire, and it is in a not in a very solid form, there may be some kind of not molten as well, but it can bind with different kind of sands or different asphalt particles as well, and that goes into the water bodies, and it contains everything like your all rubber chemicals, maybe your accelerators, your remaining sulfurs, your 6-ppd. For the time being now, 6-ppd is a hot topic now, and whenever it goes to the water body, it not only it's by feces and all, it also goes into the different grasses, and those grasses are also eaten by the your cows and all, and that milk we are eating. So it is microplastics are coming through all those routes, and because of that, there is going to be a norm or emission norm, that is Euro 7, which is will be equivalent to the BS7 in India. And till today, there was no norms that which actually having a tire wear particle. Now it will be going to be introduced from July 2025, and very soon it will come to India as well as in the form of the BS7. And there are a lot of pressures on, of course, the tire industry. and automobile industry how to control those things. So I just as a information I am telling you, and all researchers are there, so they should be knowing what is happening throughout the world. And it is estimated that 1 million tons of TRWP are emitted yearly in Europe due to this transport. So that is the big number, by the way. So now, if you see that how the fatigue happens, how the wear happens, the left-hand side plot is called, popularly known as Paris-Erdogan plot. So you can see, maybe many of you have seen that how these plots are. So basically, the crack growth with respect to the tearing energy, x-axis is the tearing energy, the energy required to propagate the crack, and how the crack is generated, the crack growth rate by dc by dn or da by dn. And you can see there are 4 such. Is not. Is it not? It was coming.
Let's see.
Yeah. So you see, initial zone, there is no crack propagation because that is called the intrinsic strength. So below that strength, even the crack exists, that won't grow, and product can have infinite lifetime, but which doesn't happen. And then it starts increasing here, and there is a steady state zone, and after that there will be a catastrophic failure after that zone. And the right hand side plot is also called the wear progression plot. Initial state is slightly higher, the slope is steeper, then it enters the steady state abrasion, and then the catastrophic abrasion happens. So do you find some kind of similarity in the steady state zone? Yes, there are. So we'll be interested in that zone, and as per the literature, that majority of the lifetime of the product spends in this zone. So let us attack that part to characterize or to correlate the wear with the fatigue rate. So that is the basic premises on which I'll be presenting the further work on this. So now, what are the factors which actually influence the fatigue? There are 2 aspects. I have got category, the material as well as the operational. Material like different rubbers, NR maybe have a different characteristics, SBR may have a different characteristics, and when you blend it, it will have a different characteristics. Then effect of filler, like if you do the testing without filler and with filler, or different types of carbon black, like 100 series, 1 series carbon black, or 2 series carbon black, or 3 series carbon black, then curing systems will have an effect, and then aging can have an effect. Just to put some of the parameters, it could be many more. And with respect to the operational, like strain can have an effect, temperature can have an effect, waveform, that type, the way you load it, that can have an influence. The R ratio, like if there is any pre-strain, that can also have an influence. So some of the things I will try to demonstrate here using those parameters. And with respect to the tire wear can have 2 types of things, like lifetime wear or irregular wear. We'll only concentrate on the lifetime wear, actually the distance that a tire travels before wearing it out. So again, just for your information, there is only this curve. If you see left side, actually there are different, like tire design, vehicle, road, and all those things are having influence. But very important is the right side part. You can see that driving condition and driver has a highest influence on tire wear. So be a responsible driver so that you can drive properly, so that you can you have a less contribution to TRWP generation. So that's the message I would like to convey. But don't ask me what is the responsible driving habit. I don't know. But I can tell you that don't put panic braking. Don't accelerate so fast like a race car or something like that. And so go at normal speed. Try to brake or see the object, what is in front of you well in advance, so that you don't have to apply the panic brake, and don't take a sharp cornering. That can have another impact, that it may topple also, which is not good for safety as well. So this can be a broad guidelines, but you see the driving condition and driver is the highest influence here. Okay, fine. Then wear rate has another thing, like if you see The wear rate could be defined as rate of wear equal to A into Fe. A is the abradability of the material and Fe is the frictional energy. Frictional energy is nothing that we talked about tearing energy for fatigue crack growth, and here we are talking about the frictional energy. So both are in energy. So when there are two energies together, we can always try to equate with each other. And the frictional energy or the abradability depends on tire material like rubber, reinforcement, edging, pavement like micro and macro texture, contaminant like water, snow, and ice, temperature of the tire, temperature of the air or temperature of the road surface, and tire construction like tread, belt stiffness, groove quiet, lug grip, or different types of rough tires. The vehicle geometry like suspension geometry, toe or camber can have an influence. Operating condition definitely will have an influence, load, impression, speed, and driver. So this is a real life thing, and in the laboratory we cannot simulate all the things together. I will try to pick some of the influencing parameter and to demonstrate using the laboratory abrasion tester how these things are influence the tire wear. Okay, so now I will try to show you that what are the different types of materials. There are 5 different types of material I have used, mainly the natural rubber and the polybutadiene rubber. These are the rubbers commonly used. Of course, SBR is also used very often, but I have just for demonstration purpose, I will only talk about the natural rubber, polybutadiene rubber, and natural and polybutadiene rubber blend. And it is all the NB and NB are loaded with 50 parts of carbon black. Other chemicals were not shown here. That's not so important here to show. And just to show the effect of filler, how it affects the specifically for the fatigue growth, that also been shown here. So that's the nomenclature I will be using in the remaining the plots and all. So if you have any doubt, you can ask me what is NG, N, or NB, or B or BG. So this is a tear fatigue analyzer. So yesterday Dr. Dasgupta talked about DMA. Today Ajay talked about RPA. So I thought that I should also have some A. So TFA is one of the equipment. And this is the tear and fatigue analyzer. So tear and fatigue analyzer actually one of the it is a very fantastic tool to understand the fatigue growth characteristics. Of course, you can also do the fatigue crack nucleation part as well. But today's discussion will be mostly concentrated on the fatigue crack growth. And the default test conditions were used like a temperature between 30 degrees centigrade, except one case where temperature variability was shown. So 70 degrees centigrade experiment was also done. And strain rate was 10% was 10% to 30% strain we have used. And this is for the pure shear specimen which is used. And these two actually the input curve, one is called the sine, the sinusoidal curve, and another is the called Gaussian parts curve. And this was done for all those materials, and I will try to show you the results how it happens. Similarly, for the wear experiment, we have used the laboratory abrasion tester, and of course, as I said, that all the conditions cannot be replicated in the laboratory environment. However, like strain, I have took the variable load like 25 Newton, 50 Newton, and 75 and 100 Newton. Newton means only for these small wheels of 84 millimeter diameter, so it can cause a stress corresponding to a tire. Similarly, I have used the variable surface temperature. We use the corundum surface, and you can heat this surface quite well, like up to different 60 degrees centigrade temperature. We have also done the study from the literature that the surface temperature in India can go as high as 65. Surface temperature, road surface temperature. Don't confuse with the ambient temperature, because the surface temperature will be much higher compared to your ambient temperature. And the variable surface roughness, like corundum 24 is the most sharp surface, and the corundum 180 is the relatively less sharp for the plant surface. And this test run matrix, which is as per one ISO standard, there is ISO standard available. Now coming to the results, that effect of rubber and rubber blend. So left hand side is the NR and PR. Actually, in this results, actually what you see that natural rubber curves are lower than the polybutadiene rubber, of course, in a certain tearing energy zone. But you just important note that the slope of the polybutadiene rubber, which is very far, stiff, and it can go down very fast. In fact, in one of our results, we have shown that up to a certain 15 or 20% results, there is a much lower crack growth rate in polybutadiene rubber. Of course, we have not captured in this plot. And the right side is the natural rubber, pure natural rubber, the same graph, and another is the natural rubber, polybutadiene rubber. And you can see that when you adding the natural butadiene rubber, and the crack growth rate is quite low there. So, which is also one of the observation here. And of course, that also depends on the tearing energy zone. But if you increase the tearing energy, then there is a reversal of ranking also happens. I am not going to present here. In fact, in my PhD, I have shown those results as well. I am just concentrated here, only the specific window here, just to show that how things are happening. Things are showing different characteristics. Now, there is a NR gum means without any filler, without any carbon black, and the field means 50 parts of carbon black. And you can see for the left hand side, sorry, for in the case of natural rubber, of course, the gum NG has a higher crack growth rate compared to the N, but the difference is not so high. However, the right side graph, there is a lot of differences you can exist in. And again, those who are from the rubber technology background, if you see that natural rubber has very good strength there, it's a tensile strength, maybe when the gum strength is about 20-25. Even if you add 50 pH of carbon black, tensile strength doesn't exist so high. However, in the case of any synthetic rubber, you put 50 pH, it will be tensile strength maybe without any filler, maybe 2 MPa or 3 MPa, it can go as high as 20 MPa. Do you know what is the reason behind it? It's a question. Polybutadiene rubber doesn't have a strain-induced crystallization. No. Natural rubber, I'm not talking about the natural rubber. Natural rubber, if you have without filler, will have a tensile strength of 20 MPa or 25 MPa. If you add 50 pH, it may be 30 MPa. So delta is 5 MPa. But SBR or BR, without any filler, it will have a tensile strength of 2 to 3 MPa maybe. Add 50 pH, it will go 20 MPa. So where it is almost 8 times higher. Why this thing happens? There is only one book actually talks about this phenomenon. Nowhere else, at least I couldn't find anywhere. Only one Russian book talks about it. They said that in the case of natural rubber, you're already having a strain-induced crystallization part and all those things. Natural strength is higher, so that's why you don't feel that reinforcement effect. But in the case of BR and SBR, in the presence of filler, Vandrysov is correct. It's a crystallization, but not strain-induced crystallization. The filler acts as a nucleus formation of a crystalline formation, and that gives the strength. And that is a fantastic effect for the SBR. You do this experiment in your laboratory, or you see the literature. In fact, one of my book chapter, I have mentioned this thing, and thanks to that book, that they have given this explanation. I didn't find it during my rubber technology courses. We found that, but never explained anywhere. So that's a thing, and which is also showing here. You can see there is a huge difference here. Don't you see? But here it is in the case of natural rubber, you don't find that kind of differences even in the absence of filler. Anyway, now the temperature, of course, the temperature effects are also shown that higher temperature has a higher crack growth rate, and of course in the NRBR blend also shown the same thing. The moment higher temperature, people start talking about the degradation, but 70 degrees centigrade is not good enough to degrade. What could be the reason behind it? Any response? Sorry, I'm taking longer time. So any response on this? Okay, I'll try to explain. Again, the viscoelasticity plays a big role. So higher hysteresis or viscoelastic loss is not always bad. It is good also for fatigue crack growth. You see, this is the crack tip. Okay, this is a crack tip taken from, this figure was taken from one of the stalwart in this field, Professor Guy Henry's paper. And there is a viscoelastic dissipation zone. What happens when you are putting some stain and all? There is a strain or the driving force here, correct, in the crack tip. And if that force can be dissipated or that energy can be dissipated through viscoelastic dissipation, then your crack will not propagate, correct? That is the thing. Now, what happens when temperature, you have seen the loss modulus with respect to the temperature or tan delta with respect to the temperature. When you increase the temperature, your tan delta or loss characteristics reduces, isn't it? Which is not good for your crack growth. And why loss modulus reduces? What could be the reason at high temperature? Because your molecular movements are much higher, and we know the viscosity is nothing. It is basically the internal resistance between different polymer chains or fillers and all. And those polymer chains, because it follows the Brownian motion at higher temperature, Brownian motion favors this movement, and because of that, your viscoelasticity part component reduces, and that's the reason actually your crack growth also reduces, not because of your degradation of the material. 70 degrees centigrade for during the testing, material is not going to degrade anyway. So that was the explanation. These are all published. One of my research article I have already published these results, and you can see this is also real result of two different materials, that how loss modulus reduces with respect to the temperature up to 70 degrees centigrade. Now next is the waveform, like whether it is a sinusoidal or it's a pulse. Of course, I believe that tire deformation is always a pulse deformation, it's not a sinusoidal. And all along we are doing it with a sinusoidal. And I proposed in my PhD thesis that sinusoidal should not be used. Of course, you can use it for certain purposes, but if you can have a facility to do the pulse, it's better to do it in the pulse. And you can see that higher the pulse, in the case of pulse, the your crack growth rate is also higher. Again, it has a root to the viscoelastic dissipation. I'll show you, I have done some finite element analysis also, part of my PhD project as well. So you can see that how the sine mode is happening, the top one, and how the pulse. And you can see that in the case of a sine, your dissipative energy at the crack tip is much higher. More energy is dissipated in the sine mode compared to your pulse mode. Because of that, that energy is not available for driving the crack. However, in the case of pulse, your dissipated energy is less because it has a relaxation time, and that's the reason actually your dissipative energy is not so high, and that's the reason actually it is having a higher crack growth rate in the case of pulse. So that was the example, because that was also one of the findings during my PhD work. And of course, I'd like to have some other explanation. The future researchers must come with new proposition, because science is nothing is absolute. What is today's finding can be challenged tomorrow, and that's the reason actually science progresses. It's a delta input. There is no breakthrough as such. So far that was the explanation we got it. Okay, fine. I think I have taken longer time. I only 3 slides. And now effect of load for this compounds, and you can see again that in a base compound having a higher severity, there are a lot of wear rate, milligram per kilometer, and you can see the picture itself. The top figure, you can see that there are a lot of cracks. The cracks are deep in sizes as well with respect to the NRBR blend. Similarly, when you do it for different surfaces, the similar behavior happens. Of course, that 24 to 60, there is a huge decrease, and 60 to 180, there is not much differences. And for temperature also shown the similar effect. So in the case of rubber, or wear nature also, you can see that NRBR blends behave quite well. Of course, in that severity zone, again, there are, whenever you talk about the wear or fatigue, you must define what is the severity zone, what is the tenuity zone. It is not that if it is good at one place, it will be good in the entire spectrum. That is not going to happen. So we have to be very, very clear. It doesn't, there is no universal truth like this. So that's the thing I'm giving the disclaimer. Okay, so finally I reach to the summary slide. So fatigue and wear behavior rubber compounds are largely dependent on type of rubber, presence of filler, and operational conditions. And NR, we have blend compounds on superior FCG and lower resistance ranking in comparison with NR compound with a given this zone where we have measured, and ranking of fatigue crack growth behavior or rubber compounds are matching with wear resistance ranking, which is good at that the steady state abrasion zone which I have shown earlier. So that's all, and thank you for your attention, and I'm gratefully acknowledge my organization for giving me permission to present my work and be part of this innovation forum, and thanks to organizer again. So I'd be happy to answer a few questions if the time permits, or maybe I'll be there for some more time. You can ask me the questions. Hope you could get some information, and I'd like to listen from you, and I would like to learn from you as well. Thank you very much. Yes. Vandri साहब थोड़ा सीधा सवाल पूछना पुराना दोस्ती है.
Normally, yeah. For the truck tire, we use normally the natural rubber.
Yes.
So can you say that the truck tire normally runs at a severe zone? That is what we have defined these 3 zones, and that's why the probably the natural rubber use the better wear resistance compared to the VR there.
Of course. We are using the nowadays the synthetic rubber also in track tires. So yes, you are right. Actually, it's not. I have not taken about the talk about the carton chip part, because carton chip is a separate phenomena and there is different equipment available. And Christopher Robertson is an authority, and Dr. Radek, they are the authority in this subject. So I think that has a different phenomena, because that is called intrinsic strength, critical tearing energy, and those things has to be understood properly. Maybe the fatigue crack growth may be part of that. Yeah.
Very interesting.
Yeah.
You classified the wear into 2 categories. What is the abrasion as a fatigue wear?
Yeah.
Take aircraft tires.
Yes.
Where the wear takes place.
Aircraft tires.
Yeah.
Okay. I think that also has a role to play for the fatigue, because when the landing, there is a lot of the fatigue cycles are happening there, and of course it is a actually aircraft tire has a different thermal. Yeah, that is a thermal runway happens.
Yeah.
Thermal runway has to be dealt in a different manner.
Yeah.
And
that's again kind of wear.
Yes.
Smearing takes place.
Smearing takes place, and Bo Pearson, he is the authority in this, and he has shown that the thermal runway is a very difficult situation to handle. Exactly. The temperature goes as high as 400 degree, 500. 800, it goes up to 800. So forget about the natural rubber, the polybutadiene rubber or the synthetic rubber can also degrade at that high temperature, and that's called a thermal runway. Right. And thermal runway and fatigue crack growth and all that time it doesn't work. Thermal runway is a it's a very critical situation, goes to a critical failure type. But only thing is that in a whatever limited understanding I am having with the aircraft tire, so what happens that when it lands, that patches actually gets all those things. So luckily that every time that patches doesn't come into picture, but when it actually they remove the tire, there is a patch goes off. I've seen it, and they retread also in some cases. So not for
the yeah. Makes some kind of lubrication between the tarmac and the tire.
Yes.
Okay, that's something like benefit out of the innovation. Coming on the abraded surface, when you look at the abraded surface, generally in the case of rubber, it forms the ridges.
Yes, ridges, ridge formation.
Ridge formation.
Yes.
There is a relationship between the wear and the
ridge. Yeah, I fully understand. And
I didn't see any kind of ridges study on the topography of the abraded surface.
Okay. Actually, ridges was not there here, but other severities ridges were there. Actually, I couldn't present the complete work because 20 minutes is too, but ridges are there. Actually, the ridges, the width between 2 ridges and the depth of the ridges actually plays a big role. Because from there, actually, the fatigue crack growth starts. That what you say that root of those ridges actually acts as a tongue, and every fatigue cycle is folding. Yeah, that's the tongue gets on. Next comes. Yeah, that's a.
One more important thing is the factor called dynamic coercion of friction.
Yes.
Yeah. If your surface is having lubrication and all your
prediction is going to be different. Yeah.
Yeah, that's
so
true.
the dynamic coefficient of friction is very important.
Yes.
If you're adding your formulation,
Yes.
it is going to alter your dynamic coefficient of friction.
Yes.
All these properties will be different.
All these properties will be different.
Yeah.
That's true.
Yeah. But do we have any factor to calculate the dynamic coefficient of friction? What is the effect of dynamic coefficient of friction? How to alter the dynamic coefficient of friction?
Yeah, the thing is that whatever I think what you say mu k, you are talking about mu k. So maybe you can factor into that what will be the mu k, generally that theoretical understanding of those mu k, because during these experiments you can have a side force coefficients, and those side force coefficients can be related with this thing. So mu s and mu k, and the severity zone can be changed according to the mu k values.
Okay, thank you.
Thank you.
Thank you very much. Thank you. It's a very good presentation. We have more questions. We're going to have lunchtime and ask him as well.
Yeah.
A small appreciation for you. Yes. Thank you very much. Actually, this subject, people are, in my online sessions or questions on this subject. That's why I want more discussion on it. Thank you very much.
Thank you for allowing more time. Sorry for others, I've taken their time.
Well, I had to apologize to the people behind you, who is going to, hey, Parent, what's going on here? Guys, what we do is this, we'll have a lunch first. I think, hungry? Yeah. I know Dr. Rajkumar, I asked him next presentation as a Raj Ganesh, and then I asked him after lunch have the presentation. Okay, so let's have a lunch, 35 minutes. Okay, short lunch. Okay, and come back again here. Thank you very much. Oh yeah, so that, yeah, I said that.
But actually, because the size was big. Because the size was big, I had to send through a OneDrive link, but I have given the edit option also so that you can download.
Let's see.
So
okay, ask you for an email.
Maybe yeah, you can put the email.
So that I don't use the
in the same classroom here on here.
Yeah, here. Okay. Basically, I need to finish the keynote, and
again there will
the breaks. Yeah. After lunch, we're going to be keynote. Yeah. Seven.
Do you have received any other email?
No.
But you have received the code?
Okay.
Let us see if it happens.
748-097.
You can copy paste me. 748-09787. Yeah, very good.
Okay.
You can download possible, maybe that is okay, because this is again through online. Maybe save us. File save us.
Why is coming like this, man? Crazy.
File save. Yeah. Download a copy. Yeah. Because this online something goes off, that becomes. But later you can delete.
No, yeah, you mentioned that email that you don't want to circulate this one. Yeah,
yeah.
So it's over. And the session will be delayed today.
Yeah, I understood.
Okay?
Yeah, I understood. I prefer you kept little early for me, but anyway, I'm there tonight here.
I want everybody work first day only.
No. I'm there till the end of the day, but I want some speaker also to be there. Okay.
Sure. You see, we have the online audience. I also this session. I want this record is going to be in my library. Library is accessible to only for the members.
Okay. Okay.
It's not for public. So basically members. So
no, here, okay, maybe I do not know. Then online may work. I just as safety, I gave the edit option also because I never use this sharing the OneDrive. Anyway, at least you got it. The sizes are big. Okay, thank you. So it is there. Huh?
Yeah, just a second. Let me. You are in this room, right?
Day one. No, room one. Sorry, day 2, room 1. Post lunch.
Just there. Okay.
Makes sense.
Okay, I know. Yeah, I understand. Yeah, let me go to the.
Okay.
Yeah, thanks, man. Thank you.
Such a nice person. So started. Nobody will do that.
Yeah, afternoon sessions. First, we go in the keynote. Okay, with the next Mr. Kamlesh Jain give a keynote. Okay.
You can see the name of the
Yeah.
Yeah, today I'm a little messy, man.
Video also is there. You need to copy the entire folder.
Sure. How do you feel so far? Is okay?
Yeah, it's okay. Otherwise, you can present on the pen drive itself.
Okay, let's.
Yeah. First run it and then see.
That is
Forum 2024. Yeah.
all.
No, yeah, start the innovation. Yeah. Particularly go to video. See. Two, 3 slides just come down. Yeah.
You are leaving today or tomorrow?
Today, tonight, I am late at 9 o'clock. I am
Okay, still have time.
Yeah. Yeah, play this. Yes.
Okay. No sound, right? Yeah.
Sound I suppressed it, yeah.
Okay, that's fine.
Sound is not good.
What only one video?
Yeah, I have a lot of videos. Go down further. Yeah. Okay, next. Yeah. Yes. Volume can be reduced. It's not.
They should feel a little bit what's factory sound look like.
No, after lunch they should sleep.
Yeah,
I think we must increase the volume.
True. Put in the rock sound.
Yeah. Will create a noise and disturb the other.
Yeah.
That's good. Yeah. Okay, that's
all good. Yeah. Okay. I think I put in my because we have many files. Let me take a whole file, man. Okay.
Need to transfer the folder.
Which one? Whole?
Which one? Yeah, because videos are. Yeah. Either you have to play from the pen drive, or you need to copy the all videos also. Backup file is required. Otherwise, video will not play.
I can keep as a stock in mind. It's okay.
Okay.
Yeah. So let me take it. So it's also in my library. So. It's a whole folder.
Is there any presentation? Or after lunch, my presentation is there.
No, that guy.
There's one more.
Okay. Yeah. First keynote.
Yeah.
Then Raj Ganesh. Then you. Okay. So. Yeah. Yeah. Today, 2 minutes slots today. That's makes it complicated. So.
Play and then see videos playing. Otherwise,
yeah. Whatever.
You copy the folder, no? Yeah.
Okay. Yeah. Which one is it? 2?
No, NRC leave it. Okay. NRC you can delete.
So that I'm not confused.
I slightly changed the title because the Pandian presenter has something. That's right.
I'm sure he's definitely sitting in this process.
Yeah. They told me.
Are you doing any? You're involved with the EP any days nowadays? No.
He's doing
so you guys meeting each other? Yeah.
He's staying very close to me only. Hardly 5 kilometers. 5 kilometers. Yes. You can take out the pen drive.
That's very good. Yeah. Okay, it's all out. No, not. Close. Sure. Okay, what is the
so lunch हो गया lunch break. না না এটা অফ করছে এদিকে নিয়ে গিয়ে রাখো.
Okay. So what is the best?
पेन पेपर है মনে করে স্লাইড চেঞ্জার এগুলো কিন্তু ভুলবে
And maybe नहीं हमारा plan है कि exhibition, small scale exhibition. It's like just a first experience. Right? It's painting. Honestly, better. Right? It's the standing. Some mistakes. Looks odd. फोटो नहीं भेजे और क्या होता है इससे पता नहीं ऐसा करता सकता है लेकिन next time they invite me when I have email, right? आप suggest कर सकते हैं ये ऐसा नहीं चर्चा ना होगा Actually, I have a big back house. I can carry it. I have many in my office. Transport and I will push it.
सॉफ्टवेयर यहाँ पर कुछ पड़ा है ना वो पुराना है और वो ऑफिस में है दिल्ली में तो वो आज
आपको ये बहुत महंगा है इसके तो मिल जाएगा तो एडजस्ट कर दो ओके 5% लेस करके देखना था ना उसी का टोटल ओके 1% बिफोर जीएसटी हां बिफोर हां जितना है आपको आपको मिलता है next meet, please take it. Thank you. Why organize both gel and international? I say, five thousand.
और अपना हिस्ट्री
Asha, I sent a message to you just now that the amount to pay to the radiant. For the decoration. 78 by 78. And I need you to send me the complete address and GST number in the WhatsApp message and forward to you to make a GST for us here. Okay, send once translate that, send me the message. And you put in the question that innovation forum decoration. Yeah, very good. Okay, yeah.
Okay, very good. Good, very interesting today. So when are we seeing you in Delhi? Soon? Let's see. No, so you travel quite a lot. So it's not just that you are in Ireland all the time.
Next weekend,
Malaysia must be quite a lot. All of them.
I do have an event in Sri Lanka.
So where are you from?
I moved by 25 years ago.
Technology you started how long? That's a long time. So you practically just worked 6 years when you moved from there and then started.
Yeah.
So what all do you do in technology? It's just these kind of programs?
So we have exhibitions. If you want to promote your this kind of business, strategy and how you get market, what is trending. So we have like a clear process. events of course, so we have a wonderful resources. One single tool is resources. All in one context. So what we do, well, it's very difficult to do. We then an association. Because you need to walk in a very thin line. I have a wall, but I'm not able to. What does it mean? Association, association. Roger, I will take you in.
Yeah, thanks to you as well. Thank you. Nice question. Yeah, it was a very nice interaction with all of you. I really enjoyed it.
It's also, we have more time to listen.
Yeah, sure.
Thank you very much, sir. Thank you. Thank you, sir. So if you are wanting to splice.
Yeah, I will flight at 4:50.
Okay, you're not that heavy like cycle there.
I just met Yusuf and other.
Okay, you met them already? Okay.
No, I.
Oh, still, yeah, they're not finished yet.
I'm not sure because I was having that. So,
okay. Check it out.
Okay. Have a nice day, sir. And hey,
okay,
yeah.
All done? Finish lunch? Yes. How was the program for you so far? Yes, yes. Police across here. That's good. That's good. We're staying for about 1 minute. Again. Yes, yes. It's a growing market in Southeast Asia. Well, there's hospital is a factory. So for you, for quality, not just performance. Quality you have to proceed. You can't no compromise on that. Price can't compete with your own market. You always have something for cheap. Cost of quality. So you always not everybody is. Nobody compromises on the quality of their own products. But the cost is okay. Thank you.
ये just करो या ना ये 16 by 9 कर सकते हैं ना 16 by 9
16 by 9 हम करते हैं
strength is 4 by 8 square this way.
शुरू हो जाता है
How are you? You're in Delhi after a long time.
Yeah. Let me help Rakesh plate. I'll come back in a minute. Okay.
Right.
मैं आपसे ग्रीन हम पे दिखेगी तो पहले ही ले लें
Yeah. Okay. So this is okay. This are slides. Yeah. This is the correct one, right?
Yeah.
Let's leave that one. Okay, I'll come back. Okay.
No problem.
So maybe another 10 more minutes. Yeah.
No problem. I'm going to just browse through the slides. And I have my notes. I can talk on the notes.
Just go with the flow. 20 plus minutes.
What I cover in 15 also, I can only save 10.
So that's why it's supposed to be 30. Let's make it 23. How are you doing, guys? How are you doing? Good. Yeah. Food is okay. Only thing, the time is a problem here today, is it? Are you all right with that? Yeah, sorry, we have a little issues with the time management today because the 2 rooms, same time. So we need to work on us a little bit on this issue. But I'm sure that you find some topics are interesting to you all. Okay. So we are on the last stretch of today. I mean, this whole Rubber Innovation Forum. How many of you participated in my rubber quiz? Did anybody finish rubber quiz? Okay, Barak, my fantastic man. Please meet me before you leave. Okay. Anybody else? Try rubber quiz. It's a good learning. If you don't know, you know this book. We have booklet, right? There is a QR code. Scan it. You still have a time. You can do by up to tomorrow. 30 actually up to tomorrow evening. Or you can work with your staff or together answer it. Yeah. Milinji, ask your staff to work on it. Okay. It will be good refreshing. Okay. Not all questions are from the presentation. Some are general questions as well. And it will be useful. See, knowledge, having in degrees, having experience is one thing. Knowledge at the fingertips is another thing. Whether you have a knowledge at the time you need, how to do that one is having exercise like this once in a while. Yeah, it is not about the how much you get score. It's a process of this is one learning process. I'm very much into try to put your knowledge at your fingertips through the activities of Technobase. Okay, without further delay, we still have many presentations. Kinsuk has a long list there waiting in there to finish his. My room has more. Okay, so let's do the keynote speech of this Rubber Innovation Forum, the 4th keynote speech. It's a very important subject. As we talk about innovations, is all about the research development, how you connect with the industry activities. So I have invited Mr. Kamlesh Jain. I think all of you know who is he, Mr. Kamlesh Jain, and his journey he's a managing director of the Whole Well. He has many companies. He does a lot of activity. Personally, he is one of my benchmark to follow in terms of thinking process. The ways he does things. Is a leader, a rubber industry leader, actually involved with the All India Rubber Industries Association. I'm going to invite him to give a talk on the industry perspective on current rubber research in academic and research organizations, opportunities and challenges. This is a presentation for research people to look at it, how we can integrate industry requirements and the research expectations from the industry point of view. So without further delay, let's join me to welcome Mr. Kamlesh Jain. We already finished our lunch. Hello, sir.
Thank you so much, Piram. Good afternoon, Dr. Kinsuk Naskar, Piram, Dr. Kanika, fellow speakers and researchers. I believe most of the subjects has been already touched, so I have nothing much to add, but still I would like you people to walk through since all the topics has been covered quickly. So we must know what is the link between the two, the expectation of the industry and what the researchers are looking at. Why are they doing the research? Who are their potential partners? It's not working. So we need to understand the market at a large. The global market of rubber industry is around 46.95 billion in 2023. Indian market is 18.27. Natural rubber, fourth largest producer. Indian market 18.27. Again, trend is towards sustainability and industry 4. So evolution and innovation in rubber technology, we have discussed among various things, advanced materials, Why advanced materials? Because that's the need of the hours. Sustainability, new materials coming in. So we need to introduce ourselves to advanced materials. I believe a lot of presentation has been given also. Then nanotechnology, how you are going to the smallest particle level to modify the property of a particular rubber. Then smart rubber, everything is becoming smart. So with smart rubber coming in, medical devices, tires, everything can be taken. The inputs can be taken and you can improvise on that. Again, manufacturing, automated production, improved efficiency, reduce waste. 3D printing is another dimension which has come up. And sustainability goes without saying that we cannot ignore the environment in today's time, because we have seen that we have bought in materials which have affected the health of the people, the environment. Now we are trying to go on the correction course, but that will take its time, but our commitment should be there. So Industry 4, probably today, Mr. Mandal, he spoke about Industry 5. So we have to go one step further. We have to be in the futuristic. Why we just follow what's currently there? We have to enter into tomorrow. Real-time monitoring, because the last stop is now old. We have to catch the current, real-time. Process control at every point of time. We have to look into process control. And energy efficient. Everything is energy driven. So energy is part of your cost also, and efficiency. So we need to understand that. So opportunities in rubber innovation. So how many of are you from the industries? Please raise your hand. Quite a few. Lovely. And how many of you are from research area? Okay. So let's have a quick 5 minutes interaction. So Mr. Pankaj, I would like to know from you, what is your expectation from the researchers?
Sir, my expectation is that research does not, unless it comes to industry, it's not going to get quantified, it's not going to get converted. And like we've heard over the last 2 days, if we are late, then we miss the bus. So we need to buck up. The interaction has to increase and ideas have to travel fast. Otherwise, it's going to be very difficult. All the hard work that all the researchers put in will be lost. My expectation is very simple. Drive at pace 5.
Right. Very true. Right. Very true. I would request Mr. Duggar, who is also an industrialist, he is also chairman Eastern Region, IRA, to present his perspective.
In fact, I was discussing with some people yesterday evening itself that a lot of researches are being happening, but what we lack is the collab between the industry and the research. Whatever research happens, most of them, what I have found is that they remain on the paper or white paper. So until and unless there is a commercial feasibility done and it is transferred thereon, so that it could be put to actual commercial production and customer benefit and users. That is where we lack the linkage. So if there could be some agency who could take care of this part, I mean, it is a win-win situation. That agency will also have ample of scope, and we as an industry as well as the researchers. So it will be a complete cycle.
Very true. Now I would like the perspective of Mr. Mandal, what he expects from the industry.
I think mindset should be very open, rather than a fixed mindset. It should be growth mindset that the industry should also adapt a bit. I know I might sound really weird, but you have to move out of the traditional things. World is moving very fast. I think in that case, you need to come up with new and that adaptability. You have to take risks. Not take, I mean, it could be a 70-30, 70 could be a regular business and 30 could be on this incubating a new type of thing and taking risks. I mean, if you have that risk-taking capability, then you can catch the bus. You will not miss the bus. That's what I feel.
Right. I would ask Dr. Kinsuk Naskar to give his perspective on this.
Yeah, I agree with that. And some of the comments from my side are as follows. What I noticed during my study in Europe is that there is a very strong consortium which is formed by the industry as well as there are industrial partners as well as academic partners. So it's not only about India. I think most of the Asia Pacific countries are very strong in rubber research. So I'm thinking one step further. So also involving Anika and other colleagues of our from Malaysia or colleagues of our colleagues from Japan, thinking about an Asian kind of consortium of research where industry partners as well as institutes will be there. And there has to be some mechanism for funding the projects. And those objectives of those projects should come from the industry. This means that we are not solving our problems. We are solving their problems through the PhD students, whoever is joining in that project. So that is my perception for future as well. And I would say that maybe this is one of the forums which is, and in my opinion, a bit different than conventional rubber, short-term courses or other conferences. Maybe this is the beginning already.
Right. Thank you. So now we have one person who is a blend of two. I will ask Dr. Tabamani to say something about this.
I won't say. Yeah, thank you, Mr. Kamlesh and Prem, for giving me the opportunity to share my views. I've been on both sides of the wall. Okay, I've been leading the research institute. I've been with the industry for more than 30 years. What I've seen over a period of time is the academics too much focus on the new concepts and developing new materials with the view to compete with the developed nations. Their performance is measured in terms of number of papers published, number of articles written. Okay, but the industry challenges are quite different. When the researchers or even the master students, after completing their course, when they join industries, they find it extremely difficult to survive. They find it difficult to software and other industries. Okay, unfortunately, these guys, when they go to industries, the problem what they're facing in the shop floor is quite different. It's a really challenging. They don't get the solution. So industry guys, they feel like IIT is producing people, knowledgeable guys who cannot provide a solution to their problems. Okay, so for that, they think that experienced workman, a supervisor will be a better choice than taking a person IIT installer. Okay, that's why we need to bridge the gap between the research priorities and the industry challenges. I've seen in China, I've traveled extensively also, even during their schooling itself, they have to the industry. Okay, but somewhere our academic and the industries are going parallel to each other, like a railway track. Okay. Sorry?
The link is missing.
Yeah, the gap is okay. The gap is always there. Okay, though we went to industries, but we, in my batch and other things, like Chandra, myself, Mukubali and all, we had a different approach. When we went to industries, really I faced the things. Probably we take 2 minutes extra. I was the top back from IT Kharagpur when we went to industries. We had very experienced people. Basically, they were chemists, not a technologist. They used to keep all the software. Those days, collaborating. The technology input came from their collaborators. They used to keep all the things in their pocket. They used to give instructions. They were doing it. But when we joined there, really it was a tough task for us. We have fundamental knowledge, but we are not allowed to work. Because those guys, they were controlling it. They thought that when we go and interview with them, they will lose their importance. But this did not last long. Company many places went down to trouble, or they were not able to face the market requirements. That was a change. Particularly when better, I tell you, the company was lost, Company declared this thing, voluntary retirement. They got rid of all the old guys. Then we stepped in. We showed ourselves. We worked very, very hard. More than 12 hours, 13 hours every day. We brought the company and we all through the time. Really, it was a challenge. The experience is quite different. Most of the industries, qualified people are there as a technologists. They are people to support them. Okay. But the next generation, they are also must ready to work hard and gain the experience. Unfortunately, rubber technology is the one thing which by reading itself you have to pick up. You need to put your hands, pick up your experience, then only you will be able to solve industrial problems. Otherwise, I can propose a project, 3 projects. Okay, I can put in the paper, which is not really going to solve industrial problems. The problems are quite different. Okay, that's the point I want to share.
Very nice view. I believe we have all the perspective over here. So what I understand is the only problem is one, which lies here. That's the mindset. The industry requires researches. The researches require the industry. Now somewhere something is blocking. So we need to work. How can we take out this difference? So industry will invest in anything where they can monetize. So making a statement that they should invest, so they should learn economics. Without economics, nothing works. Even the government has changed its stand. No more government funding till it is self-sustainable. I believe most of you must be knowing. So this is one part we need to understand. And there has to be some point of interaction. The rail cannot run parallel. So we should put in, maybe it may not happen in one go, but we should try in a small way and see where are the blockages and how can we take that out. So there is a saying in Hindi, आवश्यकता आविष्कार की जननी है. Necessity is the mother of invention, and we are in an era where necessity is never ending. So we are in a forum of innovation, and the amount of papers that has happened, it looks like I'm again studying A, B, C, D, E. I need to learn sentences, and then I need to learn a lot more. So regarding various developments, people need to identify what development is needed for their own industry application, and researchers should identify companies where they can contribute, and they should interact with them without hesitation. I think that will make more sense, and even if it does not work out, does not matter. At least you'll go to the next step. What's happening? With the environment part, now I see in various forum bio-based, lot of materials are coming in. It is bound to come. You don't have a choice. Since environment is of prime importance, it is bound to. So we need to understand those people who are doing plenty of research on this. How can you make that applicable to your industry, and how even your customers, like we in industry, we need to educate our customers that sir, aane wale time ke andar mein, in the coming times, you have to switch over to biomaterials. It may be costly to you, but ultimately being costly to the society is much more costlier than being costly to you. Technology is going at transformation at a speed unbeatable. So we all have to be quick learners. We need to understand what technology is doing and how it is going to affect one day to you. I'll share a very quick example. China started making batteries, pencil battery at 1 rupee. Okay, the Indian battery market could not sustain. Eveready and all those companies got closed because 1 rupee battery, maybe it may be leaking also, does not matter. It was affordable for the mass, and the battery unit closed down. Indian industry. So ultimately, what is happening is an external force has closed down your business out here. By the time they realize that, okay, the battery is not only 1 rupee, but it is spoiling the equipment worth more than hundreds of battery till that time. So technology from outside, how it's going to kill you, you don't know. I was doing some research on China. They have a cost leadership of 50 years ahead. How will they remain ahead at 50 years? So we have to have a longer vision to understand how are we going to sustain. We have already discussed that collaboration has to be imperative. We start small, but we have to work together. The industry has to work among themselves with the academia, and as Professor Kinsuk said, it has to be inter-country also. No point reinventing the wheel. The research has been done by somebody else. Use that. Use your energy in something, either value adding on that research or doing something new. We have to create ecosystems, taking smaller steps, as Mr. Mukherjee said yesterday, and quality is no choice. In today's time, you have to guarantee quality by doing all kinds of tests. There is no shortcut to that. If you want to remain, people are now very smart. They have complete equipments to check whether you are giving the right quality or not. So if your perspective is right, I believe you will be able to go long run. So I had the opportunity to go to Thailand with Technobis to visit Hatay, Dr. Kanika's place. And I was surprised to see the ecosystem over there they have created. They have a university, the place for innovation. Yes, Prince of Sankla University. My God. Actually, I had gone in Thailand because they were the leaders in natural rubber. And I have a tendency to follow the leaders. So I thought, let me go and see what they are doing. That was the idea. Wonderful. What testing facility, how transparent they are to show. No hide and seek. In fact, one of the person I would like to mention, Dr. Boontham. Dr. Boontham. So since I was there, so I wanted to make best use. So I wrote an email at 3 a.m. to a company who was making mattress, one of the leading companies. Dr. Boontham, he came, he was a keynote speaker. I went to him. In fact, he had some kind of reservation regarding India because trade is not happening properly. I went to him, sir, I am from India. I want to do something in latex. Please tell me. So he laughed at me. Okay, we will talk. And I told Piram, I want to see his plant. Well, he'll not allow. And I got hold of him. I want to go and see, sir. And we went over there. He showed me everything in his plant. He has made a mattress which is patented and which can help you where you will not have bed sores. So we lie down on the mattress and he had an electronic simulation, everything, and he showed how things are there. In fact, he gifted me one, which I bought from Thailand for my mother. But my daughter slept on that and she's not ready to get out of that. I'm going to. I'm making a new flat. I'm going to buy more. So what I'm saying is there is so many things to learn. So whoever the leaders are, we should follow them. There are a lot of testing facility we don't have in India. So it's important that we do matchmaking, research versus industry. We are having bridge. The gurus are there, the intermediaries are there. Ask the industry what you want. Don't create a situation where I want to eat orange and you will offer apple. This is the mismatch. So again, I will come with an example. So there is an accounts interview going on. So this gentleman asks the first person, how much is 2 plus 2? He says 4. Well, you are not selected, go out. Then the next person comes. Well, how much is 3 plus 1? He says 4. Well, you are not selected, go out. Then again one person comes. He asks him, how many is 2 plus 2? Well, 4. Well, you are also not selected. Then a mid-aged person around 45, he comes. He asks, how much is 2 plus 2? So he asks, how much you want? Well, you come. So this is the thing we need to understand. I would not say that whatever research you are done is meaningless, but our mind has to be free. It's all about psychology. Don't block your mind, be open. You can do whatever you want. We have big projects which the big industry can afford. They have got big pockets, but you should not ignore, if you really want to see the change, the MSME and tiny units are the places where you can make that your incubation center. You don't need to invest money. You can protect yourself, that you can learn through mentors, that this is the way we can protect ourselves, our knowledge or whatever patent is not misused by anybody else. But I think so that's the way out. So that is all. If there is any question.
You would like to add any points?
Apart from the industry and the academic institutes, the big boss, government has to play a key role. Yeah, as you said, we get the battery. When I was in IRMRA, government came to me, they said, in the Bombay, Maharashtra, all latex industries at the base of Dalu, they closed the factory. They started importing the latex products from China. They stopped the factory. Then the joint secretary told me to go and investigate. I called the industry association and discussed with them. They said there's a 70% import duty on the latex. The latex produced in India is not good enough. They want to import from Thailand and Malaysia, there will be a huge duty. At the same time, when they import balloon, it's hardly 4% or 5%. There's the inverted duty stick. Because of that, the latex industry was completely killed. I went back to the secretary and said, because of this skill, they said, I'm making the import duty on the balloon also. I came back to the same answer. I said, okay, how much money to increase the import duty on the balloon so that the cost will go? He said, don't do that. Our line, whatever training you are doing, that also be closed.
Very true.
See the difference in policy. Okay, because of that, today the balloons are still imported from China. We are supporting indirectly in the employment level. So when we again went back to the secretary, I said, no, we need to reduce the import duty on the latex. We should not increase the import duty on the balloon. But they said there are 90 MPs from Kerala.
Ah.
They have a key role to play in the parliament.
Right.
I can't change the import duty on the latex. Okay. So beyond all this, there is another one big thing which I think over a period of time the people must understand and then take appropriate.
I visited the Latex Association in Thailand, and it was not a very warm welcome. No, they were not wrong at their part. I'm just mentioning this because our government has put restriction on import of latex. They want to do so. As you mentioned, there are 90 MPs from Kerala. Yes. And how many farmers, I don't know. But still there is scarcity. The prices have skyrocketed right now. So there has to be some way out, maybe a small quota where that is there so that we work together. We cannot put in borders over that. This is my take, but government is super boss, as you told. Yeah, you have some questions.
I had a small take on it. I'm too small a player to actually comment over here, but the MSME, so there's number will be tire and the non-tire. In the non-tire, you can see a lot of MSME. Biggest challenge in MSME is what I have seen is the focus on cleanliness is very minimal. So if we want people, good people to work in our factories, you cannot have a shabby factory. And you cannot say this, we cannot have this attitude. First of all, that attitude has to change with the MSMEs themselves. You have to invest to that extent at least that you have a pollution-free factory. That's also a big challenge when you are dealing with a lot of carbon. For the MSMEs, we are working with leaders and not the intermediates. So then that is a challenge. So maybe industry, manufacturers have to work more on that as well. But that's again a mindset issue.
Absolutely.
I have different
Yes, sir.
Yeah.
He is the most experienced person.
My question is, it is a challenge for the technologists to go on that, take over the company. I will make the company to make a much more profit within a short period. The profit will be sufficient to reinvest in the company to bring the changes in that. That should be a challenge for the technology.
Right.
That should be the strength. You must expect a small entrepreneur to spend money and you cannot believe it for money. The technologists must make drastic changes, make improvements, see that the entrepreneurs make profit and then going back to profit into the company. That should be the challenge. That should be the spirit of the technology.
I would like everybody to give a thank you.
Okay, I need to wrap it up here. Otherwise, we'll be going home 7 o'clock. Yeah. So, Kamalji, thank you very much for hosting this session today. It's a really wonderful. Once more time for you. So the appreciation. May I ask Kanika to come forward and give that? Yes. It's a wonderful discussion. And the idea is a synergy between industry and research. Yeah.
Thank you.
Thank you very much.
What shall we do? We check in later.
Thank you very much. Thank you. Thank you.
Welcome to Thailand. Congratulations.
Thank you very much. Okay, now we are going to choose the rooms, which room you want to be. Okay, so we continue the presentations. Yeah, Kinsuk, you are going to take over your room and I take over my room. Yeah. Guys, I know we have a bit long delay with today also. Please bear with me. We'll catch up. Yeah. So the next presentation in this room will be on the by Dr. Raj Kumar or Raj Ganesh. I'm got a little bit confused with the Raj Kumar and Raj Ganesh. Yeah. Very important topic for everyone to have this good presentation on the lab issues. It's still in the morning, right? Sorry, man. Okay. Okay, next speaker is Dr. Raj Ganesh, is the Field Application Service Manager from the TA Instruments. Is well experienced in the rubber testing, rheology. He graduated from the Austria, right, University of Lyon, and I have hosted him many times for his training programs by Technobase. Well received, highly knowledgeable. So it's all yours now, talking about the setting of the rubber testing laboratory and the lab data management, good practices for the business excellence. It's all yours now. You have exactly 20 minutes.
Oh, yes.
Okay, thank you.
Okay, thank you, Prem. Very good afternoon, everyone. As the Prem explained to you that the topic of today's discussion is about setting up the testing laboratories and lab data management for the good practices for the rubber business excellence. So when you talk about polymer testings or material characterization, it's a vast science. It's a vast subject. There are a lot of characterization types. There are a lot of testings. But my focus is more about, how you can, if you come to today, different sectors of, rubber industries, like tire industries, non-tire industries. As one of the participants was talking about, small and medium scale industries. So they want to know a lot of informations, how we can set up a lab, what should be their priorities, because lab means it is going to be the investment, right? So there should be a fruitful investment. It's not like, they have provision to buy all the equipments. So how they can invest and how they get the maximum out of their laboratories. So that's going to be the topic of this. As I said, 20 minutes is a very short time. It's a vast subject, but I try to bring it up the comprehensive solution so that you can get what best out of this. So before getting to the topic, let me quickly give the introduction about TA Instruments. I'm coming from. So TA is part of Waters Corporations. We are the one of the leading material characterization providers. We have got a lot of thermal and thermophysical, mechanical instrumentation techniques, starting from thermal analysis, rheology, thermophysical properties. Means we do have instruments which can help you to measure thermal conductivity, thermal diffusivity, and also measure the expansions, shrinkage behavior. Microcalorimetry, this is another product group. This is also part of thermal analysis, but that find applications in life sciences. Last about some physical testings. These are like a mechanical load frames where help you to do the durability tests like mechanical testings. So with this, actually we are catering and touch upon every aspect of material, not only limited to rubber. We are touching about thermoplastics, engineerings. So these days, the recent times, we are actually focusing very much on the advanced materials. Sustainability is one of the key aspects of it. And the second most important, end market segment is about battery, because I've seen the previous, discussion also, we spoke about batteries. There are a lot of innovation happening on the battery sides, electronics, portable electronics. So we are providing a lot of characterization solution for the material selections, because material selection is one of the very critical aspects when it comes to the battery, design. And then we also have life science, where we are catering into pharmaceuticals, biosimilars, which is a new segment that is also coming up. And we are also into the automotives, energy industries, cosmetics, personal care industries also. So we have got almost 5 manufacturing plants across the world. Most of them, so actually we are headquarters in the US, so we are US based companies. Our headquarters is located in Newcastle, Delaware State. And then we have almost 4 manufacturing plants in US, 1 in Germany, which is at Hull-Host. And then we have a direct operation almost in 23 countries. India is one among that. And India is actually looking after the business in the SAARC nations. And as I mentioned here, we have got more than 25,000 instruments, which is all used by material technologies across the world. Okay, and many of our instruments, user definitely would prefer to go for the TA make products. So with that, I'll coming back to again the topics of today's discussions. As I said, testings of polymers or setting up a lab is a vast. Okay. And I know any testing labs would definitely go for a basic physical characterization techniques, like they will measure the hardness, specific gravity, density, tensile strength. But that is not going to, meet the current requirement. If you remember one of the speech of, Hall of Fame, Rubber World Hall of Fame acceptance, Dr. Ghosh, who is the recipient of the Hall of Fame, he stressed upon one of the things like, quality, quality, quality. That's a one mantra. So how are we going to achieve that quality? So what is the way to achieve the quality? And that's where the investment is good for the lab. And you should also select the right equipments. That is the first things. So you should have the idea what you are going to invest and what you are going to buy and what you are getting out of that, because it's going to be an investment. I can clearly understand people would be reluctant to spend, unlike they are spending like a production equipments, because in production equipments it's mandatory, it's giving to your products to you, produce the products, so you look for. But I don't see the similar type of importance not being given to the equipments. Okay, but today's topic, I'm going to give you what are the things like, especially in thermal, rheology, and mechanical testings. What are the available options you have? What you get better, and what is the problem you can solve out of this analytical instrumentation techniques, and how you can maximize the capabilities, because there are a lot of capabilities which most of the user, even I've seen in a because R&D also, they don't know. They use DMA just for a single studies, but DMA can do more other studies as well, address your real world problems. So that is what my idea here. So coming to the lab requirements, I categorically classify into 3 domains. One of the things is like qualifying the material and controlling the quality of your materials. This is the major things, because when you are coming, that's the first stage of your workflow in any rubber or polymer industries. You need to select the right materials, meeting your specifications. But how are you going to test whether I'm selecting a right material? You may get the material at the cheaper price, the same specifications, at a higher price from good suppliers also. How are you to compare that? So that is what something you have to do, which is respect to the quantification and qualification of material. And second thing is, the same lab can also address your processing related issues. Many times people may not aware how to utilize these equipment to address the process related equipments. Like you may have a challenges with the extruder. Okay, you are having a difficulties in facing the mixing part. So even those kind of things also can be addressed by these analytical equipments. And the last is product development. So it could be an early stage of product development where you want to select the right material to design that product to meet your end use requirement, or it even if in case of productions, okay, am I producing the right product which is meeting the desired level of properties requirement for the end use condition, that also you can study. So what I'm saying at top is the various aspects that you are going to study at every stage of this thing. Let's start with the quantification and qualification. So if you see this, these are the possible questions you may come across. So you are a new players, you have materials. As I said, I give an example. I'm selecting a right materials. So once you selected the materials, most probably the OEM might qualify the materials and they given a correct specifications. So your target is select those material. And then you streamline the process also based on the material. Okay. But if in case there is a variability in your incoming material, how I'm going to check this variability? Because if there is a variation in the material, if there is inconsistency in the supply material, obviously the characteristics of that material is going to be different. Even you might face the challenges at the time of processing. I hope everyone agree. Okay, so if you are facing such problem, it is going to stop your production run. For example, I give an example of a die swelling. Die swelling is a common problems in cases like extrusion, profiling, extrusion things. So if you are saying, okay, I'm making some swelling issue, and that is not going to meet my dimensional requirement, you have to stop the productions. Okay, because you have already, your process engineer has designed your parameters, what is the test conditions. But very often, if you look at that, it's actually coming from the original raw material. So how I'm going to check that? So that is what the first part of the question. So whenever you come across such questions, whether I produce the right material, even if it's coming from the rubber side, so rubber is a mixed component, I'm keeping the consistency in the mixing quality. That's the second aspect of it. And then presence of any contaminations. Today we are talking about sustainabilities. So we are trying to introduce more of recycled material, but whether that is really actively improve the properties or it deteriorate the properties, that is also need to study. So those kind of things which is mainly coming from the qualification and quantification of material. And second thing is about the process optimization. How you can utilize this equipment, like addressing this kind of questions. Can we maintain a product quality during the processing? Is my processing conditions are good enough for the material? Like sometimes you may change the thermal degradations or decomposition at time of processing. So that need to be addressed. So you can make use of these analytical equipment to address those issues. And detect stability issues, additive impacts. You may have something like, processing oils which comes out of the material compound that will create a different surface effect. Means if you are looking at the surface of things, you may have an impact on that. That can be addressed by the instrumentation techniques. Coming to product performance, we can say whether the performance criteria has been met by the selected samples. How to predict the mechanical performance. Like if you talk about in the morning session before lunch, or we were talking about fatigue behavior. If you look at 10, 15 years back, people only do a mechanical testing, means it's tensile test. They don't know much more than that. But today we all understand the importance of durability studies. Like we are not just doing a monotonic failure test, but what we are focusing more is that durability aspects. When I'm subjecting the material to the mechanical cycling, so how the material is going to behave. So that is something that's very important. So we have to do such sort of studies. And again, there is the analytical instrumentation solution to meet such requirements. So coming here, so why we are talking about is the first thing is about validations of the materials, which is the main first workflow of your things. I mean, in the processing side. So the specification is important. If I see here, these are the three things, reason why we are doing it. Product performance could suffer, resulting in rejected or return material cost is a loss for you. Okay, so you need to control this. Another thing is operational efficiency, because once you start the production unit, you heat it up and you are spending the energy. And if you are facing any challenges, you have to shut down your production, which is going to be a energy loss, money loss. Okay, that need to be improved in the beginning. Means the early stage you need to identify that, and the product returns and lost time on manufacturing line impact the financial situation of the business. So these are the key reasons why people want to have that specification, and there should be a clear check gates. With that, you have to do the check. So here, like when I'm talking about, as I said, my focus today is more of how these kind of situation can be handled by instrumentation like thermal analysis, rheology. I mean, I'm talking about rheometers, rubber rheometers, and last, it's about mechanical instruments, and also important is the software management, because end of the day, data is one of the resources you have. So you should have the data, and data should be able to predict the how far the materials been performed and what are the challenges you face. So that data integrity should be there. So that is again coming from the software. So here let's talk about some of the key things. I'm not getting into the depth of it, but if you see, one of the key thermal analysis techniques as far as polymer is concerned is thermogravimetric analysis, or TGA. So here what we are doing, getting out of it, is we are actually measuring the change in weight of your sample against temperature. So typically, if you see that this is the thermograms that you are getting, you see the exact temperature and weight, and then you can see the initial weight as we accounted 100%, and then you see as we heat the samples, the material undergo decomposition. So this is actually kind of it's actually a rubber compound, tire compound material, and you can clearly see the volatiles like low temperature, high temperature oils, which has got evaporators, which account to 6% here. And then there is a polymer, and you can see here when I looked at the derivative peaks, I could see clear two peaks. So it clearly says that it's a blend of two materials, right? So then here is the place where I switch the gases. You see, up to now 600 degrees centigrade, I run it in inert atmosphere, then I change the gas to oxidizing environment so that I can burn the carbons. So now immediately the moment I introduce the carbon, there is a weight loss which account to near about 39% carbon. And finally, I'm seeing a residue. This residue accounts to the inorganic fillers up in case you are adding fibers. Okay, because these two aspects need to be, if you look at from the quality control perspective, you have to control carbon blacks content, and also your filler content. Suppose you are adding some reinforcement into that, right? I'm going to consistently giving it. If you don't have the checklist, if there is a variation in that, ultimately that is going to affect your final mechanical properties. So this way, by using TGA, you can, I know you understand this aspect. Not only that, I'm sorry. This also will help you to do the reverse engineering. Sometimes people want that to explore what is that there. Okay, you have your benchmark samples or competitor samples, which you want to decode it. So you can utilize the TG as a technique to do the reverse engineering, because it could be a good tool to identify the composition. So how much of polymer A and B, though it is not detect what is that, detection is also possible. That is, I'm going to come to the next value addition here. That is called evolved gas analysis. So in this case, the TJ is coupled with either mass specs, or it would be with the FTIR. So in this case, what is coming at during the decomposition can be studied. For example, this is with the combination of MS, and then we can see the ion current. We can see this is nylon samples, what is evolving like NH3, CO2, and H2O, which is coming at the sample when it's decomposed. This is also one of the regulatory complaints, because oftentimes you're selecting a new material, okay, and you develop the product, but then later safety compliances comes in phase. So if suppose the material catches fire, what is coming out of the sample? So you need to well in advance think about that before the development cycle, because after introducing product, you get into that trouble of regulatory compliance or safety compliance. We say that okay, something hazardous gases is evolving out of sample, you cannot use that product, right? You cannot introduce that. That is the way how by using this PGA, MS, or so-called hyphenation techniques would able to give the more insight about that. So next thermal equipment is called differential scanning kilometer, or DSC. Okay, in this case, what we are going to do is that there are multiple applications with the DSC you can do as far as rubber is concerned. One of the things is to control the curing. Okay, I have curing. I developed a new recipe, but that recipe, is it optimal curing during my processing condition? Okay, I know that you are using a rheometers, but also you can take even that samples off from your processing station. If my curing is sufficient or not, you can make use of DSC as a techniques, because DSC can capture the reactions, endotherm or exotherms. Okay, so in this case, as you know, most of that it's an curing is an exothermic reactions. So basically, when you do the DSC analysis, we are getting a heat flow as a function of temperature. So one way the heat flow will deviate at when its samples undergoes any thermal transition expression like a glass constant temperature, which we are seeing at first. Here you can see these are elastomeric samples, two different samples. And we see that the blue samples show the TG at minus 12.61, and the green one is another compound, and which is showing a TG at minus 5.27. Then we see the exothermic curing. This is a second cycle, or you can take the sample from your production and running it on. When I integrate this energy, because you can quantify this energy, when I integrate it, I can back calculate with the software, because the software has a provision to feed your energy requirement for 100 optimum cure. Then just a click and away, by doing this analysis of integration, our software will deliver how much is curing. In this case, you can see the residual curing of the blue samples is high. So that means it is under cured. So this kind of quality check you can do by using DSC as a technique. Not only that, even the DSC can help you to detect the polymer blends, how much is the content. So for example, this is a polybutadiene mixed in the elastomers. And what we see here is, it is just, we are actually doing a modulated DSC, because modulated DSC is a technique. So I'm not talking about that technique, just to give you an overview that is a very sensitive to detect the glass constant temperature. See, here the principle is, we are detecting the glass constant of temperature of a polybutadiene, and by looking at the heat capacity change. So I know the pure polybutadiene how much the heat capacity changes. That I account as 100%. The remaining thing I'll take it for the unknowns, which is a blended one. So my software can give you the value of 0.022. You can see the transition happening here. so very sensitive, and this is the heat capacity. The change we are detecting here, and that we put in the calculation, it can even detect a quantification of 6.6 polybutadiene present in the another mixture. So this kind of sensitive measurement, you can do it by doing the techniques like modulated TSC techniques. Next, oftentimes we are doing all these studies, thermal analysis, only as a function of temperature or time and atmosphere. But what about pressure? Pressure is actually neglected factors. So we do have a solution. Like for example, this is an example of a fluoropolymer, and you all know fluoropolymer can be used mainly for gaskets, ceilings, where those materials are subjected to high pressure, not only temperature. Usually it's been used for high temperature, but how the material is going to behave under pressures, which we are not thinking about because we don't have any availability of instrument to that. But we have a solution here, like where you can see this is a studies performed at the atmospheric pressure and 40 and 60 bar, and you can clearly see pressure has a drastic effect in the thermal decomposition. It has shifted the onset of decomposition near about 50 to 60 degree. So then we can understand the importance of pressure, which is often neglected factors. Not only then, these high temperature, high pressure equipments also able to handle corrosive gases. So not only inert, because mostly we do the studies at the inert atmosphere or oxidizing atmosphere. But tomorrow, if I want to study material decomposition or stability under a corrosive atmosphere, like a real world scenario, you can do that with this kind of equipment. So that's give you another value additions. So that's about the material selections. Let's move to the workflow again. I'm going to talk about how these analytical instrumentation techniques like rubber rheometers are helpful in optimizing the processing condition. This is familiar to you all. This is a workflow. So if you see the workflow, one of the main things which is coming through the viscometer is the Mooney viscometers, which has been used widely across the industries. But again, it was introduced way back in 1930. But if you look at that, it's a single point measurement. And that Mooney viscosity, what we are specifying, it's not the intrinsic material properties. It's not a viscosity of a material. It's just the torque value we are reporting. And that also at a single point. So many a times, if you do your qualification just to depend on Mooney, there will be a problem because you have compound or materials which is having the same Mooney, but when you do it at the real world processing, there is huge differences in the behavior. So that is, but still, Mooney has been widely used for the specification and selection of material. Next is the MDR when it comes to processing, because you want to predict how the curing is happening and the characteristic time. But if come to other studies after post curing is like mainly hardness, density, and DMA. This is a common practice. But if you look at the RPA, this is the innovations. Recent times there are many companies are start moving from the MDR Mooney to rubber process analysis. Like Ajay was talking about RPA, and what solution you are getting out of this. If suppose you have difficulties in a raw material supplies, you can make use of these equipments, especially like advanced equipment like a rubber process analyzer, to answer your questions like, do I have any variation? And that variation is mainly in the polymers coming from molecular weight distribution, long chain branching. So you can rely on RPA, because many a times if you can think about the industrial people, you may have a very good Mooney, your range is within the range, and you have an MDR that is also well within the range, so you are qualifying it, but it may have a problem in the processing. But that is because of the variation in one of these. So how you can going to do it? How are you going to solve this problem? You have to work on the RPA. And today, like one of our instrumentation supplier like TA, we are offering a MDR which is convertible to full-fledged RPA. So that's the value additions. Maybe you can have the initial investment planning for MDR that would meet your current requirement, quality control requirement. But as when you have phasing and you want to broaden up the capabilities, you can go for a RPA. So that will give you a complete flexibility to control the incoming polymers. We have spoke about, in the previous lecture, we have discussed about this. And then also about the additives like filler dispersions. Okay, that we can control from the mixing station, how effective, that kind of thing. So these are the value addition you are getting by investing in RPA. Because look at that, everybody looking at the price of the RPA. I say, I am fine with Mooney, I am fine with the MDR, but later they realize that is not going to meet your requirement. You have to enhance your capability. So the wise decision is having awareness and then go for a right equipment based on your essential requirement to meet your end product requirement. Coming to processing, a lot of processing related issue can be addressed by RPA, and mainly about die swelling, curing characteristics. Like I can show the quality controls, surface effect. Here you can see example, one of the issue which I talk about is a relaxation. So die swell characteristics, you can do it with the help of RPA. But selection is also important, because when you are investing such a big machines, there could be seeing a variability, but you may not be knowing, am I really getting those variability from the compound what I'm testing, or rubber polymer I'm going to test, or is this due to the instruments? Okay, because these are like extremes. Like MDR, it is just one point. You are fixing up the frequency and the strain and study that. When it comes to RPA, you are actually working in a very broad dynamic range of strain. You have go for a low strain, high strain, and the same way frequency also low to high. So in the extremes, the instrument should deliver that. There should be a reliability on the instrument. That is often people not looking at that. So that is something is very essential, because tomorrow you are going to accept your material or reject your material based on this analysis. But if instrument itself is giving a variability, for example, I'm saying this, you can see the a simple example of a die cap. As per the ASTM, it's 0.5 mm. But during the testament at an extreme strain, the gap will change because it is like a compliance issue. Then whatever data that you are generating out of RPA is not good enough. So this is one of the factors that you have to look into that. Next comes the product performance, and we have seen conditions in a real world scenario. So okay, that we can study by using like for example, now we are moving into the product. We are released from the processing, so the form is released, and then it's subject to the regular loadings, and then there is a post-cure or aging factors which come into that during the things, and environmental exposures like a thermomechanical or thermophysical effect which affect the product quality. So one of the main things what we do is the mechanical testing. So if you look at the mechanical test, the common factor is a monotonic pull force test. Like I'm talking about UTM type of test where you will get just a stress strain plot until the failure. The next is about the fatigue test. Here we will apply a cyclic load, but again we are working on absolute values. We look for the force against number of cycles. So that's called this SN curve. So as the sample deforms, we see the mean stress or the mean force is coming down. That indicates that the material is failing slowly, which leads to the crack propagation, which we have previous discussion. Then comes the dynamic mechanical analyzer. Here we can have the possibility, but in this case we are also again applying a cyclic loading, but we can change a lot of parameters here. You can change the the force, strain, stress factors, stress level, and then correlate that properties with the structure property relationship. Like for example, your typical DMA plot of getting a viscoelastic modulus as function of temperature. But this is not stops here. Okay, I skip this point, but I want to show here a situation in a DMA analysis. You can see the green compound where the modulus is relatively between the range of 1 millipascal. Okay, and then if you go to the cute compound, your modulus is typically in the range of 10 megapascal. But the same DMA, if you remember, we were discussing the sessions where we need to do to the extremes condition. We have to go to the subambient temperature where the sample is below its glass transition temperature. That means it's completely in a glassy state. Just look at the the range of a modulus which is reaching to 10,000 megapascal, right? So it's an extreme. So the DMA should capable enough to handle the stiffness variation from starting from extremely high to extremely weak. Okay, and you also need to select your sampling according to that. Maybe you would be getting it from the uncured materials or finished components, because DMA techniques also require sample preparations. That is very, very critical. And here I'm seeing like a conveyor belt. In the yesterday, we were talking about conveyor belt, which is thick specimen about near about 24 mm. So we are actually using a 3-point bend or 4-point bend and try to get this information about this modulus part. And you can see how the variations in the modulus you can see from the scale here. Yeah, this is two more slides. Not only that, this DMA also offer you have these immersion clamps. This capability is also good if you are into the product, your product is exposed to oil or any liquids during the usage, like a seal as an example. Here we have this immersion clamps, like for example, it's a EBDM under oil. You can see oil has a drastic reduction in the modulus, and it also has changed its glass transition temperature. So this has to be considered very beginning, because if you have reduction, definitely stiffness is going down. So your seal is going to fail in that case. Okay, so you can make use of these DMA techniques. So now you can see that we can use a simple instrument for regular TG and viscoelastic modulus analysis, but you can broaden up the capabilities by extending this like different clamp selections. And even here, we can even do the heat build-up test. That is also another test you can do is on the same DMA. It's the same DMA capable to do as per the ASTM 623. I'm not getting into much, but again, what I'm saying is you can see the same thing, which is measuring the temperature rise and applying a consistent load. Okay, so but the choice is yours. Like you have a DMA today in the market coming at a different force range. You have a system which is coming with a 10 Newton capacities. You have 15 kilonewton capacities also. But if tomorrow you are going to test a small thin type samples on 15 kilometer, you won't get any data, fruitful data. But the same way, if you are running like a rubber car, like a thick specimen, you cannot work on a low force DMA. So that's the trade-off. That's selection criteria that you need to look for them. I can skip this one due to time constraint. This is about the thermal expansion part. That is, I mean, we are talking about more of flexible electronics and things where thermal matching is very important, because if there is a thermal mix patch with respect to thermal expansion, there could be a delamination and failure. And that is one of the criteria. By using thermomechanical analysis, you can able to get this expansion like a shrinkage during the curing process, because you can talk about the previous self-healing. It is possibly the curing happens in UV light, right? So that time there is a shrinkage, dimensional shrinking. So how much is shrinkage? How to control that? That information you can get. And then CTE, coefficient of thermal expansions, you can measure that, so that when you are developing a sandwich structure, you can select your CT of a different material to near about, so that it will not reach to any stress buildup. Okay, so that's about the thermomechanical analysis. I'm skipping this software part time being. With that note, I come to the conclusion. So if you have any questions, anything, I'm happy to answer.
Okay, thank you, Dr. Raj. Any questions to ask? Yes.
Is there any relation between IRST and the Soria harness?
Harness part, actually. Sir, you have any idea on that?
Different
correlations, yeah.
We have two student PA. I am from America, from UNFR.
Okay.
Recently purchased DSC.
Okay.
It was yesterday and got PA student also. We are doing the PGA analysis for the energy of the PVC. It's very difficult to find out the
PG.
Yeah. And from PGA analysis in case of PVC.
PVC, the problem is the heat capacity changes a lot when you are heating it up. Okay, so there is a way to improve that. like it's external techniques. You need to enhance, because TG is the first of all is a very weak transition. Okay, so that means the sensitivity of your system should be high. Okay, and second thing is, since the heat capacity is changing, your baseline will not be straight. It will go like this, endothermic direction. So that also will, make the detection of your TG very, very difficult. So by using some approaches like method approaches like heating rate selection, sample size rate selections, we can optimize that. I will give that inputs to you later. Yeah.
Thank you, Dr. Balakrishnan. Thank you very much. Good presentation.
Thank you for this opportunity.
I can give you the momentum for your contribution supporting this event. Thank you very much. Sound, man, sound. Thank you.
Okay, let's move to the next presentation. I also need to shift in the slots. I'm going to ask Dr. Thaumani to do the next presentation. So that I can get into the afternoon session. So it's still in the morning session, so I want to jump into the afternoon session. Thank you for, after that, Dr. Thaumani, I will invite you. Yeah, thanks. This is a very interesting presentation. I think all of you already met Dr. Thaumani. Well known, well respected, well experienced. He has a hands-on experience research, and he also is an industrialist now. And also he worked for the materials company as well, material development as well. So a living dictionary with huge experience. Yeah. Let's welcome Dr. Thaumani, P. Thaumani, Managing Director of the UMAC Auto Components, to give a talk on the innovations in power transmission belt drives with a special reference to the rubber compounds. I know him how many years now? Probably 15 plus years since there. So it's a pleasure to have him as a part of this Rubber Innovation Forum, and so honor for us as well to have him as a loud applause to him for part of this. Yeah. So yeah. Give me just a second. Oliver, sir.
Thank
Try
you,
to keep
Param.
it 20 minutes. Yeah.
I'll try to finish it as early as possible. Just run through. Yeah. Very good. Good afternoon to all of you. I thank Param for organizing this program, giving me the opportunity to present some of my research work with respect to industries. Okay. The innovation in transmission belt drives with a special reference to the compounds. I want to give more emphasis to the rubber compounds rather than working on the engineering aspects of the belt drives. Oh, this arrow.
No, it's working. Just yeah, okay, forward. This is backward.
This is a forward. Yeah, this is a
pointer. Yeah, not
okay. Yeah. Okay, I'll give a small introduction. Actually, the V-belt, first V-belt was used in car in 1920s in Japan. The purpose of using the V-belt was to drive the radiator cooling fan and the water pump. Those days, water pump was used to cool the engine. The hot water goes to the radiator. There will be a fan in front of the radiator that cools the water, and the cold water goes back to your engine again. Okay, so the main source of power is the engine, the crankshaft. Okay, from there the power goes to water pump, and then it goes to the radiator cooling fan. Here, those days, only nature rubber was available in 1920s. And the material, the reinforcing material was only cotton ropes. So the belts were made out of the natural rubber and cotton ropes. But when they use this belt, because of high load, the belt has a tendency to elongate. Once belt elongates, it will not be able to transmit the power. It will be slipping over the pulleys. So once the cooling fan is not running, you will see the water is getting heated up. So finally, you can see the water will be boiling. The radiator lid will be getting opened, and a lot of steam will be coming out of that. Okay, and this has been the case in 1920s, 1930s. You have seen in 1970s and all, the directors, they use this concept to create a romantic song. The heroine comes in a car, because of the radiator getting overheated, steam goes out, gets under breakdown. A middle class hero will come. He will come and immediately will adjust the belt tension. He will start the car. It will go away. So he creates an romantic point. From there, the song starts. So to the extent of belt was so popular. Okay. So later on, a lot of development has taken place. Innovation has taken place. See, there has been a tough competition in the automotive sectors. Always they have to come with some innovative things. Okay, with respect to efficiency, fuel efficiency, cost, and reliability, the cost of ownership, many things. That's why continuous innovation has been taking place in the automotive sector. Those days, they wanted to add more components for passenger convenience, like air conditioners, power steering pumps, power assisted brake line, brakes, all those things. So for each one, drive was required. The main source of power comes from your crankshaft, the engine. But the power has to be distributed to all other components. At least there used to be a minimum 4 bells. One to drive the water pump, alternator, air conditioner, power steering pump. The alternator is designed in such a way that even at idling RPM, the alternator generates a power to charge the battery. So they keep the pulley, alternator pulley, much smaller. Okay. What happens because of smaller pulley, the belt quality is not good. The belt used to slip over the alternator, and battery, they do not get charged enough. Once the battery doesn't get charged, then you will not be able to start the engine. So on the middle of the road, if you stop your car or stop the bus, you're not able to restart the things. This has been the case in the 80s or before 70s. Okay. When you use more belts, there are more chances of failures. Okay. So you would have seen it, people pushing the buses because bus doesn't start. Once the alternator is not generating power to recharge your battery, you can't start the engine. So people push a bus, then start the bus. After that, everybody gets into that and then moves. Similar is the case. When the water pump is not working properly, your radiator gets heated up. Okay, engine also gets seized. So there has been a continuous innovation to replace the situation with a single belt. Here you see many belts. Many belts. Okay, many belts means each belt will be in a different plane also. It occupies more space. Okay, and each belt is a much thicker belts. Those days they used around 8 to 10 mm belts. When you use a more quantity of rubber and more belts, lot of energy is wasted in the form of static energy losses. The fuel efficiency was getting reduced. Okay, in order to improve the fuel efficiency and the belt performance and the reliability, the designers, they moved the things. The complete layout of the drive was changed. All the components have been brought into the same vertical plane so that a single belt can drive many components. Now you see all your alternator, water pump, air conditioner, power steering pump, even the air assisted brake pump also is driven by a single belt. This belt is much thinner. It's hardly 4.5 mm thickness. The rubber content is much less. The only thing is that when you use a single belt to drive many components, the load is going to be very high. The belt should not get elongated. If it gets elongated, again slippage will be taking place. The transmission will not be efficient. Okay, to that extent, there has been a lot of improvements on the reinforced material also. Okay, coming to a very important point, the belt tension is maintained by putting automatic tensioner. There is an automatic tensioner. This tension always keeps the belt tension constant. Not only that, if you want to replace the belt, just push this tensioner down. Belt gets loosened. You can take it out. You can put a belt easily. To that extent, innovation has taken place. A single belt, which can drive many components. This is made out of a special material, which do not elongate so easily. At the same time, fitting and replacing the belt also so easy. Anybody can do it on the roadside also. Okay. Now, the engine compartment is more small. Earlier, they put a very big engines. You would have seen that all Tata trucks used to have a separate bonnet in front of the same driver seat. Similarly, Ambassador used to have a big room. Now they compress the engine compartment. They created more space for passengers and other purpose. Okay, because of this only, because of layout change and making it more compact, the engine was very compact. When you open this, you will not be able to see the belt also. This is a very critical component. Because of this, the underhood service temperature has gone up.
Earlier it used to be around 90, 100 degrees centigrade. Now it has gone up to 150 to 160 degrees centigrade. Not only that, here to save the energy, the radiator cooling fan now it is not driven by the belt. It is driven by electricity. And also it has a thermostat with a magnetic clutch. Whenever temperature goes up, only that time the radiator cooling fan will be on. Similar is the case with the AC also. AC compressor, there is a thermostat sensor with a magnetic clutch. Whenever the temperature goes up, that time only it gets. To that extent, the efficiency has been improved to a larger extent. Okay, this may not be interesting for the polymer technologies, but overall, as a common thing, I'm sharing with you. Okay, so very important innovation is when you use a V-belt, the contact goes only on the edges. But when you move to poly V-belt, shown in the last one, the number of ribs are more. The overall contact area is improved. Okay, this has increased the contact area and thereby the power rating of the belt, so that a single belt can drive many components. This is another application which I wanted to share with you. This is the snowmobile belt, which is used in snow when the countries where we have temperature less than sub-zero. There, they use a belt. The belt has to work at minus 40 degrees centigrade. Okay, at minus 40 degrees, you have to start to run it. Once you run it, it generates a lot of heat. The temperature also goes up to even 120, 130 degrees centigrade. Just I'll play the video. It has two clutches. One is attached to the engine, another is attached to the drive track. See, the first one, which is attached to the engine, has two flanges. When the RPM goes up, it compresses the belt from sideways, so that radially belt moves up and the effective diameter increases, and thereby the engine RPM, the speed gets increased. See that when you're starting it, the belt is stagnant. With increasing speed, moves up. Yeah, then the vehicle drives it. Here, the belt should not get elongated. Once it gets elongated, it cannot transmit the power. Second thing, there will be lateral compressive force coming from the flanks. Okay, it has to withstand the compressive forces. That's why the belts are made with a special material. It's a basically composite of fiber, aramide cut fiber. Plus, this may sometimes made with the aramide or is with carbon fiber. There is another application, e-bike. You have seen in the motorcycle, only chain and sprockets were used in the past. Now in the electrical vehicle, even I have taken down assignments to redesign the drive. Here, the metallic part, chain and sprockets are being replaced with a belt and a aluminum-based sprocket. This is called synchronous belt. The belt has a teeth like this. The matching part pulley also has a teeth. It engages with the teeth on the pulley and then transmits the power. Okay. This being a belt, a rubber material, it doesn't generate a noise. It does not need lubrication. The overall weight of this drive system is much less compared to your metallic chain and sprocket drive. That's why all your electrical bikes are coming with this kind of belt and synchronous belt and the battery drive. But the point is, this belt should have very strong strength. That's why here they use carbon fiber. I had an opportunity to work on a carbon fiber technology, which has much higher strength, 3 times higher strength than your steel on a comparable weight basis. Okay, here also the belt is made out of carbon fiber material. Yeah, look at this. The carbon fiber has a very high modulus, very high strength compared to your other materials like epoxy classes or aramide material. So there has been innovation. In the carbon fiber also we have a T300, T500, 300 gigapascal, 700 gigapascal modulus, high modulus materials available. And then look at the elongation. Elongation at the breaking point is hardly less than 2%. The belt literally they do not elongate. It behaves like a chain, so that the pitch is not mismatching it. It gives a longer service life. Yeah, coming to the very important thing is for a variable speed belt or poly belt, a single belt is transmitting more power, so it should be flexible along the circumference. During the life cycle, it makes millions and millions of cycles. It should not develop a crack. At the same time, it should have enough rigidity across the belt section so that it can withstand the lateral forces. Okay, that means more flexibility along the circumference, high rigidity across the belt section. All these belts are made with a compound which has a hardness more than 90. Okay, but when you go for a conventional reinforcement with the carbon black fillers, probably you'll be able to get a hardness of 80, 85. But belt life above 80 hardness. See this curve shows. This curve shows the belt life. When the hardness is less, life is less. Belt life goes up, reaches an optimal level at around 80 hardness, beyond which drastically gets reduced because it loses the flexibility and develops a crack. So with the conventional carbon black reinforcement, it is not possible to have this kind of anisotropic property. One side flexibility and another side rigidity. That's why you need to go for a composite material. Okay, in the composite material, you have a rubber matrix in which short fibers are dispersed, but these fibers are oriented in a particular direction. Okay, so when we do mixing, it gets random orientation. Then we do calendering. During the calendering, along the direction of shearing force, the fibers that gets oriented. Okay, see along the sheet, the fibers are oriented, but on the belt, you need a rigidity across the belt length and flexibility along the circumference. Okay, so what we need to do is we need to cut the fiber and change the direction. Once you change the direction, see when you bend the strip, this like this, the fibers are not taking the load. Only rubber matrix is taking the load. That's why it will be more flexible. But along the fiber orientation, when you bend it, the fibers are taking the load, which is a high modulus material. That's why this material will be more stiff. So we build the belt. See, to get a uniform thickness, we calendar sheets of around 0.8 millimeter. Then only the orientation, the fibers will be uniform. Then we play up the layers one over another, keeping the orientation across the belt section, and then we build the belt and cure it. Okay. For playing up, the tackiness is very, very important. And moreover, the interfacial bonding between the short fiber and the matrix, rubber matrix, is very important. If the interfacial bonding is weak, then during running itself, failure will take place at the interface, and then crack also will propagate, and you will not get the desired life. So, very important thing, the rubber matrix should have good tackiness and also good affinity with the fibrous material. Then only you will be able to design a belt with good bonding. The strength comes from the reinforcing material. Yeah, this material may be carbon fiber or polyester or aramid cotton. Okay, so the rubber, whatever we use, should have good bonding with the reinforcing material, with the fillers, and also sometimes we use a fabric. With the fabric also, it should have good bonding. So there are various materials evolved over a period of time. First, they started with the natural rubber, but with increasing heat resistance and performance, it was not able to meet the requirements. Then from 1960s to 2000, CR, polychloroprene rubber, has been the workhorse of the belting industries. Okay, CR could work up to 110 degrees centigrade maximum, but nowadays the availability of CR, because of environmental concerns, is getting diminished, and also it's quite expensive compared to other rubbers. Then there was another material. DuPont came with a material. This material called Axiom, which is chlorosulfonated polyethylene. That could increase the service temperature up to 130 degrees centigrade, but it was quite expensive. So 5 times expensive. The third item was the EPDM. EPDM, I was leading the technology management of EPDM in SABIC. I know it's a very versatile material. You can tailor make any grades because of 3 monomers. Okay, so it can work up to minus 50 degrees centigrade on the lower temperature side, and the higher side it can go up to 160 also when it's a EP rubber. Only thing is oil resistance is poor, ozone resistance is excellent, price wise also it's very competitive. Okay, the very important task for making the EPDM is it is a 3 monomer. It consists of 3 monomers: ethylene, propylene, and a pure side monomer ENB. When you polymerize ethylene, you get a plastic material, polyethylene. Similarly, polymerize propylene, you get a polypropylene. I was leading both the industries. The third monomer ENB, when we introduce it, third monomer ENB, which destroys the linearity or introduce the long chain branching, and thereby prevents the alignment of the molecules and crystallization. That's why with the introduction of ENB or long chain branching, we could create a polymer with a more amorphous phase. That's why EPDM is a plastic. It's not a EPDM is a rubber. It's not a plastic. But it has challenges. So EPDM is a polyolefin rubber consisting of only carbon and hydrogen, only 2 elements, carbon and hydrogen. There is no polar material like oxygen or anything else. EPDM is totally apolar, non-polar, and this is not compatible with any polar substances. All fibrous materials are highly crystalline, polar material. It needs interfacial bonding. So with the EPDM as such, it's not possible to have a bonding with those materials. So by chemical modification, EPDM can be made an oil resistance comparable or better than polychlorobenzene rubber. Polychlorobenzene rubber is a polar material. It's easy to have a tackiness, easy to have a good bonding with the fibrous material. But with the EPDM, it was not. The possibility of EPDM can be made as good as the CR once we modify the EPDM. The chemical modification is very, very important to achieve this. When you say chemical modification, as a scientist and the polymer scientist, there are two routes. One, you can do the chemical modification in the reactor itself. Okay, while making the polymer itself, we add monomer or whatever material is required and then modify it. The second is the post-reactor modification. One of the things is crafting, blending, all the things are post-reactor modification. The reactor modification is quite expensive. For example, when you take polyethylene, and then do the chlorination, you get a chlorinated polyethylene, which is expensive, which is costlier than ethylene. Similarly, if you take nitrile rubber, do the hydrogenation in the reactor. Hydrogenated nitrile rubber is 10 times expensive than nitrile rubber. So reactor modification is quite expensive because it needs a lot of cleaning, other things, and the process also needs a very stringent conditions. That's why it's preferred to have a post-reactor modification rather than the reactor modification. So I did a lot of work the post-reactor modification. EPDM being a saturated polymer, okay, the only possible for chemical modification is knocking out of one of the hydrogen atoms, which is susceptible for radical attack, create a macro free radicals, then create another functional monomers with the free radicals, attach these two to form the functionalized EPDM monomer. The possible route is the ethylene, the ENB part, which is used for cross-linking. This hydrogen is called tertiary hydrogen. This hydrogen is highly susceptible. When you put a peroxide, it makes a free radical and then reacts with any vinyl material, and thereby you can functionalize it. Okay. But in the EPDM, the total quantity of this part is hardly maximum 10%, not more than that. Okay. And those who are familiar with this, they know very well. When you put a peroxide and do this, there is another possibility that this tertiary hydrogen in the propylene segment that also gets knocked out. When you want to make a propylene, polypropylene with a low well flow index, with a very high molecular weight, what we do, we manufacture it with a high molecular weight, and then to produce a low well flow index, we crack the high molecular weight polypropylene with the peroxide. Okay. When you put a peroxide, the polypropylene undergoes degradation and makes a low molecular weight fraction. Same thing happens here also. When you do functionalization with the peroxide radical, the propylene segment has a tendency to undergo degradation. Okay. And this what happens, this is a competing reaction with cross-linking. So it undergoes cross-linking and forms a gel. So we did a lot of experiments, not only myself, but many scientists who are working in the polymer industry, they've done. They try to replace this with, try to introduce hydroxyl groups, amine group, epoxy groups, and thereby we can increase the polarity and then by increase the oil resistance and also compatibility with the other substances. But maximum only 5% could be put there. Beyond that, the competing reactions were causing either degradation or cross-linking formation. So, but this 5% functionalization was not good enough to get the desired properties. So, I was thinking about this. Then I came with a novel idea that instead of using a monomer with a single functional groups, I wanted to go for a polyfunctional monomer. A monomer which have more than 2 functional groups. Okay. Polydimethyl siloxane, which has more than 10 functional groups. Like that, I will synthesize one polyfunctional monomer, and then we carried out this chemical modification. By removing one hydrogen, we put one PFM, polyfunctional monomers, which introduced monomer with many reactive functional groups. With that, the polarity of the material enhanced to a large extent. The property of the polyfunctional crafted EPDM was much better than other materials. Okay, just I'll show you the kind of improvements what we have done. So the functionalization was done in internal mixture at 130 degrees centigrade using peroxide as an initiator. After functionalization, the processing. Otherwise, EPDM does not form a band easily like this. Okay, you can easily mix it like a natural rubber. So the polarity has increased the cohesiveness. Okay, it has given a very good tackiness and also sticking to the mill so that you can easily process it. Yeah, we did FTAR. We confirmed that the crafting of functional group is attached to the EPDM. Next, we went on the compound. The compound is done. After mixing from the dumbbell, the operator could easily sheet it out. Otherwise, the EPDM rubber generally has a tendency to backing and sacking. It doesn't form a roll easily on the two-roll mill. Okay, but functionalized EPDM makes a very smooth band in the sheeting mill. Yeah, to see the calendering process, this rubber runs very smoothly in the calendar. Sorry, there's a here you can see the compound is making a smooth rolling back on the middle of the calendar, thin-roll calendar. The fabric completely uniformly gets coated with EPDM. It's really very difficult unless you do the functionalization. Okay. Then we made a belt using this functionalized EPDM and tested the bonding with the material. This is the adhesion test. You can see the fabric is having uniform coating, very good adhesion strength. There's interfacial failure. There's no interfacial failure, it's a cohesive failure, which shows that the bonding with fabric, it is a polycotton fabric. It's very difficult to get a bonding with the polyester cotton blended yarn. But because of the functionalization, we could get very good bonding. Similarly, this is with the polyester cord, which is required for reinforcement. We got a very good strength. Finally, we made a belt with the functionalized EPDM that gives very good life, even at 115 degree elevated test temperatures. Okay, coming to the end of my presentation. Design of the belt tray layout has undergone an innovative change from multiple belt to a single belt over a period of time. That has removed many of the hurdles, many of the problems. Okay, the innovation in drive systems such as addition of auto tensioners, magnetic line, tamper pulleys have optimized the energy consumption and ease of maintenance, etc. The innovation in material science indeed drastically improved the reliability, overall cost, and performance of the belt drives. Rubber fiber composite enabled to design belt with adequate rigidity to transmit the demanding torque, and at the same time, the needed flexibility so that the belt can make millions of flex cycles over an array of pulleys without developing cracks. The invention of exotic fibers like a glass and carbon aramide fibers really augmented the strength of the belt so that a single belt can transmit enough load. The crafting of polyfunctional monomer and EPDM enhanced the polarity, processability, and addition of the fibers, and thereby enabled to innovate high performance polymer belt. Thank you. Where is that Param? Yeah, if you have any questions.
Substituted the ionic hydrogen with the EPDM. So how was the curing possible after that?
Curing is a peroxide cure. Yeah, peroxide cure. It's a peroxide cure. Yeah, peroxide cure you can do it because any hydrogen on the main this thing can be knocked out and then make a crosslink. No, sulfur cure is not possible. Sulfur cure is not suitable for 150 degree centigrade application. Okay. Yeah. See, maximum the sulfur bond can withstand up to 130 degrees centigrade, not beyond that. But our requirement is 150 degrees centigrade, so we need to go for peroxide curing.
So what kind of peroxide you use as the initiator?
Yeah, we used two is a proprietary thing is going for a patent. That's why I'm not selling. We have one primary peroxide and a secondary peroxide. The secondary peroxide decomposes at low temperature, creates a free radical, accelerates the decomposition of another peroxide. Then we have co-agent also. Yeah, so that we get a crossing intensity, enough crossing intensity. Yeah.
One question.
Yeah.
That in your scheme that you have shown that PGM that you are functionalizing with the polar molecule, but it is highly likely to get the hydrogen from the ethylene knocked out rather than propylene hydrogen.
No, that's what I explained there.
Because it will create a tertiary radical which is quite stable.
Yeah, that's what. There's only two tertiary hydrogen atoms are there. I'll go to that particular slide. Yeah.
Yes. Yeah.
You have two tertiary hydrogen atoms. One is in the propylene. This is the tertiary hydrogen atom. Another is this hydrogen atom. Okay. Because of this double bond, this is more labile. This can be easily knocked out.
This is already knocked out.
Yeah.
And the other hydrogen.
Other hydrogen. Yeah.
Similar environment. The other hydrogen from the polyethylene is also likely to be knocked out.
Yeah. That I explained the things. When we want to make a low molecular weight polypropylene, we make a high molecular weight polypropylene and then we crack it. The cracking is done through peroxide. The mechanism is called a beta session. Okay, once you knock out this hydrogen, this cleavage takes place. Okay, the fragmentation takes place, molecular weight comes down. Okay, so this knocking out of this hydrogen is not desirable. It leads to scission, breaking up a propylene segment.
It does not remain as polypropylene. It's propylene unit anymore. If you are fragmenting, it is not saying as polypropylene unit.
This is a propylene segment. It's not a single unit. There will be a block of a propylene segment. Okay, but once you knock out this, it undergoes breaking up that chain and makes low molecular fractions. Okay, that's one of the competing reactions that I would have mentioned here. Yeah, there is a very because of that only introducing more than 2.5% functional group was difficult. One is a competing cross-linking reaction, another a degradation reaction. Yeah, that was the limitation. That was putting a limitation on introducing number of polar groups. But anything less than 10%, you will not see a significant change in the properties of the polymer. Yeah. Okay.
Thank you, Thank you very much. You can please.
Thank you. Thank you, madam.
Thank you for your appreciation.
Yeah.
Thank you, sir.
Okay, let's move on to the few more presentations left before we all go home. How are you feeling, guys? Tired? Okay. I know. Tired? I know this is missing. It's just 10. This is missing in the morning. Okay, so yeah. As per schedule, we don't manage the time properly. So there is one more presentation before you. We are a bit running a lot of late. You know, like some Indian railways today. So, okay, so I'm sorry about that. Really. Oh. I'm good. I know that I want to maintain, but unfortunately I had to. Yes, please. Thank you. Okay, let's join me to welcome Mr. Nishank Verma from the School of Nanoscience and Technology and the based in IIT Kharagpur, right? And he's going to give a talk on the material modeling of non-linear viscoelastic behavior of the rubber composites. Guys, young guy doing his PhD, yeah, right? So join me to welcome him, please. Yeah, good.
Thank you, Ram. Yes, sure.
I will take that for you. So I think we should understand the material from the macro level and the micro level also, from wherever we are interested in. So here I am presenting my talk on the material modeling of the nonlinear viscoelastic behavior of the rubber composite. So when we go inside and we discuss about the viscosity, which is the property of the material that we all know that exhibits the viscous part as well as the elastic part also. As we can see in the ball, when we are dropping under the gravity only, we can see that thing happening in front of us. And where the viscoelasticity is critical for, it is critical for material deformation, understanding the material deformation, how it is deforming under the loading and unloading, and how it is recovering under the stresses, how the durability has been changing with the change in the viscoelasticity of the material, and how the energy absorption is being happening inside the material. And the other critical point is what viscoelasticity can tackle is the damping property of the material. So when we see how we can differentiate with the linear versus the non-linear viscoelasticity, is that if you can see in the plot, it is just an ideal plot I'm shared here for understanding the difference between both of them. Is that when we are applying the strain of like sigma or sorry epsilon, and we are getting a stress of sigma naught, and as we are increasing, as we are doubling it, in the linear viscoelastic behavior, it is getting double. The stress induced in the material, the stress developed in the material is getting double. But it is not the case with the non-linear viscoelastic material behavior also. And if we go on the modeling side, when we are defining some models, when we are defining some material modeling into it, and some mathematics we are introducing into it, we are replicating the behavior with some like if you have seen that we have considered springs and dashboard models. Somewhere we are having the springs only, somewhere we are having the dashboards only, somewhere we are having the combination of both of them in the series, in the parallel, for understanding better about the how the linear viscoelasticity and the viscoelasticity behavior is happening inside the material. And that is not the case just for understanding the viscosity. There are different methods and different properties that we can study with those meta models. So what is the non-linear effect in the rubber is that it is quite helpful in understanding the hysteresis and the energy dissipation, as stress strain curve is different during compression and loading, and the energy dissipation what is happening in the rubber material is very helpful for the damping applications. We can go for the understanding for the load dependent stiffness also, and as we can see, the phenomena are very crucial for understanding the creep and the stress relaxation behavior of the material, and the damping response and the material design and optimization. As we go for the nonlinear theory of the viscoelasticity, there are some mathematical standards that has been maintained, and some of the assumptions that has been made so that we can replicate those material models into the real world, and we can correlate with them with the real world situations. As we can see here in the slide, we can I've shown an idealized DMA plot where we can see there is a glasses and the glasses and the rubber plateau and the viscous phase of the rubbery part is available. For each of the part that is there in the DMA plot, we have a model. We can show them, we can replicate them, we can we can understand them with the help of the elastic, the Kelvin-Waggett model, or whatever it is there in the description. Like they are just a series of and the parallel or the combination of the series and the dashboard model only, the spring and the dashboard model only. So what we have done is we have developed a non-linear viscoelastic model with the help of a parallel combination of one that is just the elastic part that is being covered in the part the network A of the model, and there is a the series part of spring and the dashboard that you can see here is represented by the Maxwell model and the elastic model. So we have a combination of both of them to understand the time dependent and the time independent behavior of the material, and including the Payne's effect also through the function. As if we can see with this variable, we are introducing the Payne effect into the picture also. If you see the Cauchy stresses developed in the network A and the network B, we are conjugating them and we are creating the hyperelastic model for the pouring series. But this is not where we are stopping. We are looking forward to develop this material and to introduce a
single variable where we can take into account the parameters that are being used in the 3D printing, the parameters that can take account into the change in the parameters of the 3D printing processes, like the nozzle temperature or the hot bed temperature, or what is the nozzle size. These kind of things are changing the property of the material, but not at a very significant ways. But we can look into it with the help of these nonlinear viscoelastic models. So for the determination of the material parameter, that is the major task while we are using any of the material model, while through the simulation or just we are doing the mathematical calculation. For that, we as I was already told that the design of the experiments and the testing facility should be utilized in an optimized way. Is like we can go for the tensile compression or a selection test and the volumetry test. And for their optimization and for their correlation with the real text experimentation data, we can use some optimization, numerical optimization techniques that I mentioned, like Levenberg-McIntyre method and Nether technique. For the model validation, I have just shown a few examples. Like if you can see in the first figure number 5, you can see there are 5 of the models that has been used, and if it is clear that we can see with the experimentation data, the Madlow model is quite relatively showing the similar behavior in this. And when we go for the figure 6 for the uniaxial tension and simple shear for the bearing, we can see that there is just only one model, that is the Yog model. It is, I forgot to mention the name of the Yog model. The Yog model is able to predict the material behavior from the starting, and it is just kind of replicating with the smallest of error in the model. And if we see, it is just taken from the fitting error and the distribution of fitting errors. If we can see, there is a very small error possibility that is happening and that those are only happening in the small range of the RPMs, and that is in the yaw model. So based on this, we have on the conclusion that the yaw model or the material model that are able to predict about the viscoelastic and the linear and the non-linear viscoelastic, both those materials can be beneficial for understanding the behavior of the metal in the future also. So this is the future scope, like the multi-scale modeling approach, and using those material in the advanced constitutive modeling and the additive manufacturing also, and for 3D and the 4D printing techniques we can use. That's all. Thank you.
Thank you very much. Thank you very much. I had a few questions on it because I have finished some of the projects. And I want to give you a small appreciation. Take a picture. Come on, you are photographer. Thanks. Thank you. Okay, let's go to the next one. Some people have train appointments or family appointments. I need to keep up. Yeah, so please do understand. Okay. The next topic of this conference is the tire technology into the future. Our innovator speaker is Dr. Jyoti Prakash Rath. He is the head of the R&D Asia Compound Development at Apollo Tires. So please join me to welcome Dr. Jyoti Prakash. Come on, guys. Yes, so please. Jyoti, I know that time is essence here. Yeah. So please do the best. Yeah. So thanks.
Thank you very much. I'll try to do it in 15 to 20 minutes.
Sure, fine. Yeah.
The number of slides a little more, maybe certain slides should skip through.
Okay.
Fine. Hi, good afternoon, everyone. So my topic is tire technology into the future. So this is not a very heavy dose of paper. Generally, what has been presented, pre-lunch and post-lunch with a lot of data. So this is more of a review on the approach, what
we feel that tire industries are going through or in the future is required, and how as an organization Apollo Tyres is preparing. So that is what will be covered. Okay. So coming over to the broadly tire market scenario, the takeaway from this slide is that if you consider last FY, so it's a close to 232 billion USD company, and the projection is by 2030 it will be around 300 plus USD billion dollar company. And considering India, it will be the second largest PV globally. So presently, if you consider China is the largest two-wheeler manufacturer. So largest and most influential segments of the automotive sector, if you consider this graph, so 45% of the revenue is going to come from Asia Pacific. So the manufacturing hub will be Asia Pacific. Now moving over to the next, what is the major challenge when you consider a tire in terms of sustainability? So which is one of the buzzword, and which is the presently we said in the near future, that is the most important future technology which all tire industries are preparing into. So typically to material distribution of truck tire and passenger car tire has been given. If you see that maximum except natural rubber, most of the other chemicals are coming from crude oil. So today, which is and of course everyone is very clear that crude is depleting, and we have to prepare ourselves, and that's where we have to have a much more sustainable source of materials. So again, beyond that, when you are saying that tire industry is a 300 billion plus industry, what is happening in the tire at the end of the life? If you consider the left, you can see this is the percentage of the tires being produced, and in the right side graph, if you see the right side graph, if you see, so most of the material recovering what is happening is around 47% or roughly 50%. The other 50% today is not really properly recycled. The circularity part is not that great at this point of time, where there is a big opportunity. So sustainability including circularity. So circularity becomes more prominent in the tire industry. So now typically what is the different mix of the materials? Today if you consider present current situation, 50 to 60% are non-renewable material. Hardly 30 to 40% materials are renewable or recycled. In fact, it is maximum will be 20-25 to 30%. And BAU 2050 means if you do not do anything, business as usual will continue. So by 2050, this percentage will further increase. Non-renewable. So there is no material. Non-renewable materials are won't be available. So by 2030, what is the very short-term target? I will say in the next 5 to 6 years. So we would like to reduce the non-renewable content of the material. And if you see that the material B and C, which is renewable and recycled, that is going to increase maybe 50 to 60. And moving over to 2050, we want to completely get rid of non-renewable material. So the material will be fully sustainable. Today, so the two materials what is available will be renewable and recycled. So that is what the sustainable material. So the key actions, okay, reduce RM consumption. We can always reduce the consumption, recycle effectively, develop new renewable materials. So moving over, what big industries are doing, and we are also following the same trend. So everyone is trying to increase their sustainability content. So Apollo Tyre is, if the last graph is from Apollo Tyres, so we are trying to increase our recycled material and sustainable material. By 2030, we want to have 40% of our material sustainable. So like yesterday, some presentation was there where it was addressed. The industry has to do looking towards the social aspect. So presently, if you consider the driver is economy, the majority of the industry, not only tire, I would say it is general, it is economy driven. But in the future, trial will be towards more of environment as well as social. The economy part may be only a quarter. So that is what is the future expectation, and it is a must. So we are preparing towards that. So now sustainability, when you are saying that in a tire manufacturing, so Apollo Tyre, our approach is that 6R approach. What we say that 6R approach means reduce, reuse. You can, if you see this, reduce, reuse, recycle, replace, redesign, reliability. So this is how we would like to approach. So reduce means reduce material consumption, reuse the materials, again like retreading, recycle. At the end of the life of the tire, it has to be recycled in the right way. Then replace non-sustainable to sustainable material, redesign with light materials. Then reliability, enhance the life of the tire so that the demand for new materials reduces. So now what we have done over the last 2 decades, if you see that the tire weight has reduced by 100 to till 2030. So presently, if you consider, we have already reduced by 20 to 23%. So by 2030, our target to reduce to 74%. That means 26% reduction in the overall weight. So that is directly material saving. So what happens of this effect on the rolling resistance? Everyone knows that, you know, one of the major criteria for fuel consumption or higher fuel consumption is higher rolling resistance. By reduction of this 26% weight, the rolling resistance has been reduced. Now presently, if I consider, it has been already reduced over the last 2 decades, more than 30%, 1/3, 66 is the present rolling resistance, considering 2000 as the index of 100. So we expect by 2030 it will be further reduced to 57. That means more than 40% will be reduced. So which will lead to, so what will be effect of reduction of rolling resistance? So 15% of the total CO2 emission can be reduced. So typically what we are saying, if 20%, 25% rolling resistance reduction happens in a tire, that will lead to save of 10 trees in a single trip from Delhi to Mumbai. So 10 trees can be saved if we use 25% low rolling resistance tire. So that is what, when you see that we have reduced 34% presently and we are going to reduce further another to 47% rolling resistance. So this is the kind of impact which can help the sustain our Mother Earth. Now moving over to, of course, this major content is with the innovation in terms of the materials. So presently we are using, okay, conventional materials. I am not saying that. So now in the very near future, or already we are in the transition phase, going to sustainability, you know, coming the materials bio-based. Today morning also, Professor Srilekha already presented on the sustainable different materials. So what we are preparing, whether it is in the GPSNR, whether it is biopolymers, whether it is vegetable oils, those things are already in progress. Then the future technology, what will be? So functionalized materials, so that the performance of the materials can be improved, so the life can be increased, so that the weight can be reduced. And another thing is that, you know, in the era of IT, so we also have to, you must have heard autonomous vehicle. So tire will be sensorized. That means there will be a lot of sensor. Tire will be also kind of a, today tire cannot speak. So future tires wants to speak with autonomous vehicle, and which will require also a lot of smart materials. That is what the future in terms of the materials are going to be. So now coming over, you know, to the part of the sustainability, one is that how we are doing the end of life tires. Of course, there are different technologies, Styromer, D-Link, Labgum. These are different technologies. I'm not going through all of these. There are, of course, there are conventional technologies. These are the popular technologies, which is, if you consider the recycle domain, so these are the winner in terms of technology, which is being used by the major industries. Okay, basically all recycle this technology is to how we can because after curing we know that rubbers become thermoset. So can we again bring back the polymer? So that is what different ways everyone tries. Now the next one, so all last what I was saying, that when you are trying to break the bonds, so we are trying to get the rubber. But another one of the another ingredient which is being used in the compounds is the carbon. So also recovered carbon black, that is also another great approach. Today, if you consider the technology is there, the grades of carbon what we can get is not that great in terms of performance. That means if you consider ASTM grade till N6 series kind of carbon black is can be recovered. The quality, suppose we use 2 series, 3 series hard blacks for the tire tread and all. So those areas still requires further improvement. And there are lot of with the tire is or the carbon black, what it comes, it is also having a lot of content which is not required, which has to be cleaned. That is why the quality can improve. So those technology also has to progress. Now next area in terms of sustainability is that biomaterials. So typically in biomaterials, what we are saying that how the monomers can be made from the bio source. So basically whether it is different, turbine feedstocks, liquid furnace, betamycin, bioethanol, penicillin expansum. So these are the different monomers which has to be made. And today also, presentations were there in the other hall. You must have heard, where all the major polymer manufacturers are using biomonomers. So basically these are the roots which is being used to make the biomonomers, and which is again will be used to make the polymer. And this way the synthetic rubber, the SBR, BR, what is being used in the tire, or even for that matter synthetic polyisoprene. So that also can be made, which is in a sustainable way. Now moving over from polymer to bio-based filler. So of course you know that cellulosic fiber CNF is extremely important because of its abundant availability, because of its great strength. It is the material which is under investigation. In fact, we have projects today morning also. Professor Srikala already presented. We have a project with her with MG University for cellulosic fibers. Then lignin, another abundant material, strength is great. So, but these materials have to go through the hard route of evaluation, development. Still, if you consider the tire application, there are multi-facet requirements. These materials still are in the research stage, publication stage. The industrial challenges has yet to be overcome. Now another important material is silica, which is being used in the low RR tire. Conventionally, silica is, though it is coming from a natural source, but the manufacturing is highly energy consuming. So that is silica. Conventional silica is not considered as a sustainable material. So the sustainable material is the rice as silica. So I see Tata Chemicals is present. So we have also done our work and published a paper with respect to rice as silica. And what we have seen, at least 75% of the present silica is replaceable in present technology, and we believe very strongly 100% of the conventional silica what is being used can be replaced with rice as silica. We have a publication last year, so these results are mentioned. So almost all the properties are equal, and some of the properties also better. So here actually we are not looking for to improve the properties of existing silica. We have to only match it. So now what Apollo is doing in terms of sustainable tires in the last couple of years, if you see that Apollo Tires has in all segments of sewing, the reason of showing all different segments of products, the technology, the compounding technology is different in different kinds of products, whether it is OHT, whether TBB, TBR, PCR, in all segments 65 to 70% sustainable content tires already we have showcased. But today those tires are not available due to two reasons. One is that availability of the exact sustainable material, the technology is there. This is going under proving, the duty cycle of the tire is maybe 3 to 4 years. That has to be proven. So those developments are happening. But we believe that within the next 2 to 3 years, we have the technology where we can have 65 to 70% sustainable material. Now Apollo is working with a lot of suppliers as well as the university. So Tyromer, the recycle, we have tie-up with them. With NRF Singapore, you are with IIT Kharagpur and other major recycling companies in India and outside India. We have tie-up to secure or to develop the ecosystem, which is one of the most critical requirement. Today, suppose we have a technology also, the availability of the material has to be great. In the morning, there was a presentation with respect to 6PPT alternate, but still the volume of the production is limited. They are not yet supplying to tire industry, considering the volume requirement for tire industry is much higher than a non-tire. So moving over from sustainability to technology advancements. So of course, everyone knows today the era of data science, artificial intelligence and machine learning. Today, tire industries are coping up with this challenge, and as a part of Apollo tires, Industry 4.0. Today, all of our plants, mixers, Apollo is having 7 plants across India and as well as Europe. So all the 7 plants, all mixers data is connected. Earlier it was not there. So the information what it is coming and using the data analytics, we are even the same material is being different plants is being used in a different way. That can be improved. This is in the manufacturing. Deeply we are collecting the data and analyzing, and this is the manufacturing part I have said in terms of AI ML, but this is can be also used in terms of collecting the tire mileage informations. The next big trend in terms of automotive is our mobility industry is to make the autonomous vehicle, connectivity, IoT, electrification, shared mobility. So what it requires? It requires sensor tires. It requires sensor tires. What we call that smart tires or talking tires. Tire has to, if the inflation is low, if the temperature is high, if some issues is that they have to communicate to the vehicle. Today tires cannot do that. So we are working on that. Then of course airless tire you must have heard, or low noise. These are the typical requirement or regulation requirement in terms of low RR, better durability, extended mobility, run flat tire. Then extremely high mileage traction. These are the safety requirements which commonly tires also today it is demanded. Now coming over to the talking tire, what has to be done here, for the last 2015 onwards, Apollo started working in the talking tire domain. In fact, I was part of the team in talking tire where we are developing sensors where the tire can throw data. So we believe by 2035 there will be a great business opportunity in terms of talking tire, and we are preparing ourselves for that. So then, okay, one of the limitation for talking tire is that when the data transmission has to happen, this is the energy. As the tire moves, we cannot have a battery very quickly, it will drain out. We have to have an energy source. So energy harvesting, again, with Professor Srikala, we are working on an energy harvesting project. And also our Europe R&D is also having energy harvesting projects which we are working. Okay, there are many different technologies in terms of energy harvesting. I'm not touching upon those in the short because of shortage of time. And the next part, very short, I will touch upon within a minute. So, 2 ways of making the tire smart. One is putting the sensor. Another thing is that we all are material engineer. We also want, can my material be smart? Not only tire putting a sensor. Can suppose what I mean? So we are taking inspiration from the nature. Okay, the definition of smart materials. A smart material can be defined as a material that changes its properties. It's to or response on external stimulus as temperature, electricity, light, pressure, sometimes magnetic force. So these are the concept materials. If you say that like, okay, touch me not plants, or it is a sunflower, depending on the location of the sun across the sky, the direction changes. Or it is sea cucumber. Their properties inside the water is different, outside the water is different. So we are taking inspiration from them, and can be materials be made. So of course we are also exploring to the new ways of making the material smart by phase transition materials, by magnetoreological elastomers, basically having feelers which can respond to magnetic field, and all those because of the changes in magnetic field, because of changes the in heat, the behavior of the material will change. When the behavior of the material will change, their impact on the tire will change, which will make change the contact area of the tire. Okay, I'm leaving this part. So basically what we're seeing, this mechano-adaptive composites. So this is in a very early stage of research. Of course, advanced countries are exploring. Apollo is also started in a small way exploring of these materials. Okay, I will move over and okay, of course, everyone, the last 2 decades Michelin has shown the airless tire, 2-wheel tire. So now the new thing in this area is that now it is not that only everyone knows that polyurethane. It is not only the polyurethane in 2-wheel tires. There are a lot of new materials are being used to improve. So ceramic bulb, graphene, glass fiber. In fact, these are, we have reverse engineering. We are doing also what competition is doing. So these are the materials are being patented or being already in use in airless tiles. So these are the materials has to be explored. And yesterday there was a presentation with respect to intellectual property. I would like to just add this slide today morning. So with respect to intellectual property, Apollo is having more than 280 patents. In the last 3 to 4 years, we have filed 50 plus patents. Of course, if you consider 5 years back, our orientation towards IP creation was not that high, but now it is much better. Yeah, so the future outlook, what we would like to at the end of say, so sustainability, circularity, and technology. Technology means, I mean, the digitalization, the smart tires. This is what is going to the future. Yeah, with this, I will end my talk. Thank you.
Thank you. Thank you. I wish I give you more time, man. I wish I give you more time, but next time. Yeah, thank you. A lot of information.
So then you are inviting me for the next.
Yes, a long time. Give more time for you.
Fine. Thank you. Thank you, Param, and thank you, Professor Kimsuk, for giving me the opportunity to share our ideas. And of course, I would also like to thank our management to giving the opportunity, and in fact, giving the opportunity to explore this kind of projects. Thank you.
Thank you, Jyoti. Let me take you appreciation to you. Thank you very much. Thank you. Thank you, Jyoti. That's okay. So the last, not last one.
Dr. Soumyadeep, please join us to give a presentation on the actually this topic. I wish that I put in the yesterday. Lot of things happening in this area. Role of polymers in energy landscape. You want to put your slide, right? Yeah. Here.
Answer the question. Are you recording? Are you recording?
Yes. But I will delete it. You don't need to worry. Let me close others so that it does not affect you. Dr. Professor of the Rubber Technology Center, IIT Kharagpur. I do encourage all of you look.
Earlier version was better.
Sorry.
Earlier version was better.
No, we see this both,
Okay.
The screen. So yeah, that's fine.
Okay, thank you, Piram, for your introduction. Today I will talk about the polymers in energy storage landscape. So basically, we are polymer scientists, and the battery people are also there, energy people who are dealing with energy storage, energy efficient construction, energy efficient design, everything, but all end up with one one module or one product that deals with many polymer products. And I will briefly give an overview of how the polymers actually are standing in the energy storage landscape. The transition.
Yeah, I'll do it.
From here.
No, you can.
I can also do from here. Okay, fine. So basically, we know the importance of energy storage. We have a lot of material that can provide us energies. So, but we have to know that many of the energy resources, for example, the fossil fuels, they are very limited resources are there. Means they will, one day they will completely finished. So what will be the future then? So we have to think well in advance. So we have plenty of non-renewable energy resources, or renewable energy resources like wind power, solar power, tidal waves, and many more. So we cannot just fix a wind turbine and just sitting with the computer. This is not a direct plugging is not going to be a solution. So we have to use we have to store the energy, and we have to provide them, or we have to supply them on demand. So there are different battery storage modules. I will explain in a few minutes. This is a kind of plot. It's called Rugoni plot. In Rugoni plot, power density or specific power is plotted against energy density, and different energy storage modules are placed here and based on the relationship of power density and energy densities. So if you look into the fact that what is the worldwide energy demands and technologies, then we see that more than around 80% of the energy storage technologies was coming from coal in 90s. But the use of coal is declining, and the other storage technologies or other energy resources are coming into the picture. And now we can see from 2020 onwards, there is a steep rise of renewable energy resources. That means at some point we will see that the energy will be extracted from the renewable sources very future, and that should account for more than 45% of the total energy requirement. But the point is that, okay, if we go for this, and sometimes there are surplus of energy because we have wind, a lot of wind, we have a lot of sun, they are available, but there are no user. So that means the energy will be wasted. To avoid the wastage of this, so we need the storage devices, and one of them is the batteries or supercapacitor as well. So if we see in this plot on the right hand side, in 2010, the battery price was quite high. But with time, when we started to understand the importance of energy storage, then the battery price actually goes down because we evolve us with a lot of technologies, lithium-ion battery pack. We change the technology, we change electrolyte, we change the electrode, we change the design, many more factors we changed, and ultimately we are trying to get the lithium battery cost expecting to be below $62 per kilowatt hour at 2030. In that case, the new energy storage technologies should come up. So if you see the history of electrification, before combustion engine came, actually electric vehicle came. So you see in the year of 1830 to 1880, the electric car actually came out in the market, and that was looking like a rickshaw. So then once the gasoline actually invented, then we saw that, okay, this is much better because instantly we can get energy. We do not have to do a lot of electric things. So the arrival of petrol, diesel, actually then the electric vehicle went to the hibernation period. And so we keep on dealing with combustion engines. But once the alarm is there that the renewable energy resources are important and the coal and fossil fuels are getting diminished, so we rejuvenated the research of electric vehicles. And now 2021 to present day, that is, we are expecting the vehicle to be transformed to electric ones. If you see, the first practical electric car was introduced by William Morrison in late 18th century, and then it could run at 32 km per hour with 12 people on board. Later on, Daimler and Benz simultaneously developed world's first combustion engine automobiles in 1886 in Germany, and then the entire scenario of transport sector changed. And Porsche developed the world's first hybrid vehicle, while Thomas Edison even patented Henry Ford to build an affordable electric vehicle. But that also was in hibernation because that was a very high cost. It was very cost intensive. So we still keep on doing the combustion engine. Now here, interesting thing that supercapacitor and batteries are the major energy storage technologies. So what is the difference actually? The difference is the supercapacitor having very high power. That means it can instantly provide power. Means, for example, if you want to do arc discharge, supercapacitor can do, but battery cannot do, because battery provide a lot of energy with a lot of with prolonged time, and but it maintains a stable nominal voltage, where supercapacitor the voltage is declining. That means at their peak voltage they can give a lot of power. So this right hand side, the picture is from a bus that is running in Shanghai, and nowadays in Germany also I have seen this kind of ultra capacitor buses, where basically they are a supercapacitor and battery modules together, and they are called external hybrids. Means supercapacitor, they need very short time to charge, and then it can run for, let's say, 5 to 10 minutes. So for local bus, they are actually introducing this external hybrid concept, where the supercapacitor actually is running the bus, but once the supercapacitor got discharged, then the battery is charging it. So that means if you start from this stoppage and the supercapacitor is taking you to the next stop, and it stops for the passengers is getting into the bus and coming down from the bus, and by that time the battery is actually charging the supercapacitor, then it is capable of running again further, maybe 5 kilometers of distance. So these external hybrids, also there are possibilities to install internal hybrids where both supercapacitor and battery modules are inside the same chamber. Next, we can see the comparison of supercapacitor and batteries, and this plot which I was showing earlier, there you see the supercapacitor is here. That means it has very high specific power, but batteries are here. That means very high energy density, means or specific energy. That means none of them can provide both power and capacity, and power and energy. So here also you can see the power density of supercapacitor is very high, but here the energy density of battery is high, but supercapacitor is low. That is the point where we can think of a hybrid energy storage module, and that is one of my interest of my research group. So if you see the car developments, so once the discovery of oil came out, then the battery research went into a dormant research theme, and then once we see into 2000, in the year 2000, we started thinking about batteries, and then also the research actually also propelled up, and then you can see the list of publications on EV or HEV is steeply rising. That means we started knowing the importance, and then we are taking the action on it. In fact, there are different automobile companies who are now strongly investing a lot of money on development of EV and EDV. In fact, NASA also sent first man-electric lunar rover on the moon in 1971. So that means it can have the capability to reach the goal that IC can do, but it has to, the technology has to be matured, because there are a lot of factors behind. I will show one by one. Here you see the battery electrically driven vehicle EDV per capita. India is not there in the picture, because if we have a look into the number of electric vehicle and divide by the population, India cannot be in this picture. It will be so tiny. But if we want to invest the EDV, then we have to be affordable. And there is the key challenges that the battery car, if you want to go to the battery car, if you are thinking to buy a car purchase, first thing that you see that what is the cost, this is the first and foremost. Second thing, how many kilometers it can drive you per charging, and how frequently you have the charging stations, because in this case that infrastructure is not there in India as till date. So that means the batteries cost, its EDV cost is very high, only because the battery cost is high. So that means there should be a battery technology, for example, lithium sulfur, lithium air, which has the possibility to be at par with the IC this research has to be on board. So see, the India government also announced that they are going to launch the they have already launched the National Electric Mobility Mission Plan, and on this plan they are setting up 30% e-mobility by 2030. So in that case, in fact, the 49% of the total car has to be transformed to EDV. But to tell you the truth, that changing the passenger PCR means passenger vehicle, changing to electric vehicle will not solve the purpose. But we can make a drastic move if we can change the battery, means the truck and the huge heavy vehicles, that we can translate to EDV. Then only this benefit of the energy storage technology can be actually realized. Now IC versus EV engine, the basic difference is that you see the torque and power plot. Here for the IC, you see the torque is rising and then it is declining, and power is going rising, stable, and then it is decreasing. And for IC, that you can for the EV, you can see the power is actually increasing steeply with like a linear relationship, then it is stable. While the torque, initially a very high amount of torque is required, and then it is stable at high RPM, then decreases. Now anybody can guess why the torque, the power of EV IC is decreasing after a peak? Can anybody guess why it is happening? First of all, power, actually it is not power, it is called specific power, kilowatt per kilogram. Now you see that if you have full tank, that weighs something, and if you have a battery, that weighs something. So your total car weight is constant in case of IC, but in case of EV, but in case of IC, once you run your car, your tank get emptied. So this power, specific power, actually getting decreased. So as a result of which, you can see the power is decreasing. Okay. On the other hand, the EV, that you have a very high torque demand in the beginning, and then it's stabilized, and power is increasing with high RPM, then actually the benefit you can get at high speed. And this high amount of torque actually becomes our headache, because the tire that you are using for IC cannot be used in EV, because it needs a lot of high torque. Means it has to handle high amount of torque in the beginning, and also needs a high cornering force. So all these things are actually the key measures, performance measures for the EV tires. Now you see in the battery, actually we a material scientist make some battery material, then we make a cell, then cell are constructed in a module, and this module actually packed in a manner that can save some space, or it can accommodate in your vehicle. Most of the time you can see that these are placed underneath, means under your seat. So that means if the battery does not meet a safety requirement, then also you are also there sitting on a hot seat. So it may explode, it may make your life really problematic. So in that case, all these things has to be handled properly. This pack, housing, battery separators, everything, they are made of polymers. And I will quickly go browse through those aspects. There is a comparison, and then you can see the IC versus EV. There are a lot of benefits. One of them is quiet operation. It does not make any sound. That means if you want to run your EV, then you have to take care that the EV, as it does not make a sound, and one person is walking on the street, maybe in the middle, but unless he or she does not hear that the car is coming, he will not be on the side of the road. So that means an extra sound producing module has to be installed that will simulate the sound of an IC. So that means extra thing. Unnecessarily you have to put a sound producing device. And then the initial investment is quite high. High energy means battery means it needs a lot of cost that actually has to be borne by the customer. And infrastructure is one of the main lacking things. And batteries, you can see that if the batteries, if you drive IC, if you fill the tank, you can run for 600 kilometers, 700 kilometers per filling. But on the batteries, maximum you can run up to 200 kilometers, and that also dependent on how many passengers are sitting. So if you have less number of passengers, the car will drive more kilometers. So if you have full amount of all space of seats are occupied, then the battery will run less. Means it is obvious that it has to take the load of everything, as the load power is related to kilogram. So in that case, you are actually carrying a lot of kilogram. So in that case, your performance will be less. So major raw material commonly used lithium-ion batteries. There are different materials. I do not want to go in detail of these. Then the major challenges of EV weight. Electric cars are heavier in weight, obvious. Standard engines account for nearly 12%, but electric car powered car is about 25%. And also another thing is that the EV, the additional tire, the stepney, actually you cannot have the space for putting a stepney. If you want to put a stepney, then means the space for your battery is less. So definitely you can put a stepney, and then your battery longer, means more the battery modules, longer you can drive. So that stepney is also difficult to place inside. So that is also a corner. So to accommodate the additional weight per tire, the tire cavity needs to be strengthened, particularly in the tire sidewall region, because sidewall actually takes a lot of botherations. Now you see, this is a pure EV tire. To maximize the EV performance, the vehicle's aerodynamic drag coefficient has to be optimized. The tire's rolling resistance should be low, but also it should have a grip. But that grip should not be so high that to overcome the grip, your battery has to work. So battery has to work means your kilometer range will be less. Tread pattern has to be optimized, and sidewall design optimized, focusing on optimal traction, mileage, and tire handling characteristics. And due to the storage of battery, I told there is limited space. So as low as you can store for additional things like stepney. So instead of thinking of a stepney tire, you can design the tire in a way that it can self-heal. If there is crack or leaks, it can self-heal. Then that will add on to the milestone of your tire research. Now, EV tire suffers 25 to 30% less mileage, mainly to overcome high initial torque during start of the vehicle. It aggravates by vehicle weight. That means more passengers are there, so EV performance will drop by 25 to 30%. Impairs the overall tire performance like grip. Grip will be more with more weight on board, handling, and to balance the remarkable torque, tire has to be sturdy with very good grip, but that should not be so grippy that the battery has to work further. Due to heavy batteries and unusual vehicle load distribution in EV produces stress during acceleration and cornering. That is why the tire structure has to be carefully managed. Like this, it is noise free definitely. EVs are designed by design aspect. You can say this is noise free. For the safety of pedestrian that I mentioned earlier, that extra sound producing module has to be inserted, and tire designers need to careful consideration to balance the performance attributes and tread pattern noise. And now you can see the tread pattern. You can see this tread pattern has to have a good, balanced grip, stability, and efficient water dispersion to spill the water on two sides and to maintain low loading resistance. So how to get
achieve this. I just go in this. So if you see a conventional tire, you see this is quite wide, and some people prefer a thick tire, but this is not good for EV, because that means you have a wide tread area. That means more amount of grip should there. But on the other hand, the EVs, to control over the instantly high peak torque, handling and braking, and higher vehicle own weight, the harder tire is required. And traction which can withstand high torque acceleration can provide more mileage and low resistance compound. If you have such kind of larger diameter and high inflation, high and narrow tread, then the force per unit area is high. That means larger diameter narrow tread pattern reduces the tread deformations, contributing to low in rolling resistance. And it provides more friction due to more pressure per unit area and more area of contact. As a result of this, you have to handle less aerodynamic. Now, this is the important part of the tire, EV tire. This is the sidewall. The tires to be lightweight, and as well as it has to be sturdy and robust. So side tire walls should be reinforced so that it will be having high stiffness and maintain other performance characteristics to accommodate increased vehicle weight. And the sidewall can reduce tire damping coefficient and improve the ride at the cost of aerodynamic drag. So the tire sidewall has to be designed in a way to reduce the drag. And there is another possibility to introduce host layers of polyurethane foams and related materials for noise reduction in the tire cavity. So then this curve, you know very well that you have to have a good rubber. Selection of rubber should be there, and SSBR can be a good choice of rubber, and also silica. One of our colleagues, our chairperson, Professor Kingston Master, is working on the green tire technology, and he's working intensively on the silica reinforced things. So these are one of the major things that can reduce the rolling resistance, and also some self-thinning aspects. If that can be introduced, then the tire inner wall and side wall can be designed to perform to the best level. And definitely the silica and this SSBR, you need a coupling agent, so that also can be introduced to incorporate the fillers in. Now the fillers can be case, graphene, CNT, nanocellulose, and then also the silica. These nanofillers impart interesting properties as strength, modulus, mileage, rolling resistance, cut properties, air impermeability in small doses. And additives, you can add highly loaded silica-based tread compounds, commonly classified as processing aids and performance additives for better dispersion of fillers and set of performance like anti-reversion agent, cross-link modifiers, blend homogenizers, tachyfiers, coupling agents, etc. Piram, how many minutes are there? 5? Can I take 5 minutes only?
How much time you need?
5.
Okay,
5.
finish.
Okay. So now, just carcass, bell system. There are a lot of things. I do not want to go in detail, but I want to give an overview about this. For example, if you are doing batteries, now tire part is, for example, we have a optimized tire, but still you are not able to handle the batteries. So battery, there is one important part is that, carbon black. So as you know, the carbon black is very good, good conducting, but it can be having different structures parameters like high structure, low structure, high surface area, low surface area. So we can use carbon as additive and as active material. And in active material, we need high surface area, and as additive, we need low surface area but high structure to achieve these connecting points at the at very small dosage. So also we can design some kind of branch porous structures. That is also a kind of advancement doing this. My group is also working on different types of nanoporous architectures for batteries research to get this performance done. Now also if we have optimized carbon, then also you have to deal with the electrolyte. And electrolyte, not in water, also the organic solvents, they are also solvated. So solvated ion should go inside. So you have to have the passage of ions throughout the matrix. Otherwise, it cannot give the actual performance that you are targeting. So another work that we have done together with Professor Noshkar, that using polymer as solid polymer electrolyte. Here we have used special sorts of rubber. It's called gecko. It's epichlorohydrin rubber with different cross-linking possibilities and having oligoethylene units in the backbone, so that it can conduct, it can have high ionic conductivity. We have got quite promising performance, but here also again the thickness of the membranes were a bit high. So that has to be reduced without sacrificing the performance. And in that case, we can also replace the liquid electrolyte by solid polymer electrolyte. And here also we have the possibility to go for flexible batteries. Next is batteries. Once 2 electrodes are there, and if we are still thinking to use this solid polymer electrolyte, then our job is done. But if you are not using a solid polymer electrolyte, we can think of liquid electrolyte, and that has to be accommodated in a separator, very porous membrane that can absorb the electrolyte, rest onto it, and provide the electrolyte ions during the discharge. And during charge, the opposite things will happen, but the separator material actually avoid short circuit and accommodate the strength, volume expansion, many more things it can basically tackle. Different types of separator, stretch film separator, that you can stretch from both sides and the pores can be generated, and also you can have non-oven separators, different types of separators and glass fiber separators, all are available in the market. Now all set. Now also last part of the battery, that is one part I forgot that I will include in few seconds, that the packaging. If the battery is made, now you do not have a good packaging material, because packaging material is required if there is any leakage, if there is any heat buildup, if there is any thermal runaway, all these things can be tackled by the packaging material. And so in this case, the outer layer, barrier layer, inner layer, all these things are polymer made. So polymers are metallized and then they are used as a packaging material, and they also have a good sealing characteristics. Otherwise, the packaging material has to be a fixed part. So different polymers are used. Last but not least, polymers also, you have a carbon, you have active material, everything, but how to convert them to an electrode? So you need a binder. So normally porous carbon or whatever carbon you have to make a slurry and you have to coat or cast on a current collector so that the electrode can be ready. And then electrolyte, everything will be there, and then you can seal the material and the battery is ready. So with that, actually, I want to conclude that first of all, energy efficient storage technologies required for sustainable futures, and we have technologies like batteries and supercapacitor which have their own benefits and shortcomings. And ideal cases, if we can make a hybrid material out of these, so we can get also the power density and specific energy to a high level. So based on the demand, the module actually, energy storage module will choose which one to work. That is a kind of smart battery technology. And then polymers are everywhere in battery parts, electrode, and there are also redox polymers which can also work as electrode, but they cannot, they are lacking some energy density, specific capacity range. That is why we are not using. So we can focus on carbon, precursor, separator, electrolyte, binders, as well as the packaging materials in batteries and supercapacitor. That's all. I thank you for your attention.
Okay, thank you. This is an evolving area for the polymers, right?
Yeah.
So guys, any questions to Dr. Somadev? Okay, good.
Sir, I have just one doubt.
Yes.
What is the physical significance of energy density and power density? I'm not able to understand the concept.
Okay. For example, if energy density means, you know, supercapacitor that reacts very fast. So that means it within a second it can perform whatever you want. So that is actually can be correlated with the power density. And if a battery, it has means like supercapacitor, the voltage versus time has a linear relationship. That means it reached to a voltage, peak voltage, then charged and then discharged, and that total thing can happen within few seconds. But in the case of batteries, they have means basically in supercapacitor they are occur ion electrosorption. So make double layer and that gives you a voltage, but there is no redox process involved, and that is why the performance means the voltage drops, but at the peak voltage it will do its job. And like in cricket there are pinch hitters in the earlier time, now all are pinch hitters, so it is like pinch hitters. And now batteries, they have redox processes and they are slow relatively. It takes minutes or sometimes hours, but in total process, for example 10 minutes, 30 minutes, they attain a plateau voltage in which all this redox process occurs, and then this voltage actually you get from your battery over a period of maybe 1 hour, 2 hours, whatever is your discharge rate. So that means plateau voltage is there, so you have a nominal voltage. In supercapacitor you only can report peak voltage. As a result of this plateau voltage, you can report you can get a high specific energy or energy density. Peak voltage is important, means how high can go. For example, aqueous supercapacitor, you cannot go more than 1 volt or 1.2 volt, because aqueous supercapacitor the water splits, so you are limited there. And organic supercapacitor you can go up to 3.5 volt, 3.8 volt, but they drops also.
Yeah.
Thank you, sir. Nice presentation. The big challenge after recyclable or how to decompose?
Pardon?
Recyclable or how to decompose?
Means
battery.
The batteries. Yes. Yeah, actually the thing is that the battery recycling is a major challenge. First of all, battery littering is also a problem. And the opening of the batteries, the active materials are actually gone. But there are researches going on. I am not doing such kind of research. They are trying to extract the lithium, or they want to use the carbon materials. Also, they can be used. But normally what happens to the carbon, the ions are going there and it changes the entire morphology over means maybe in 1 year. Means in my battery that is present in my mobile phone, I am using it very badly. Sometimes fast charging, sometimes slow charging, sometimes power bank, and ions are moving a lot, so at high speed, so they actually destroys the electrode. So if you want to reuse, it is sometimes they are sacrificing the performance, but it can be used as additive, but a thorough cleaning is necessary.
Actually, we are thoroughly promoting eco-friendly like EV vehicle, but we are manufacturing battery, so some carbon be producing. How we can see the reduction of carbon footprint?
Some carbon is
using
battery
making.
Yeah.
How we can see the carbon footprint reduction?
No, if you can use the same carbon, I just reviewed some a couple of weeks ago a paper who are actually disassembling the battery, lithium-ion battery. They took out the graphite and they converted them to graphene, and they started using it again in another type of battery. So such thing also you can do. Okay, so you can use the carbon, you can just wash out very nicely so that no contaminations are present. Then you can use it again in the battery. But mind it, the performance may be sacrificed to some extent. Okay.
Okay, thank you very much, Dr. Thank you very much. Can you come forward, present this token appreciation to Dr. Sandip? Yes.
know Mr. Milind, right?
No, I am not.
Saga
working.
Elastomers, MD of Saga Elastomers.
Nice to meet you.
Maybe short introduction to Milind. So maybe you should talk about yourself a little bit.
Thank you.
Milind, few words about yourself and what you're doing.
I'm a person who's incidentally into rubber industry. I have done my electrical engineering from Vijay and then started a rubber factory. We had a lot of losses. Then somebody suggested that I should do rubber technology and then start a rubber factory. So while running the rubber factory, I did the rubber technology course and since I'm an engineer and have a lot of information and cannot do good marketing, so ventured into products which are difficult to make. And that is how got into this. This is a small, what I can say about myself. We have a studio setup in Palghar, near Bombay, about 100 kilometers. We have 2 micro lines and now also getting into more lanes. That's it. Thank you.
Thank you very much.
Thank you very much.
One more time. Okay. Thank you very much. One more presentation to go. Your professor. Okay, let me check whether he's on there. Okay, so we'll finish it off with that one. Professor Narayan Das ji, are you there? Professor Narayan? Let's see. Professor Narayan Das, are you there? I know it's been a long day for you, so we waited for this program. Yeah. Yes, open. Okay, he's here. Can you hear us? Just a second. Can you hear us?
You have to unmute. Unmute.
I think he's unmuted already. He's unmuted. Yeah.
Message.
You know, he's already unmuted and everything is fine. It looks like your phones are not good on speakers. You can hear us, right? You can hear us?
I think we can hear.
Yeah.
But we cannot hear. अपना फोन की स्विच ऑफ he cannot hear us, right?
He can hear us.
अपना फोन की स्विच ऑफ 1 minute 1 minute.
Okay, we have to go with signage.
Yeah, he's calling me. Yeah. Hello. না আপনার কথা শোনা যাচ্ছে না. Will he log in again?
No.
Log in করুন আবার.
Okay, try again.
Try again.
Okay.
করুন, আপনি আরেকবার লগ ইন করুন। জয়েন ওয়েবিনারে ক্লিক করুন, ক্লিক অন do not know the interface.
Everything is okay.
হ্যাঁ, অ্যাক্সেস টু দ্য মাইক্রোফোন কিছু চাইলে কিন্তু অ্যাক্সেস অ্যালাউ করতে হবে। হ্যাঁ, ওকে না করে দিলে হবে না। হ্যাঁ, ব্যাস হয়েছে।
কোনটা ধরে রাখতে হবে?
Not yet. ওই আপনাকে দেখাও তো যাচ্ছে না এখন। দাঁড়ান, ওই he has logged in again but he is not appearing.
Yes, open the camera.
হ্যাঁ, not yet. আপনাকে দেখতে পাচ্ছি না।
So voice না आ रहा है।
আপনি আমার ফোনেই দিয়ে দিন, স্লাইড গুলো চালাতে চালাতে যায়, আপনি ফোনে দিয়ে দিন। হ্যাঁ,
स्पीकर सेटिंग कुछ नहीं बदल दिया ना।
আপনার না, আপনাকে দেখা যাচ্ছে না এখনো। আপনার মাইকে কোনো প্রবলেম নেই তো? মাইক্রোফোনে মাইক্রোফোন অন হচ্ছে না, আনমিউট হয়েছে। হ্যাঁ, শেয়ার ইওর ওয়েবক্যাম করুন।
ये ओके ठीक है ना।
বলছে ঘুরছে।
नेटवर्क मेबी नेटवर्क इशू
सब ठीक है ना।
ওখানে নেটওয়ার্ক
আরো একবার করবেন, করুন। কালকে ট্রায়াল দিয়ে দিতে গুগল মিট।
Okay, let's maybe we had to make a decision that maybe next time I can record with him separate session and can share the file to the audience. Yeah, so no, because it's on. They don't have slides. Yeah. Mic problem.
কেন মাইক্রোফোনে তো আমাদের গুগল মিটে আছে। ও আই থিঙ্ক তো আপনার মাইক্রোফোনেই প্রবলেম আছে, বুঝতে পেরেছেন? আপনার মাইক্রোফোনেই প্রবলেম আছে। তাহলে একটা কাজ করুন, আরেকদিন আপনার একটা সেশন ইয়ে করে, হ্যাঁ, আপনি ইয়ের সাথে পেরামের সাথে একটু কথা বলুন না।
Professor Narenji, it looks like we have a difficulty. Yes, it looks like a difficulty. Already people waiting for your presentation. What I suggest is that we record it later and send to the audience later. Better, yeah. Yeah. Sorry to trouble you, but it looks like yeah. Understood. Yeah. Okay. Thank you for understanding. Okay. Thank you. Thank you.
Okay. His memento, I am expecting.
Sure.
And he is presenting to me.
Your place. Okay. Yeah. So.
Okay. We try. He should listen.
Oh, okay.
না, তাহলে একে কল করতে হবে।
Okay.
হ্যালো, বলছি আপনার মেমেন্টোটা কি? Should I accept your memento on behalf of you? No, presentation we will be recording separate session and then
Okay.
আচ্ছা, তো ঠিক আছে, তো আমি ওটা নিয়ে নিচ্ছি, তাহলে আপনার হয়ে আপনার প্রেজেন্টেশনটা আরেকদিন হয়ে যাবে। ঠিক আছে। ঠিক আছে, thank you.
Okay, we are taking the Dr. Swamidev taking the moment of the Dr. Professor Narayan Das. Give a big hand for Narayan Das. Yeah. Okay. Yeah. Thank
But
you.
he will be presenting.
Well, let me take a
in
picture.
your-
Yeah, of course. Let me take a picture, man. Let me take a picture. Let me take a picture. And I have to show, right?
The name should be visible. The white LED.
Oh, super. Okay. Okay. Thank you very much. Thank you very much. And I see she want to, yeah, come on, Param, let's wrap it up. Say goodbye, everybody. Right? She's waiting for how many times? Get up. I can feel for you. I can feel for you. It's a long day and it's been delayed. Okay. First of all, thank you all. Thank you all for joining. And I'd say the survivors, survivors of this Rubber Innovation Forum. It's with a good objective to promote innovations from young people, and it's something that we want to continue join together, journey together, and promoting the young researchers and connecting with the industry people. So that's an objective. I know we have hectic schedules we prepared. At the same time, sometimes some sessions took longer than we expected, but it's all for good. Some learnings as well. So I really thank you all for being part of this Rubber Innovation Forum. I'd like to invite Professor Kinsuk Naskar, the forum chairman, to say a few words about how you felt about it. You also want to get up and sit and get something like that, or? Okay. Professor Kinsuk Naskar.
First of all, I would like to say whoever is present, give a very big hand for Param first. It was not easy to organize, being in Thailand and organizing some event at Kharagpur, in Kolkata is not easy. So I think also Mr. Kamleshan has helped a lot. So we'd like to thank you as well. Yeah. And I will start with the research scholars first, okay? Kind of enthusiasm, what I noticed for the last 2 days, kind of interaction they had with those experts and other senior alumni of our department or other departments with the industries. I thought that it was learning experience for you guys, and please keep in touch with all of them, and also be in touch with Param for any sort of help. I think he's very helpful guy. He helps also with sometimes with the job opportunities. I see some posts and everything. So be in touch with him, and the delegates, of course, the speakers, the sponsors, and who came a long way. But last but not the least, it is just the beginning, I would say, and we shall continue. Okay, with your blessings, we shall do it again. Thank you.
Okay, one last picture together would be nice. Yeah, let's come together with the banner. Okay, photographer is here, right? Where is he? Yeah. Okay, great. Yeah, let's take a picture. Maybe another one.